In this video, we'll learn about the C++ if statement. The if statement is the most basic of the C++ selection statements, and its syntax couldn't be any simpler. We start with the if keyword, and this is followed with the control expression in parentheses. The control expression must evaluate to a Boolean true-false value. If the value of the expression is true, then the statement is executed. Otherwise, the statement is skipped. Note that the statement is indented. We indented our code in the main function, but indentation is a very important element of style that we need to start getting used to right away. By indenting the statement, it makes it easier for someone reading the code to see that the statement is part of the if statement. Remember, indentation and style is just for us human programmers to help us see the structure of the code. The compiler doesn't care where you place the statement. So you can see how simple an if statement is. Let's see conceptually what's going on in the if statement. Suppose we have this code. If num is greater than 10, increment num by 1. The expression num greater than 10 will be evaluated to true or false. If it's true, then num will be incremented. If it's false, no increment will take place. The flowchart on the right shows visually what the flow of control looks like. Let's see some simple examples of if statements. In the first if statement, we're checking if selection is equal to the character A. If it is, then we execute the output statement. If it is false, we skip the output statement. In the second example, we're checking if num is greater than 10. If it is, we execute the output statement. In the last example, we're using the AND logical operator in the control expression. In this case, we check to see if health is less than 100 and player healed is true. If both these expressions are true, then the entire control expression is true, and we set the player's health to 100. Otherwise, we skip the statement. What if you want to execute more than one statement if the condition is true? Well, that's where block statements come in. A block statement is a sequence of statements inside a block which is made up of opening and closing curly brackets. Notice the code on the left. The two statements in the body of the if statement are inside curly braces. If num is greater than 10, then the block statement is executed, which means that the increment and the output statements are both executed. The diagram on the right shows a visual representation of the control flow. Let's talk a little more about blocks. We've actually already seen a block statement. Remember the main function we've been using in all our programs so far? It has an open curly at the beginning and a closed curly at the end. This is a block statement, and we had sequences of statements in the block statement. Block statements introduce a new level of scope. We'll talk about scope as we go through examples in this course. But just like we declared variables in the main block, we can declare variables in any block, even in a block that's inside an if statement. Variables that we declare in a block are only visible to statements that are also in the same block. This lets us modularize our code so we have better control of who sees what, which makes writing and debugging our code easier. Let's head over to the IDE and we'll see some if statements in action. Okay, so I'm in the CodeLite IDE. I'm in the Section 9 workspace in the if statement project. And what I want to do here is I want to create a simple program where we'll create 4 different if statements. Let me show you what we'll do. Let's say we've got a number line here, and there's a minimum of 10, and the max is 100, let's say here. What I want to do is I want to ask the user to enter an integer, and I want to be able to check that the integer is greater than or equal to 10. So that'll be one of the if statements. I want to make sure that the integer they entered is less than or equal to 100. That would be the second one. The third if statement I want to write is I want to be sure that that integer they enter is within that bound. So between 10 and 100, including 10 and 100. That'll be the third one. And then the fourth if statement we'll write is we'll check that boundary condition. So we want to know whether it's actually equal to 10 or equal to 100. So those are the 4 if statements we'll write, and we'll talk a little bit about if statements as we go. So first thing I want to do is I want to create some variables. I need an integer. I'll just call it num, and I'll initialize it to 0. This is where I'm going to read the integer from the user into. And then I need to model those boundaries. So I'll use constants for that. I'll just say min and max, and we'll set min to 10, and we'll set max to 100. Okay, so that represents those boundaries. So the first thing I'll do is I'll ask the user to enter a number between min and max. Okay, simple as that. And let me put a little colon here so they can see what they're doing. And then what we'll do is we'll read that into num. That's the only input we're going to be able to get in this program, just a simple integer. We'll get it from the user. Enter a number between min and max. Let's test that, make sure we didn't make any mistakes. Enter a number between 10 and 100, exactly. And I'm entering 10. I'm doing nothing right now with it. And let me just get rid of that little extra space that I had there. Okay, so now let's write our first if statement. That'll be number 1 here. So I'm simply going to say if the number that the user entered is greater than or equal to 10, which in this case is min, then all I really want to say is, there's my output statement. I'm going to say num, I'll say is greater than min. That's it. All right, so let's test that out. So I am going to type something greater than 10 now. I'm going to type in 20. That if statement should fire, and I get 20 is greater than 10. Perfect. Now, if I type something in that is not greater than 10, let's say 5, I should see no output, which is exactly what happens because that statement will be skipped. Now, suppose that I want to display something else. I want to execute more than just that one statement. This is where you need a block. So I'll create a curly here, and I'll put a curly down here below the if. That establishes a block. Notice that I'm indenting. I'm not writing all my code all flush on the left. If you indent, it's much easier to see the structure of the code. And as you indent further and further and you nest things one within the other, the structure of the code really jumps out at you and it's very easy to follow. So in this case, I want to do a statement right up here. Since we're going to write 4 if statements, I'm going to say, let's do a /n to give me a new line at the beginning, and I'm just going to put some dashes, and then I'm going to say if statement 1. And I'll put some more dashes here at the end. You'll see why I'm doing that in a little bit. Okay, so if we run that now, we should see both of those lines display. So I'll enter something greater than 10. I'll put in there 30, and those are both my lines. My if statement 1 line as well as the 30 is greater than 10. So again, really simple. Anytime you want to execute more than one line of code or more than one statement, you need to wrap them up in a block. Now, suppose that I also want to display how far away that is from min. What's the difference between the number that I entered and min? Well, I could just subtract, right? It's pretty simple. So we could create an integer here, and I'll just call it, let me create a little space here. Okay, I'll have an integer. I'll just call it diff for the difference. And I'll initialize that to the number the user typed in minus the min, right? Because I know it's greater than min, so that's going to be positive. And then I'll just say cout, the number you entered is, and I'll use diff here, the difference amount, and I know it's greater, and I know it's greater than min. That's it. Now, it's really important to understand a couple of things here. One is this variable, I'm declaring that variable diff inside the block. You can see the block right here. There's one curly, there's the other curly. So what that means is that that variable diff is only available to the statements after I've declared it inside the block, basically. So it's only this block. That's it. Nothing else can see that variable. This is a good thing. If that diff gets a really screwy value in there and it's really out of whack, well, then the only place it could have changed that is this block. So I know exactly where to look. Okay, so let me clear a little bit of that. And what I'll do now is let's run this and see if this is correct. So I'm going to enter a number between 10 and 20 and 100. Let's say I want to enter 50. I know that that is greater than 10, and I know that it's 40 away from 10. So that's what I'm expecting. And there's my if statement 1. 50 is greater than 10, and 50 is 40 greater than 10. Perfect. If I, again, type something in like 5, I'll get no output. which is perfect. That's exactly where I want to be. So that takes care of that first if statement. Now let's write the second if statement. This one we're going to check to see if the number is less than or equal to max, right? So it's the same idea. I'm just going to say if the number is less than or equal to the max, that's the upper bound, then I want to display this cout statement. Let me just copy and paste that. And I'll just change this to a 2. So that's my if statement 2. And over here, I want to say that my num is less than, in this case. Actually, it should be less than or equal to, right? I should fix that up here because I know that it's greater than or equal to, since that's what I'm doing in my condition. Let's fix that real quick. There we go. That should do it. In this case, it's less than or equal to max. Okay, and let's do the difference here as well. Now here, if I just do something like diff is equal to max minus num, which is the calculation I want to do, but when I compile this, you're going to get an error. It's going to say diff was not declared in the scope because diff is gone now. Diff was declared in this block. That block is finished, so diff isn't even visible anymore. So I need to create another diff. So if I just say int diff, and I'll just initialize it to max minus num, similar to what I did above. This creates a new copy of that integer diff that's only visible to this block here. Now, sure, I could have just created that diff way up here, like I did with num, and it would be visible to everybody, but I just wanted to show you how the scope rules work. Okay, so there's my diff. Now I'm going to say cout the number you entered is diff amount, in this case less than max. And I'll finish that off. Okay, so let's run this and test this out. All right, so let's type a number like 80. We expect both those if statements to fire, right? Because 80 is greater than 10 and it's also less than 100, less than or equal to 100. So there we go. Both if statements fire. 80 is greater than or equal to 10. 80 is 70 greater than 10. And over here we're saying 80 is less than or equal to 100, and it's 20 less than 100. So both those if statements fire. But let's test this with other numbers here. So let's say I type in 150. In this case, only if statement 1 fires because 150 is greater than or equal to 10, but it's not less than or equal to 100. Okay? Same thing if I type in, let's say 5. Only if statement 2 fires now. Okay, so hopefully that makes sense. So now, the third if statement we want to write is the one that's right here. It's going to check to make sure that that is within the bounds. Okay, so in this case, what we'll say is if the number the user entered is greater than or equal to the min, and the number the user entered is less than or equal to the max. Remember, you've got to do this here with num. You've got to write that word in. You can't just say less than or equal to max. You've got to say num less than or equal to max. Again, I'll have my block statement here. Notice that when I type that beginning curly, CodeLight finishes it off with the close curly. And let's copy this guy right here. And we'll say that this is if statement 3. And in this case, we'll just say something like cout num is in range, let's say. Okay, so we know that it's within that range. There's no difference here to take care of. We could do differences, but let's just do that. What's interesting here is that statement 3 will only execute when statements 1 and 2 execute, right? Because we're in range. We're greater than 10 and less than 100. So let's write that down as well. We'll say cout. This means statements 1 and 2 must also be true. Or must also display in this case. Let's just say display. Okay, hopefully that makes sense, because you can see what's going on here. If I entered a number that's in range somewhere in here, then obviously this is going to be true and this is going to be true. So we'll have all three of those statements displaying. Okay, so we'll run this and test it. We'll enter a number in the middle. Let's put in 50. Notice all three if statements fire, which is exactly what we'd expect. If we type in a number that's greater than 100, only if statement 1 fires. And if we enter a number that's less than 10, only if statement 2 fires. Okay, so now the last one we'll do is we'll actually check to see if it's right on those boundary conditions. So we'll say if the number the user entered is equal to the min, or the number the user entered is equal to the max. Notice how you have to have that or in there. The and would not work because it's never going to be equal to both. So in this case, we just care if it's equal to one or the other, in which case we'll output statement 4. We'll change that to a 4 real quick, and I'll leave this code available for you guys to play with afterward and mess around with it all you like. And then what we'll say is cout num is right on a boundary. And what's neat about this one is that if this one fires, then all 4 statements must be firing. So again, I'll say that all 4 display. And we'll give this a quick test. Okay, so let's do one of the boundary conditions, 10. There you go. All 4 if statements fire because 10, obviously, we're in the range, we're on the boundary, we're greater than one side and we're less than the other. So we're good here. And again, if I just type a 5, only that second if statement fires. So you can see some of the logic. Now, what's important to understand here, let me just clear the screen real quick. What's important to understand here is a couple of things. One is these are independent if statements. There are no else's in here. We'll talk about else's in the next video. So this statement will execute. So that condition is checked. If this condition is true, we execute this code. Then we come here and we check this condition. So we're basically checking the condition for all 4 of those if statements. Okay, so hopefully that gives you some insight into if statements. They're pretty straightforward. Remember, this condition we have in here could be anything. We could use relational operators like we're doing here. We can use equality operators like we're doing down here. We're comparing num and min. We could use logical operators like we're doing right here. We can use all kinds of combinations of these things as well. Okay, so that finishes up off this video. In the next video, what we'll do is we'll talk about the if-else statement. In this video, we'll learn about the if-else statement. Adding an else section to an if statement is the obvious next step to improving control flow in a program. Many times, we want to perform different actions depending on whether the condition is true or false. Again, the syntax for the if-else statement is very simple. We have the same syntax as for the if section as in a simple if statement, but we add the else keyword and the statement we want to execute when the condition is false. So in this case, if the control expression is true, we execute statement 1, and if it's false, we execute statement 2. Notice the indentation. I can't stress enough how important good indentation and style is. By simply looking at the construct, we can easily see both sections because it's indented properly. In this slide, you can see example code and the flowchart that visually shows the flow of control. The condition num greater than 10 is evaluated. If that's true, we increment num. If it's false, we assign 10 to num. In both cases, we then continue execution to the next statement. Let's see a few more examples. In the first statement, we check if num is greater than 10. If this is true, we display num is greater than 10. If it's false, we display num is not greater than 10. In the second example, we check if health is less than 100 and heal player is true. If both these conditions evaluate to true, then we assign 100 to the player health. Otherwise, we simply increment the player health. Here we could see sample code along with a flowchart that visually shows the flow of control. Notice that in this example, we're using two block statements in the if-else statement. So if num is greater than 10 is true, we execute both statements in the block. We increment num and we display increment. If num is not greater than 10, then we assign 10 to num and display reset. Regardless of which block statement executes, we continue processing. Finally, let's see another example where we group if-else if statements. In many cases, we can group if-else statements together. Here's a common example. Suppose I want to display a student's letter grade given their score on an exam. In this case, we can check if their score is greater than 90. If it is, we display an A and we're done. No other conditions will be checked. So we continue to the last output statement and display done. Suppose the student scored a 75. First, we check to see if the score is greater than 90. It isn't, so we go to the next else if, score greater than 80. Again, it's not true. Then we check score greater than 70. Now it's true, so we display a C and we're done. No other conditions will be checked, so we continue to the last output statement and display done. Notice that the last else in the construct doesn't have an if associated with it. This is the catch-all else statement. If none of the previous if statements is true, then this else statement will execute and F is displayed. This is a very, very common pattern that's often seen in programming. It's efficient since no extra checks will be performed once we know which condition is true. We could obviously change the logic and start with score less than 60 and work our way up to an A. Let's head over to the IDE and see some examples in live code. I'm in the CodeLite IDE. I'm in the Section 9 workspace in the if-else statement project. This one's really, really simple. The user is going to enter a number and we're going to store it in num. And we're going to compare the number to a target. In this case, I just assigned 10 to the target. So we'll ask them enter a number and I'll compare it to 10 in this case. Okay, we get the number from the user, and then we've got a real simple if statement. If the number is greater than or equal to the target, we're just going to display this line, and then we're going to display the number they entered is greater than or equal to the target. That's it. We're also going to calculate the difference between the number and the target and display the difference. So in this case, in this piece right here, this is the if statement right there. That's the if section. That's the true section. We're going to say, yeah, the number you entered is greater than or equal to the target. It's so far away from the target, it's so much greater than the target. That's it. Now, if the number they enter is not greater than or equal to the target, then the else part fires. And in which case, we're still going to print a line, and then we're just going to say the number you entered is less than the target. What's the difference between target and number? And we're going to display that difference as well. Okay, so really, really straightforward program. Let's compile and run this. So in this case, let's enter a number and I'll compare it to 10. Let's say I enter 10. It says 10 is greater than or equal to 10, which it is, and 10 is 0 greater than 10, because it is 10. Perfect. So let's run this a couple more times. Let's put in 100, and we get 100 is greater than or equal to 10. 100 is 90 greater than 10, right? And let's put in like negative 10. In this case, negative 10 is less than 10, and negative 10 is 20 less than 10, which is again correct. So you can see, real simple program. Adding an else section to the if statement is really, really simple. And actually, it's super powerful because it gives you, the ability to have a binary decision and execute code on both sides of that decision. In this video, we'll see how we can nest if statements within other if statements. Many times the logic we need to use in order to solve problems is more complex than just an if-else decision. Many times we need several layers of logic. Since an if or if-else statement is a statement, then we can use it in C++ anywhere a statement is legal. So in this case, we can replace the statement part of the if statement with an entire if-else statement if we want. That's exactly what this example shows. Notice the indentation. It becomes even more important now. In this case, we can test multiple complex conditions easily. So we evaluate expression 1, and if it's false, we skip everything. But if it's true, then we test expression 2. And if it's true, we execute statement 1. If it's false, we execute statement 2. We can continue by including if or if-else statements as we need. Notice that we have 2 ifs and only 1 else. In computer science, this is called the dangling else problem, and every programming language has to decide how to handle it. The problem is, which if does that else belong to? In C++, an else belongs to the closest if. Of course, we can use block statements to achieve any logic we want. Let's see another example. In this example, we check if score is greater than 90. If it is not, then we skip down to the bottom output statement and we display sorry, no A. If the score is greater than 90, then we check the nested if statement condition and check if score is greater than 95. If it is, then we display an A+. If it's not, we display an A. In this slide, we can see a flowchart that visually shows the flow of control for the logic in this example. Notice the first condition is checked, score greater than 90. That's the expression in the first diamond on the left. If true, then we test the condition in the nested if statement, which is on the true branch. Of course, we can also use block statements as required to execute multiple statements. In this example, we're checking if Frank's score is not equal to Bill's score. If this fails, that means that their scores are equal, so we go to the else statement and display looks like a tie. If their scores are not equal, then we check the condition in the nested if statement, and if Frank's score is greater than Bill's score, we display Frank wins. Otherwise, we display Bill wins. In these examples, the nested if has been in the true section of the if-else statement. We can have nested if statements in the else section as well. Let's go to the IDE and see some examples of nested if statements. Okay, what I want to do next is I want to open up the grades project within the Section 9 workspace again. In this case, the main is empty, and I'm just going to get rid of this piece right here just to print out a new line at the end. Okay, so what we're going to do here is this program is going to ask the user for the score on an exam between 0 and 100, and we're going to tell them the letter grade, similar to what we did in the slides. But we want to validate to make sure that what they entered is actually between 0 and 100. And if it isn't, we're going to tell them, sorry, you need to, the number you entered is out of range. Also, once we determine the student's grade, we'll tell them your grade is, your letter grade, A, B, C, D, F. And if they get an F, we'll tell them, sorry, you have to repeat the class. Okay, so let's start here. First off, we need a couple of variables. Let's just use one called score. That's what we're going to ask the user for. And we'll say cout. Let's do the input-output part really quickly. We'll just say enter your score on the exam. And we'll actually put 0 to 100 here so they know what the range is. And we'll grab the input into score. Okay, so now we've got what we want. We also would like to have a variable called letter grade. And what we're going to do is we're going to assign A, B, C, D, or F into that variable. We can simply use a character variable. That'll be fine. So I'm just going to say char letter grade. And we'll just initialize it to 0. Okay, so now the first thing we need to do is we need to validate that score. We need to make sure that the score is between 0 and 100. So we'll use a simple if statement here. So we'll say if the score is greater than or equal to 0, and the score is less than or equal to 100, I'll use a block here. We need to do the true part, right? This is where we need to calculate their grade. But if it's not, then right here, we want to say else, and I'll do another block statement. And in this case, what we want to say is, sorry, we'll say sorry, and we'll tell them that the number they entered is not in range. Something real simple. When we learn about looping in a couple of videos from now, we'll be able to ask them to enter it again. But in this case, this will be fine. And let's test this. A lot of times when we test our code, you see there's nothing in here right now. So we just do something like this, and we expect to see that output in the positive case, right? In the true case. We're going to write code in there to actually calculate the grade, but it's good to test as you go. Don't write all your code all at once and then try to test it all at the end. Just test as you go, and you'll be much better off. So let's try this. Let's run this. Got an error here. Sorry. Num. It's not num. It's score. There we go. So there we go. Enter your score on the exam. Let's enter something valid like 70. We should get the X's displayed. There they are. So we're good here. And let's run it one more time, and let's type in 120. Sorry, 120 is not in range. And let's try something like -1. Sorry, -1 is not in range. Cool. So our logic seems to be right. Now what we need to do is write the logic in this piece right here that's actually calculating their grade. All right. So what we can do here is we can write the if, else if type code. When I learned this stuff a long time ago, that was called an if-else ladder. I haven't heard that term in a long time, but it makes kind of sense because it does look like a ladder. So what we'll do here is we'll say, we'll use that same grading scale, 90, 80, 70, 60. We'll say if the score is greater than 90, and I'm not going to use blocks here just to save some space on the screen. We'll say the letter grade, and we'll assign an A to it. Now notice that's a character. So those are single quotes, not double quotes. So we've got that. Then we'll say else if score is greater than 80. We'll say letter grade is a B. Again, single quotes. Don't forget the semicolon. Else if, you get the idea, we're just walking right down that ladder. If it's greater than 70, then the letter grade, in this case, is a C. Couple more. Else, if the score is greater than 60, then the letter grade is a D. And finally, there's our catch-all else, in which case their letter grade is an F. Okay, let's try that out. Let's run this. We'll test it with a few numbers. And I said greater than 90. I probably should have said greater than or equal to 90, but it's all good. So we'll say 91. That's definitely an A. We never printed it out, so let's do that. This is why we test, right? See out your grade is, and we'll just display letter grade here. We'll put an end line at the end. Okay, now remember, I'm going to put this here and fix that V to a C. This will execute no matter what. So this if statement will execute. One of those letters will be assigned, and then we display it here. All right, let's try that again. So in this case, we got a 91. That should be an A. Your grade is an A. The 81 should be a B. It is. Let's do about a 50. Which is definitely an F. And here we go. Okay, obviously you would test this a little better, but for the sake of time, I'm not going to do that. The last thing we want to do is right here, we want to tell them, did they pass or did they fail? Well, the only way you can fail in this example is if your letter grade is an F. Right? So there's no sense in checking the score again. We've already got the letter grade. So I'm simply going to say if the letter grade is equal to an F, remember, double equal sign, not a single equal sign. If that's the case, see out. Sorry, you must repeat this class. Okay, otherwise you passed. Congrats, that's a passing grade or whatever you want to enter in here. All right, so that should do it. Let's go through this real quick one more time. We've got their score here. We're prompting for the score and we're reading it in. If the score is within range, we do the calculation. If it's not within range, we're down here and we're out right away. Sorry, the score's out of range. Let me clean that up a little bit. If the score is within range, then we're going to use this if-else ladder. And if it's greater than 90, it's an A. Greater than 80, it's a B. We're going to walk all the way down. You know what? Let me put equal signs here because it's bugging me. That way it matches the slides that I gave you. Okay, so that's a little better. So now if it's greater than or equal to 90, you get the A and all the way through the F. Then when we're here, your grade is your letter grade, and then we check to see if an F. If it's an F, you must repeat the class. Okay, let's run this now with a couple of test cases. Suppose you got your 90 now. It should be an A because we have the greater than or equal to. Your grade is an A. Congrats. If your grade is 59, your grade is an F. Sorry, you must repeat this class. Okay, so there you go. That's a simple example of using the if, else, if, and the if, else statements together. On the next example, we're going to open up the shipping project in the Section 9 workspace. So we're in the shipping project of the Section 9 workspace. And I've gone ahead and started this little example just so we'll save a little time. And what we're doing here is we're using a shipping cost calculator. We're going to ask the user for the package dimension in inches, and the package dimensions would be length, width, and height, and they're all integers. The dimension must be 10 inches or less for each dimension, otherwise we can't ship it. The base cost for shipping is $2.50. And if the package volume is greater than 100 cubic inches, there's a 10% surcharge. If the package volume is greater than 500 cubic inches, there's a 25% surcharge. Okay, so I started this already and I've got some variables set up, and let me talk about them really quickly. We've got, obviously, we need the length, the width, and the height. That's what the user is going to enter. And we've got the base cost, which is a double at $2.50. So I've initialized that. Then we've got a couple of other constants here. One, the tier 1 threshold, that's the volume. So if you exceed 100 cubic inches, that kicks in. And we've got the tier 2 threshold to be 500 cubic inches. So I've defined those as constants. The maximum dimension for any length is 10 inches. And I've got the tier 1 surcharge at 10% and the tier 2 surcharge at 25%. So that's pretty much it. I've got all these constants and variables declared so that I can use them. All right, I also have another integer here called the package volume, which obviously we need to calculate. So this is where we're at. Hello, welcome to the package cost calculator. Enter the length, width, and height of the package separated by spaces. And we've just read the length, the width, and the height into these variables. Now we need to do our logic for the calculation of the package. First thing we should do is let's make sure that the package is valid, right? Otherwise, there's nothing to do. So what we can do here is we can say if the length of the package is greater than the maximum dimensions, right? The max dimension length, which is 10 for everything, or the width is greater than the max dimension, or the height is greater than max dimension, right? If any one of those is greater than the maximum allowed dimension for any one side, we really have nothing to do. We're done. So in this case, what we want to do here is we want to say cout, sorry, package rejected or something like that, dimensions exceeded. Okay, or some message that tells them what's going on. Okay, so that takes care of that. Now here's the else part, right? And we may as well put this in a block because we never know when you're going to add code to this. So I'll put a curly here and a curly here. Now I can add code in there easily. So that's my my if part. This is when the package has been rejected. The else part is now where we're going to do all our calculations. So again, I'm going to do cout and do a quick test to make sure that we're compiling and everything looks good. So I'm going to run this, and I'm running the old project. Let me double click on shipping, and let's try that. Enter the length, width. Okay, so let's say I'm exceeding, right? So I'm going to say 12, 8, and 12, 5, and 3. So the 12 should be over. Sorry, package rejected, dimension exceeded. That's good. We could do test cases for all three of them, right? I'm not going to, just to save a little time. And in this case, 6, 7, and 8, that's valid. And we print out the 3 X's, and we're ready to do our calculation. Okay, so let me get rid of that statement that I just did and that hello world down here at the bottom. All right, so now in here, what we need to do is our calculations. So we need to know what the package cost is, right? So we need to have a double in here. We can do that right inside the block, because the only time we're going to use it is if we're going to do some calculation. So in this case, I could just say package cost, and I can just initialize that to 0. And how about the package volume? Again, I could have defined that in here as well, but it's already defined outside. The package volume is the length times the width times the height. Okay, so now we've got our package volume here is being calculated as the product of those 3 dimensions. And we may as well say that the package cost is the base cost, right now. We could start with that. It's always going to be $2.50 plus perhaps some surcharge. Okay, so that's where we're at. So far, so good. Now we need to do these checks for the package volume exceeding those thresholds. What we want to do first is we want to check the tier 2 threshold, because it's the highest. So what we want to do here is we want to say if the package volume is greater than the tier 2 threshold, if that's the case, then the package cost plus equals, we're incrementing that by the package cost times the tier 2 surcharge. Okay, remember, we're incrementing the left-hand side by the right-hand side. And we could put a debug statement in here. Again, it's very common to do that. Just saying adding tier 2 surcharge. You can get rid of these when we ship the code, but it's nice to have them in here. Soon I'll teach you how to use a debugger, which makes this even easier. Okay, so if this is not the case, then we can say else if the package volume exceeds the tier 1 threshold. And if that's the case, we can basically just copy this, and I'll paste it in here. In this case, the package cost is the plus equals package cost times the tier 1 surcharge, and we can just change that statement right here to do that. Okay, so we're really done. What we need to do now is say cout the volume. We'll give the user some information. The volume of your package is, and we'll display the volume, package volume. We have an end line here, and then we'll just tell them how much it's going to cost. I mean, that's really what they want. Your package will cost, and we'll put a $sign here. And I believe it was package cost. There it is. To ship. And that should do it. Let me clean up some of this white space. And we'll run this, and then we'll do one more little thing before we go. And let's see, tier 1 surcharge. I spelled it wrong. I should need an underscore right there. And that way you can see some of these errors. Perfect. So let's say 5, 5, and 5. I'm adding a tier 1 surcharge because the volume is greater than 100. You can see here's to 125. So the package will cost $275 to ship. Let's make it a little bit bigger, the package. Let's say it's 8 by 8 by 8. In this case, I'm adding a tier 2 surcharge. The package volume is 512, and it's going to cost $3.12 to ship. Okay, now you'll notice this 3.125 displays. I'll show you how to set that a little bit later in the course, but for now, I'll just show you how to do it really quickly. If you come up to the includes and you include IO manip, that's the input-output manipulators, and then right before you start printing the dollar amounts, or actually anywhere, you could put this anywhere, you could just say cout fixed, followed by set precision to 2 decimals after the package. That just prints dollars nicely. So if we run this again, let's try that again. We'll do 8, 7, and 9. You could see it prints it out nicely, $3.12. And again, I'll talk about those manipulators a little bit later on. It just helps us look at our code a little nicer. All right, so there you go. There's some logic for shipping this package. We've got an if-else statement. We've got an if-else-if statement. And hopefully this logic makes sense. Again, build these programs one step at a time, testing as you go. In this video, we'll learn about C++'s switch statement. As you've already seen, it's very common to have to execute specific sections of code depending on the value of a constant. For this particular use case, the switch statement comes in very useful. We'll learn the switch, case, break, and default keywords. The syntax for the switch statement is a little more involved than the if statement, but it's not too bad once you understand what it's doing. First, we have the switch keyword, which is followed by the control expression inside parentheses. This control expression must evaluate to an integral type or an enumeration type. Then you have a series of case statements enclosed in curly braces. The value of the control expression will be compared to the values following the case keywords. These case statements must also evaluate to an integral or enumeration type and must be known at compile time. That means they must be constants or literals. When the value of the control expression matches the case expression, then the code after the colon is executed until you hit a break statement. The break statements are optional, but best practice is to include break statements for every case statement unless you've got a really good reason not to. In the next several slides, we'll go through the behavior of a switch statement with and without break statements. Finally, a switch statement can have a default case at the end that will execute when none of the cases is true. This is similar to that catch-all else at the bottom of an if-else statement. The break statement is not needed in the default case. Let's see some examples of the various forms of the switch statement. In this example, selection is a character type, which of course is also an integral type. We assume that the user has entered a character at the keyboard and it's been assigned to selection. We can write if-else if statements to execute code depending on the character entered, but in this case, we can use a switch statement since the control expression is an integral type and the case statement contains character literals to match. So, suppose the user enters the character 2. The switch will start at the first case statement and compare the 2 to the literal expression following the case keyword. So the 2 will first be compared to the 1. Since this is not true, we proceed and check the next case statement. In this case, we have a match. So all the code following the colon will be executed. Notice that we can have multiple statements here without the need for a block. However, if you need to declare variables in this section, then you need to put the curly braces in for a block. So we display 2 selected, then we execute the break statement which completes the switch statement. No further cases will be checked, and we continue with the rest of the program. Notice that in the case of 3 and 4, we display 3 or 4 has been selected, and then we're done with this switch. This is handy since we can write logic that's equivalent to an OR statement, as we see in this case. Finally, the switch has a default case. If none of the previous case statements match, then we execute the default, which in this case displays 1, 2, 3, 4 not selected. No break is needed in the default statement. Also, the default statement is optional, but it's best practice to include one. Let's look at an example where we don't have some break statements. This is an example of the fall-through behavior of the switch statement. Notice that there are no break statement in cases 1, 2, and 3. Case 4 is the only case that has a break statement. Suppose the user enters the character 1, and it was assigned to selection. We check the first case statement and it matches, so we execute the code following the colon. In this case, we display 1 selected. Now we continue executing code going straight down the switch statement until we hit a break statement. So in this case, we also display 2 selected and 3 selected and 4 selected. Finally, we hit a break statement in case 4, and we're done with the switch. Remember, once a match is made, all the code in the switch cases, including and following that match, will be executed until we hit a break statement. No other conditions will be checked. This sort of logic can be handy in some cases when you want to execute a subset of statements depending on various conditions. However, this should not be the way you normally code a switch statement. Best practice is to include a break statement in every case statement. If you need logic that falls through, please document the code and be very clear in the documentation that the fall-through behavior is what you intended. If another programmer sees the code and needs to modify it, they'll understand this and be very careful when adding or removing new conditions or statements. Let's see an example of using a switch statement with an enumeration. In this example, we see an example of using a switch statement with an enumeration type. We have an enumeration type called color with 3 enumeration constants, red, green, and blue. We also have a variable named screen color, which we initialize to green, but it can hold any of the 3 enumeration constants. Using this enumeration variable in the switch statement is a very common use case and a great way to execute code depending on its value. In this case, we switch off the screen color, which can only be red, green, or blue, and we execute the appropriate code when we match the specific value. Also notice that in this case we're supplying a default case, but this should never execute unless we add another enumeration constant to our enumeration and forget to include a case for it. So let's review what we learned about the switch statement. The control expression must evaluate to an integral type. The switch statement is commonly used with enumeration types. The case expressions must be known at compile time, so only constants or literals can be used, no variables. Once a match occurs, all code in the following case statements is executed until a break statement is reached. Finally, best practice is to always include break statements for each case and also provide a default case. Let's head over to the IDE and see some switch statements in action. I'm in the IDE in the Section 9 workspace in the Switch project. And what we're going to do, we're going to do a little program here that uses a switch statement. We're going to ask the user what grade they expect on an exam. That'll be a character, A, B, C, D, F. And we'll tell them what they need to score to get it. Okay, so I made a start here where we have a letter grade, that's a character, and that's what the user is going to enter. We prompt the user to enter the letter grade they expect on the exam, and we read that into letter grade. Okay, so now what we want to do is we want to switch off of letter grade. It's a character, so that's definitely an integral type. So we'll say switch, and we want to switch off letter grade. Okay, I'll put in the syntax I need, which is the open and close curlies for my switch statement. Now what we have in here is we need to provide the cases. Now in this case, we could provide upper and lowercase for each character. So we could say case lowercase a and case uppercase a, I want the same behavior, right? Because the user could certainly type a lowercase a. So if they type a lowercase or an uppercase a, all we'll say is cout. Let's say you need a 90 or above. And we'll tell them to study hard. Okay, so that'll be the statement for that specific case. We need a break, otherwise we'll fall through. I don't want to fall through in this example. And let's do the B case. Again, lowercase and uppercase. And also remember that I'm using single quote marks here because these are characters. So in the case of a B, if that's what they want, I'll say something like you need 80 to 89 for a B, and we'll say go study. I'll use an end line here. And again, I want to break. Let's do our C case. There's only a couple left. So there's my lowercase c. Here's my uppercase c. And in this case, I'll just say output something like you need 70 to 79 for an average grade, let's say. And we'll end line here. Again, a break. We'll do the D case. And here we'll say something like, I don't know, like, you should strive for a better grade, huh? Let's just say all you need is 60 to 69 or something like that. And we'll put an end line here as well. Of course, the break is required here because I don't want to fall through. And then in the case of F, again, lowercase f or uppercase F. Here we'll just do cout. Let's just put a little placeholder here to test ourselves because we want to add a little bit of code here once we finish this example. Okay. And we'll break out of here. Our default is going to say something like, sorry, that's not a valid grade. And I think we're pretty much done here. Okay. Let me clean that up just a little bit. So let's look through this right before we run it. We're grabbing the letter grade from the user. We're switching off of it. We're checking for lowercase, uppercase A. We've got a message, the B, the C, the D, the F, and sorry, not a valid grade. And we'll get back to the F in a little bit. We'll write some code in there. So let's execute this. Enter the letter grade you expect. I want an A. You need 90 or above. Study hard. Okay. Let's do the B. I'll do a lowercase b this time. You needed 80, 89 for a B. Go study. And let's do the F. And there's my X's. Okay, so what we want to do now is, in this case right here, in the F case, let's ask him, are you sure you really want an F? Did you type this incorrectly? So what we want to do is we want to write a little if-else-if statement here. And I'm going to declare a variable in here. So I want to be sure that I'm using a block. And I want to use the block right in here like this. Okay, so I'm going to get rid of this guy. And I want to put the break inside this block. Sometimes the IDEs don't put those curlies in the right places. I think it's okay now. Okay, so this is the logic I want here. So I want to have another character. And I'll call it confirm because I want to confirm that they really want an F. And we'll initialize it to blank, to 0. And then we'll say cout, are you sure? Or something like that. And we'll say yes, no. Okay, so they'll enter a yes or a no. And I'll read into confirm. Again, so they're going to type in a character, either yes or no, hopefully. So what do we do? Well, let's say if they type in a yes, uppercase or lowercase, we'll give them a message. If they type in a no, we'll give them another message. And we've got to make sure that they type a yes or a no. If they typed anything else, we'll give them a little message that says, I have no idea what you're saying. Okay, so let's do that. Let's say if the confirm character is equal to a lowercase y, or the confirmed character is equal to an uppercase y. Remember, don't forget to do the double equal signs here because we're comparing. So if that's the case, and I'm not going to use any block statements here because I don't need to, I'll just say cout Okay, I guess you didn't study. Or I guess you don't want to study, right? And I'll give them an end line here. Okay. Else, let's check to see if they actually typed no, because it could be anything else now, right? All we know is that it's not a yes. So in this case, we'll say else if confirm is a little lowercase n, or again, confirm is an uppercase N. And then we'll just simply say something like cout good. Go study. So now here we need that catch-all else, right? At this point, they typed something in other than a yes or a no. So what do we do here? We tell them, boy, you really do want that F, right? We'll just say cout illegal choice or something more clever if you like. Okay, that should do it. Now, because I'm creating and declaring that character right here, I need those curlies inside the block. Otherwise, if I was not declaring a variable here, I don't need to put the curlies. But once I have to declare a variable, I need those curlies. Right? So let's execute this and see what's going on. Okay, so what's the letter grade? The only one I really changed was the F. So let's type the F. And now it says, are you sure? I'll say yes. Okay, I guess you didn't study. Exactly what we expected. Let me run it again with the F. Are you sure? Nope. Good. Go study. And then we'll just give it another character. Again, we'll go F. And let's say, are you sure? Q. Illegal choice. There you go. So here you can see some logic using the switch statement with a character, which is an integral type, a bunch of literals here with the lowercase a's and so forth. And in the case F, we've got some if-else-if logic going on as well. So you could see that the logic for this is pretty straightforward. The switch statement makes it nice to do. It's kind of long. The code is pretty wordy, but it's very, very easy to see, very easy to understand. And when you read this, I mean, it can't get much clearer than that, right? You're switching off a letter grade, if it's an A or an A or a B or a B, really, really clear. Indentation, again, and style, really, really important. If everything here was at the same level all the way on the left-hand side, it would be really, really hard to read and figure out what goes where. Okay, so that takes care of the switch statement in this context. Next, we'll do the switch statement using an enumeration, and we'll do that one really quickly. Okay, so I've switched to the switch enum project, and I've started it already, so let's go over it here. What I've done here is I've created an enumeration type called direction, and you can see it right here between lines 10 and 12. And the enumeration constants are left, right, up, and down. So it's pretty straightforward. Remember, when you declare an enumeration, you're creating a new type, so we can create variables of that type. So heading is of type direction, just like we could have said I is an int. And we're initializing it to left, which is one of those enumeration constants. Okay, so now what we want to do is we want to switch off of that heading. Heading is an enumeration, so basically it's an integral type. That's what enumerations are. So here I'm going to type in switch, and I want to switch off heading. In this case, our cases are left, right, up, and down, right? They have to be. They can't be anything else. Let me get rid of that extra curly here. So we can say case left. And then at this point, we could just say something like cout, let's say going left. Just something really simple so that we know we hit the right case. And we'll put an end line here. And of course, I want a break. Okay. We'll say case right. And we'll do the same thing. I'll just copy and paste these two lines to save a little time. And now I'm going to compile this. And you'll see the issue that we see right away. And let me just clean this up just a little bit. Okay, so let's compile this. I get a run that says going left, just like I expect, right? But look down here, and you've got some warnings. The warnings are saying, warning, enumeration value up, not handled, right? Warning, enumeration value down, not handled. This is telling you that the compiler understands that there are 4 enumeration constants here. You're using an enumeration variable in your switch, but you're only handling 2 of those cases. Well, C++ gives you the warning. A lot of other programming languages now won't compile this. This will be an error. They force you to handle all the types. So you could create 2 more types for up and down, or you can use a default that's going to catch everything else. And I'll just say OK here. And now, no warnings, all good, and we're going left. Okay, so that's really what I wanted to show you with the enumeration types. When you use them with switch statements, I mean, there's a reason you create an enumeration type, right? You've got these enumeration constants, so that variable heading could be any one of those 4. So you really should be handling all 4 cases in your switch, or using a default to handle the fall through in case one of them doesn't match. Okay, so that finishes up this video with the switch statement. In this video, we'll learn about C++'s conditional operator. This is a really neat and very useful operator. The operator is represented by the question mark and the colon symbols, but they aren't used next to one another. The conditional operator is a ternary operator, which means that it operates on 3 operands. The first operand is the conditional expression, which is usually in parentheses. The conditional expression is evaluated first, and it must evaluate to a Boolean or true-false value. Then we follow the conditional expression with the question mark part of the conditional operator, followed by expression 1, then the colon part, followed by expression 2. This may sound complicated, but it's really super simple. The conditional expression is evaluated. If it's true, then the expression returns the value of expression 1. If it's false, then the expression returns the value of expression 2. You can see it's like an if-else construct in a single expression. While this operator is very handy, it's also easy to abuse. Best practice is to never nest a conditional operator expression within another one. This leads to if-else-if logic that quickly becomes unreadable and difficult to manage. Let's see some examples of the conditional operator. In this example, we have variables a and b initialized to 10 and 20 respectively. We also have score initialized to 92 and result initialized to 0. The first assignment statement uses the conditional operator on the right-hand side. First, we evaluate a greater than b. If a is greater than b, then the value of a is assigned to the result. If a is not greater than b, then we assign the value of b to result. That's it. You see, it's very straightforward. You can see this works exactly like an if-else statement, but it's more concise. The second example evaluates if a is less than b. If this is true, then the value of b minus a is assigned to result. Otherwise, the value of a minus b is assigned to result. In the third example, we're using the conditional operator to avoid a divide by 0 error. First, we check if b is not equal to 0. If this is true, then we divide a by b and assign the result back to result. Otherwise, we simply assign 0 to the result. Notice how we're avoiding a divide by 0 error by making sure that b is not equal to 0 before we divide. Finally, we often see the conditional operator used in output statements. In this case, we check if score is greater than 90, and if it is, we display excellent, otherwise we display good. You can see the conditional operator can be very handy and easy to read and understand when it's used this way. Let's head over to the IDE and see it in live code. Okay, so now I'm in CodeLite. I'm in the Section 9 workspace in the Conditional Operator project. And what I'd like to do is just go over a couple of real simple examples of using the conditional operator. First, we'll write it using a regular if-else statement, then we'll write it using the conditional operator. Okay, so let's get started. Let's create a variable here. We'll call it num. And this is what the user is going to enter an integer into. We're going to save it into here. We'll prompt the user to enter an integer. And we'll read that integer into num. Okay, simple as that. Now, what we want to know is we want to know whether the integer they typed in is even or it's odd. So let's use a simple if-else statement. We'll say if the number they entered, mod 2, is equal to 0. Okay? In this case, we're dividing by 2 and we're looking at the remainder. So obviously, if it's an even number, the remainder will be 0. That's what we're testing. So in this case, we'll just say cout. Let's say num is even. And in the else case, obviously, it has to be odd. Okay, so that's real simple logic here. Let's test this out. Yeah, I forgot the L in the end line. Okay, so an even integer. Let's say we want to type in 6. 6 is even. That's correct. We'll run it one more time with 7. 7 is odd. Simple as that. Now let's rewrite this if-else statement just using a simple conditional operator that's inside of the output statement. So we'll say cout, and we'll say same thing, num. Now here's where we'll put the conditional operator. Num is, and right here is where we'll put the conditional operator. Okay, so in this case, we need to wrap this up, and we'll put the conditional operator right in here. So we're going to test to see if num mod 2 is equal to 0. Okay, if that is the case, then I've got my question mark, which gives me the true side, and I'll just say even, and the colon, odd. That's it. And we'll end this with a new line as well. And let's run this and see what it looks like. So we'll put in 2, and we can see both of those statements fire because we've got the regular if-else statement going. And let's try to run it again with 3. There we go. Now let's see what's really going on here. In this case, again, we are testing to see if the number is even. If this is true, then this piece is the one that's going to, remember, we've got an output operator here, an insertion operator. So this is going to be replaced, this whole thing right here will be replaced with even, the string even. If it's false, it'll be replaced with odd. So we've got the same thing going on here, right? Num is even, num is odd, except that it's all in one statement like that. You may be wondering, why in the world would you do this? Well, a lot of times it's really handy to not have this sort of logic here, but rather put something right in a print statement. So suppose we've got some sort of output statement and we've got some kind of looping thing going on, and every 10th time I need to do something, or I need to print something different. It's real handy to use this operator in that context because it makes your code a lot cleaner. And if you use it properly like this, it's really easy to understand. Okay, let's do another example, and I'll comment this out here. And let's just do a real simple example. It's just going to compare 2 integers. Okay, so we need those 2 integers here. We'll call them num1 and num2. And we'll tell the user to enter 2 integers separated by a space. Okay, and we'll read into those 2 integers, num1 and num2. All right, so in this case, I want to display the largest and the smallest of those 2 integers, but I want to do it using the conditional operator. So the first thing we need to do is we need to see if the integers are the same, right? If they are the same, then we'll just say they're the same. There is no largest or smallest. So let's do that logic first. So we'll say if num1 is not equal to num2, in this case, we want to say, okay, one's bigger than the other. Which is biggest, which is smallest, right? The else case means that they're the same. So let's handle that case first. So we'll just say cout, and we'll just say something like the numbers are the same. And I'll put a new line at the end. Okay. Now, this is the logic we need to figure out now. We need to figure out what's the largest and what's the smallest. I could write an if-else statement in here a couple of times, right? But in this case, I'm just going to do it right in line with an output statement. So let's do the first one. We'll say cout. And what I want to do here is I'll just say the largest, because that's what we're going to look for first. And now we'll use the conditional operator. So again, I'll put the parens in there. And I'll put an end line at the end. Might as well do it now. Now the logic in here says, okay, let's test to see if num1 is greater than num2. Right? If it is, I use the conditional operator and display num1. If it's not, I display num2. That's it. Simple as that. And over here we'll say cout smallest, and same sort of logic. We'll come right into these parens right in here, and what we'll do is we'll test, in this case, num1 less than num2. And if it is, num1, otherwise num2. Okay, that's it. Let's run this. And it says no, it should have been num1. Enter two integers separated by a space. Let's do the equal case first. The numbers are the same. That's good. Let's do a 5 and a 10. Largest is 10, smallest is 5. And now let's do a 10 and a 5. Largest is 10, smallest is still 5. So we're good. So here's a real simple example of using the conditional operator. We'll use the conditional operator in a couple places as the course progresses. And typically it's going to be inside a loop as we're looping and we want to do something every 5th time, 10th time. You know, let's say every 5th time you want to print a new line or something like that. Then this makes a lot of sense to do it inside, right inside an output statement like this. In this video, we'll do a quick overview of looping in general and specifically in C++. Looping is also called iteration or repetition. It's the third basic building block of programming. After this section of the course, you'll have all you need to begin to solve very complex problems using sequence, selection, and iteration. In this course, we're covering C++. However, all programming languages must support sequence, selection, and iteration. Once you understand these concepts completely, then it's just a matter of picking up the syntax of another programming language, and you'll be able to implement solutions to problems in those languages as well. Loops allow the execution of a statement or block of statements repeatedly. And they're made up of two sections. First, the loop condition, which determines when we iterate and when we don't. Second is the loop body. That's the statement or block of statements that will be repeated. That's it. Conceptually, it's very simple. Let's look at a few use cases for looping. Here are some typical use cases for looping. We want to execute a loop or repeat statements a specific number of times. For example, we want to do something 10 times, or we ask the user how many times they wish to do something. Another use case is iterating one time for each element in a collection. So suppose we have items in an array or a vector, and we want to process each of those items. Other times we want to loop until a specific condition becomes true. So we loop until we see a specific value, then we stop. Of course, we can also loop forever. This isn't as common as the other use cases, but operating systems are an example of programs that loop forever executing system processes. There are many other use cases and variations of these existing use cases. Let's look at the C++ looping constructs now. C++ has three main looping structures: the for loop, the while loop, and the do while loop. The for loop has a range-based variant, which is really great. First, let's talk about the for loop. The for loop is typically used when you want to iterate a specific number of times. For example, you want to loop 10 times or n times, where n is determined by the program. The range-based for loop makes it really easy to iterate through a range of items or through the elements of a collection. With arrays, vectors, and other collections, this is a great loop to use. The while loop iterates while a specific condition remains true. When the condition becomes false, we terminate the loop. In the case of the while loop, the condition is checked at the beginning of every iteration. The do while loop is similar to the while loop, except that the condition is checked after each iteration. With only these basic loops, we can implement any iteration pattern we want. All programming languages have loop constructs. The C++ loops are clear and concise. Let's go through the C++ loops one at a time. Let's start with the for loop in the next video. In this video, we'll learn about the C++ for loop and a few of its variations. The for loop consists of the for keyword followed by 3 expressions in parentheses. Each of these expressions is separated by semicolon. The semicolons are required, but the expressions are all optional. We'll see more about this later. In its simplest form, the for loop has an initialization expression followed by a conditional expression that evaluates to a Boolean, and then an increment expression. First, the initialization expression is executed exactly once before any iteration occurs. Then the condition is checked. If it's true, the body of the loop is executed. Then the iteration expression is executed and we check the condition again and repeat. When the condition evaluates defaults, the loop is terminated and we continue processing the statements that follow the loop. As you can see in this examples, the for loop can execute one statement or many statements by using a block statement. Let's see a simple for loop that counts from 1 to 5. Let's walk through this for loop one step at a time. Notice that in order to count, we need some sort of variable. It's common to use the variable named I as the loop variable that's incremented or decremented in the loop. In this case, we declare I to be an integer and initialize it to 0. Now we enter the loop. The first thing that happens is the initialization. In this case, we assign 1 to I. Now we check the condition. Since 1 is less than or equal to 5, we execute the body of the loop, which is the output statement, and we display 1. Then we execute the increment expression, which increments I by 1. Note that ++I and I++ mean the same thing here, since the increment happens on its own and it's not in another expression. So now I is 2. We check the condition again and it evaluates to true. So we execute the body of the loop again and display 2. Then we increment I again and keep iterating. After we display 5 items, I will be 5, and then we increment it to 6. At this point, the condition fails and the loop terminates. C++ for loops are very efficient and in their basic form very easy to read and modify. Let's see another way to declare the looping variable. We can declare and initialize the looping variable I in this case right in the initialization statement. This is very commonly done and has some advantages. Here you can see we're doing it using 2 styles. The first uses initialization style and the second uses assignment style. I will be using initialization style in this course. The looping variable I is only visible inside the for loop. Once the loop has finished, I is no longer visible and you'll get a compiler error if you try to use it. This is a great feature since you know that I is totally under your control within the loop and won't have any strange values coming into the loop or exiting the loop. Let's see another example. In this example, we're looping from 1 to 10. The body of the loop tests to see if the remainder of I is 0. So it's testing to see if I is an even number. If it is, then it displays I. So this loop displays all the even numbers between 1 and 10 inclusive. Let's see how we can use a for loop with an array. In this example, we're using a for loop to display the elements of an array. Here we've declared scores as an array of integers and we've initialized it to 100, 90, and 87. Since array indexes begin at 0 and go to size -1, we must be sure to stay within those bounds or our program could likely crash. So we declare and initialize I to 0 and our loop condition is I less than 3. And we increment I by 1 at each iteration. So we loop for I equal to 0, 1, and 2, which is exactly what we want. The body of the loop simply displays the array element at index I. This will display 100, 90, and 87 as we want it. Be very careful when you work with loops and arrays. The condition should either be less than the size of the array or less than or equal to the size -1. Hot tip, always use one or the other and stick to it. Don't start flipping between them because eventually you're going to make a mistake. I always use less than the size of the array, and I've been doing it that way my entire career. This helps prevent what are called off by one errors, which basically mean that we went over bounds and your program could crash or corrupt data. C++ has an operator called the comma operator that isn't used very often in C++, but sometimes you see it used in loops to initialize loop variables. The comma operator allows you to separate expressions with a comma, and both expressions will execute. Note that the associativity is right to left, and the result of the comma operator is the leftmost expression. In this case, we're just using it to initialize two variables, and then to increment those two variables. In this example, we want I to start at 1 and j to start at 5. And we want a loop while I is less than or equal to 5. The output statement in the body of the loop displays I times j, the product. Then the increment also uses a comma operator to increment both I and j. So in this case, I goes from 1 to 5 and j from 5 to 9. And at every iteration, we display the product of I and j. Walk through this example slowly yourself, and you'll see that it's pretty straightforward. The syntax looks a bit odd though, since there's so much going on. The basic for loop with all three expressions is concise, easy to read and modify. In the examples I showed, we used integers, but you can use doubles with for loops as well. Also, I counted up in these examples. You of course can count down. But since the expressions are all optional, it's possible to have all sorts of variations. You could even have a for loop with just the semicolons in the parentheses. This is by definition an endless loop. Best practice and pro tip: don't write for loops with missing expressions and complicated expressions with comma operators. The example I showed is simple and understandable, but if you find that you're omitting expressions, then consider using one of C++'s other loops. Great, let's head over to the IDE. We'll see some examples of the for loop in live code. I'm in the CodeLight IDE, and I'm in the Section 9 workspace in the for loop project. What I want to do here is I want to write a few different for loops. We'll write a bunch of them that behave differently. Some will count up, some will count down. So you get a feel for how these for loops work. And I'll write them and I'll comment them out along the way. That way they'll be in the source file so you can play with them later. So let's do a simple one first. Let's just say something like for int I, we'll start I at 1. That's the initialization expression right there. And then we want to loop while I, let's say, is less than or equal to 10. And at each iteration, what we want to do is increment I by 1. Now, in this case, I can say plus plus I or I plus plus. It means exactly the same thing in this case. And I'll simply output I. Okay, simple as that. Let's run this. And you can see we're going from I1 to 10. Obviously, when I hits 11, this condition right here fails. And I stop the loop, and then I just hit this end line over here, right before the return. Okay, so real simple example. Now I'll just copy and paste this so that you can see a variant of it. And I'll comment that out. Here now, suppose I want to go from I to 10 by 2. I don't have to increment by 1. I can increment by whatever I want. So I can, here in the increments expression, I could just say I plus equals 2. So I equals I plus 2. So we're going to do the same exact thing, except when we increment, we're going to increment by 2. So let's run this one. And there you go, 1, 3, 5, 7, 9, exactly what I expect because I'm starting at 1. And then eventually it's going to hit 11 and it'll fail. Okay, so hopefully that makes sense. Let's count down on the next one. So let me comment that out. And let's do this now. Let's say for int I, and again, I is a real common variable name to use with looping I, j, k. You'll see those all over the place in C++ code. So let's say I want to initialize I to 10 in this case, and I want to loop while I is greater than or equal to 0. Let's just say greater than 0. And in this case, I want to decrement I every time. Okay, so again, I'm starting with I is 10. And as long as I is greater than 0 or I is positive, I want to execute the statement, which I'm going to write right now. And again, I'm just going to output I. And then I want to decrement I. So this should count down now. So let's try that out. And there you go, 10, 9, 8, 7, 6, all the way down to 1. If I write in something like this, let's say blast off. Then we expect that to execute after the loop is done. See that? So that works out perfectly. There's your blast off. And one quick thing, some compilers, not all compilers, but some compilers will give you a warning when you indent wrong. Okay, so in this case, if I indented cout this blast off statement over here, that's not correct, right? Because I don't have curlies. So this for loop really only executes that one statement. But when I see this code, visually, my eyes are telling me that those two statements are in the for loop, but they're not. If I try to compile this, notice it works, but I get a warning. The warning says, warning, this for clause does not guard. That's not real helpful, I know, but notice the warning message. It says misleading indentation. That's a great warning. A lot of compilers don't do that. So what it's telling you is that something's not right with the indentation. You may think it's doing one thing, but it really isn't. So once you unindent that and indent it properly, now you'll have a clean compile with no errors and no warnings. That's a really nice feature of the GCC compilers. Okay, so let me comment that piece out again. And let's write another version of a for loop. In this case, why don't we count from 10 to 100 by 10? So again, for the initialization statement, and I will initialize it to 10. Remember, that only happens exactly one time right before the loop begins. And I want to loop while I is less than or equal to 100. And at each iteration, I want to say I plus equals 10. So I want to increment by 10 each time. And I'm going to put in a block statement here just because I'm going to use a few other statements in a bit. But right now, let's just print I. Okay, so again, we're going from 10 to 100 inclusive by 10. So we expect this to print out 10, 20, 30, 40, all the way to 100. Let's try that out. And that's the result, from 10 to 100 by 10, exactly what we expect. Now, suppose I only wanted to print out those numbers that are between 10 and 100 by 10 and also divisible by 15 without a remainder. Okay, so what we can do here is we can put an if statement here. We can say if that specific I I'm looking at, mod 15 is equal to 0. Right? So if that thing is divisible by 15, then I want to display it. So at this point, out of those 10, 20, 30, 40, 50, and so forth, we really only expect 30, 60, and 90 to match this criteria. Those are the only ones that are divisible by 15, I'm sorry. So let's run this. And there they are. 30, 60, 90 are the only ones in that set that are divisible by 15. Now let's take a look at that comma operator I talked about. The syntax for this is, again, it's not bad. It just gets kind of long and convoluted. So let's try that out. Let's say for. Now in this case, in the initialization statement, I want to initialize more than one variable. So I can put them all in here separated by commas, not semicolons, commas. So I'll say int I, and I want to initialize I to 1. Now I put a comma in there and j to 5. That's my initialization. I'm setting I to 1 and j to 5. Now comes my loop condition. I want to loop while I is less than or equal to 5. And now is the increment expression. So where I say, what do I want to do at each iteration? Well, I want to increment I, and I want to increment j. So I can put the comma operator there and increment j. Okay, so you can see the purpose of this operator within this for loop is just to make everything concise, because it makes sense here, right? I mean, I want to initialize I and j before I loop, and I want to increment them both at each iteration. So rather than spread this logic all over the body of this loop, you can just put it right in the header like that, and it really conveys exactly what you want. At this point, I can just have a simple output statement that, let's say we want to add I and j at each iteration. So I want to display I want to display the plus symbol. I want to display j. I want to display the equal sign. That's a literal. And let's just display I plus j. And we'll end that with a new line. So let's run that. And you see we have 1 plus 5 is 6. Now, I encourage you to walk through this example. I mean, grab your pen kind of like I'm doing right now and say, okay, this is I, this is J. Right now I've initialized them, right? 1 and 5. Now I start the loop. Is I less than or equal to 5? Well, I is 1, so sure, it's less than or equal to 5. I execute the body of the loop, which says display I, okay, 1, then the plus, then the J, then the equal sign, and then their sum. Then we do the increment, which means now I is 2, J is 6, and just walk through the loop this way. This way you really get an understanding of what's going on. Remember what happens. We do the initialization one time, then we check the condition, then we execute the body if it's true, and then we do the increment. So that's the order that this is all happening in. Okay, so let me close this up. And let's say that we wanted to use, let's use that conditional operator inside the loop, just like I showed you in the conditional operator video. There's a handy way to do it here. So suppose I want to print out the numbers 1 to 100 in a little bit of a table format. So they look nice. There's 10 across. So 10 rows of 10 columns each. How could I do that? Well, I could do something like for int I. We can start at 1, and we want to loop while I okay, let's try that again. Let's loop starting at int I set to 1, and I want to loop while I is less than or equal to 100, and at each iteration I want to increment I. Okay, so that's what I want to do. I'm going to put a block statement here so I can write a little bit more code. Now, I want to output I. And I don't want to put an end line here. I just want to output the I itself. And what I want to do is every 10th I want to output a new line. Otherwise, I just want to output a space to move them across the row. So let's do that with the modulo operator. I can say if I mod 10, so if it's the 10th item, equals 0. What do I want to do here? Well, in this case, I just simply want to say cout, give me a line. And if I is not the 10th item, I simply want to output a single space. Okay, that's it. So let's run this and see what we get. You can see we're going 1 to 10, 11 to 20, 21 through 30. And again, walk through this and you'll see exactly what's going on. It should be pretty clear here. I'm printing out the I, and I'm checking for every 10th item. And if I get every 10th I, I'm going to print a new line. Otherwise, I just put a space. If I wanted to print this as 5 across, I can just change that guy right there from a 10 to a 5. And now I've got 20 rows of 5. Okay? So that takes care of that one. Now, suppose I wanted to write this same logic using the conditional operator. Well, let's see. Let's get rid of this stuff here. And what we can say right now here with the conditional operator is we could say, let's output that I, and then let's output, let's check the condition, right? Same condition we had before, I mod 10 equals 0. And if that is true, we just display a new line. We'll use the escape character. Otherwise, just a space. And if we run this, we should get exactly the same behavior we had before, which we do. Okay. Now, remember, since we're outputting, and we can chain output, we can actually just get rid of all of this stuff and just make it all in one line. We can do that. We can output the I followed by either a space or a new line. So this can be just written as a single line. And we get the same behavior as before. Okay, the last example I want to go over is using a vector. And let me comment that out. In the slides, I showed you how to do it with an array, how to loop through an array. And here I'll show you how to use a vector. And in the next video, we'll use the range-based for loop, which makes using vectors really, really simple. But in this case, let's create a vector. And I'll just give myself a little room here. And I'll just call the vector nums. And it's going to be a vector of integers. Let's just call it nums. And let's initialize it to, I don't know, let's say 10, 20, 30, 40, and 50. So we've initialized it to those 5 numbers. Now remember, we're using a vector, so we have to include vector. So I'm going to come back up to the top and pound include vector, otherwise we'll get a compiler error. So I'll come back down. So there's my vector. And let's say I want to loop through that vector and just display each item in the vector. Pretty easy. I could say for int I, and I want to initialize to 0. Remember, vectors start at 0, just like arrays. And I can say while I is less than nums.size. We'll use the size method that is in the vector class. Okay, that tells me how many items are in the vector, and I want to increment by 1 each time. And I just simply want to say cout nums sub I. And when I run this, I expect to get 10 through 50. We're going to get a warning, and I'll show you how to fix that warning in a second. And it's actually a good warning, but there you go. 10 to 50 is the output. That's what we expected. We're printing out all of those elements. The warning says, warning, comparison between signed and unsigned integer expressions. Okay, what's going on here is that this nums.size expression right here is returning an unsigned integer. That makes sense, right? Because you can't have vectors that are negatively sized. So that's returning an unsigned integer, and you're comparing it to a signed integer. So you can just simply type unsigned here instead of signed, and it actually makes more sense. I've been using signed integers all along, but a lot of times when you're looping, especially when you're looping through all the positive numbers, it makes sense to use unsigned integers here. So I'll save that. We'll compile and run. And now we've got down here, as you can see, no errors, no warnings, and a clean compile. Okay, so that pretty much covers the basics of for loops. I will leave all these examples in this source code so you can play with them and change them around as you like so you can learn from them. The best way to really learn this is just to make up little examples and print out every 5th element and see if they're divisible by 7 or something like that. And just really get a feel for the way that loops and walk through these examples one step at a time. That really, really is helpful. In this video, we'll learn about a really great feature that was added in C++11, the range-based for loop. This loop really makes C++ feel like a modern programming language. The idea with the range-based for loop is to loop through a collection of elements and be able to easily access each element without having to worry about the length of the collection or incrementing or decrementing looping variables or subscripting indexes. The syntax is very simple and elegant. We have the keyword for followed by open and close parentheses as usual. Inside the parentheses, we provide the type and name for the variable we want to use in the loop body. This variable will be bound to each element of the collection, so it should be of the same type as the collection elements. Then we provide a colon and the collection or collection name. That's it. Now when we access the variable name in the body of the loop, it will have a specific element in the collection. Pretty cool. Let's see an example. In this example, our collection is an array of integers named scores that we've initialized to 100, 90, and 97. And here's the code that iterates over that collection using the range-based for loop. Notice that in the parentheses, we provide the type of each array element. In this case, it's an integer. And we provide the variable name that we can use in the body of the loop. In this case, score. Finally, we provide a colon and the name of the collection, which is scores. That's it. Now we can use score in the body of the loop. The loop displays 100, 90, and 97, which are the elements in the array. See how much cleaner and less error-prone this is. It was a great addition to C++. We actually don't have to explicitly provide the type of the variable. Instead, we can use the auto keyword. This tells the C++ compiler to deduce the type itself. In other words, you're asking the C++ compiler to figure out the type based on the declarations. So in this case, the compiler sees that you're using a collection scores in the loop. So it looks at scores and it sees that it's an array of integers. So it uses an integer for the score variable. Pretty easy. Actually, in this case, using auto versus int doesn't really buy us much, But C++ can have very complex collections, and sometimes defining the type of a collection variable can be quite long and tricky. Auto makes it dead simple. In this example, we want to calculate the average temperature from a vector that contains doubles that represent temperatures. The vector in this case is called temps, and it contains 4 doubles. In order to calculate the average temperature in this vector, we need to iterate over the vector, access each temperature, add them all up, and divide by 4. That's it. Notice the for loop and how simple it is. It's saying loop through the temps collection, and each time through, assign a temperature from the vector to the loop variable temp, which the compiler deduces to be a double. We add this to our running sum. Then when the loop is done, we perform a simple division to get the average. Notice that I'm using the vector's size method, which returns the number of elements in the vector. In this case, it will return 4. The range-based for loop can also use an initializer list as a collection. Let's see that one. This example also calculates the average of 4 temperatures. Notice how we can explicitly provide the collection right in the for loop. This is sometimes handy when you know the elements of your collection ahead of time and they won't change. The only downside is that you have to calculate the size as you go. In this last example, we can use the range-based for loop to iterate over a string, which is a collection of characters. In this case, the string is the literal franc, but it could be a variable. We're going to discuss strings in the next section of the course. Well, that pretty much covers the basics of the range-based for loop. Let's head over to the IDE and see some examples. I'm in the CodeLite IDE in the Section 9 workspace in the range-based for loop project. What I'd like to do in this example is go over a couple of examples of using the range-based for loop with an array, with a vector, and with a string. So the first thing we'll do is just use a simple array, and you'll notice that I've already included vector right up here since I'm going to use vector in a minute. So let's create an array of integers, and we'll call it scores. And we'll initialize it, let's just say 10, 20, and 30. Okay, so what we want to do now is we want to iterate through that collection. It's an array in this case, using the range-based for loop. It's as simple as can be. We can say for int, because we know we've got integers here. And what do we want to call each int? We'll call it score, because that's what it is, a single score. Then we have the colon, and then we provide the name of the collection, in this case, scores. So that's the loop header. And then all we really need to do here is just say cout and display the score. That's it. Let's run this. And that's exactly what we get, 10, 20, and 30. Now, as I mentioned in the slides, we don't have to provide that int there. We can simply use the auto keyword. And what's going to happen here, I mean, it's pretty straightforward, but it's important that you understand what's going on. You're telling the compiler to figure out the type. So the compiler is going to come in here and say, okay, what's going on? The collection is scores. Okay, scores is an array of integers, so this must be an int. So it's going to deduce that type right here to be an int. Same as we did before. As I mentioned, this is not a big deal. It's easy to type int. It's easy to type auto. But collections in C++, especially generic collections and templates, get really crazy syntax. And sometimes it's very difficult to write exactly the type that you want. And this just makes it so easy. You just type auto and the compiler will figure it out, which is great. That's what we're doing here. We just printed out the scores. Really, really easy. Let me run this using the auto keyword now. You can see the behavior is exactly the same. All right, perfect. Let me comment that out. And let's do another example. In this case, we'll create a vector. So let's create a vector of doubles. And we'll just call it temperatures. And we'll initialize these to, let's say, 87.9, 77.9. Could be really any numbers you like. And 80.0. And how about 72.5? So those are the 4 temperatures that I'm interested in. Maybe they're temperatures per week, per year, per month. It doesn't really matter. It all depends on what you're trying to do. Now, what we want to do is we want to calculate the average or the mean of those temperatures. All right, so we're going to need the average itself. So we'll just call it average temp, and it's a double. We'll initialize that to 0. And we also need a double that's going to be the running total, because we need to sum them all up and then divide them by whatever size that vector is. In this case, it happens to be 4, but it could be any size we want. So there's my double. I'll call it total, and I'll initialize that to 0. All right, so now let's loop through that vector. So we'll say for auto, let's create the variable temp. That'll be one of those temperatures, one at each iteration. And the name of the collection is temperatures. All right, what do? We say total plus equals temp. And I'll scroll up just a little bit, give myself a little bit of room. That's it. Now we divide by the size of that temperatures vector. But before we do that, always make sure that that size is not equal to 0, because we don't want to divide by 0 error. So we'll just say something like if temperatures dot size, that's the method for the vector, if that's equal to 0, then we don't want to do the division, right? So what do we want to do? We want to make sure it's not equal to 0. If it's not equal to 0, it's safe to divide. And what I'll say is as simple as average temp is equal to the total divided by the temperatures dot size again. Number of elements in that vector. That's it. Notice we don't have to do any casting here, because total, this is an unsigned integer right here. It's going to return the size, which is an unsigned integer, but total we defined as a double. So it's going to do double division. All right, so that's it. We'll output now. We'll say something like average temperature is average temp. We'll put an end line at the end, and let's run this. There's the average temperature, 79.575. Now let me show you one of the I/O manipulators that you can use. And as I said, I'll cover these later on in the course. There's a whole bunch of them. They're not all that important, but they're important to help us format our output. What we can do is we can say, first thing we need to do is we need to go up top here and include I/O manip. That's the I/O manipulation operators. And what we'll do here is right before we output, we can say cout fixed, and then set precision to, let's say 1. That's one number after the decimal point, and it will round. So in this case, let's run that, and now you'll see this formatted as 79.6. I think before it was 79.575 or something like that. I don't recall. But it's going to round it up to 79.6. It's always going to have one digit to the right of the decimal point. If this is what you need, this is an easy way to do it. Otherwise, 79.575 works for me. All right, so that'll take care of this example. Let me show you a couple more examples, and again, I'll comment these out so they don't keep executing. Let's put in an initializer list right into the loop. This is not something you see very often, but I wanted to show you in case you do see it, you know what's going on. In this case, we'll say for, again, auto, and the value, it will be val. And right in here, we can put the initializer list. So we can say 1, 2, 3, 4, 5. Sometimes you see this when you know that these numbers are ahead of time. And in this case, we could just say cout val, and we can do end line here. So what's going to happen is it's going to iterate through that collection. Remember, this is a collection, and it's going to display 1, 2, 3, 4, and 5. And let's run that real quick. And there you can see the 1, 2, 3, 4, and 5. Now, the last example I want to show you is with a string. Now, there's two kinds of strings in C++. There is a C-style string, and there's a C++ style string. I'm going to cover these in the next section. What we're going to use here is just a C-style string. That's what we've been using all along. That's a bunch of characters inside double quotes. So what I want to do is I'm just going to say for, again, auto. In this case, it's going to be a character type. I'll call it C. And my collection is basically a bunch of characters, right? A sequence of characters. So this is a test. That's it. What can I do in here? Well, I can output the character. And I'm not going to put a new line because I don't want a new line at the end of every character. That'll print them up and down. In this case, it should just print that string right back out at me. And there you see right up here, this is a test. So it's printing it out directly out at me. Suppose I wanted to skip the spaces. How would I do that? Well, I would just filter the spaces out. I would say if the character I'm looking at, C in this case, right, is not equal to a space, then print the character. So what's going to happen here again, at each iteration, I'm looking at that character. If it's not a space, I print it. If it is a space, I'm not doing anything. So I'm basically just getting rid of all the spaces inside that string. So when I display that, you should see, you see that right there. This is the test all bunched up together. Okay. Now suppose I wanted to replace the, and again, we're not changing the string here. We're just printing out the string, one character at a time. Suppose what I wanted to do was every time there's a space, I want to replace it with a tab character. I want to display the tab. So I'm going to spread these characters out a little bit. Well, we can change the logic here a little bit. And again, let me comment this out so it's available for you to play with. And I'll do something like that just so I can just modify a little bit of code and get this to run right. Okay, so we're here in the same position. I'm going to comment this out. And so I'm reading the string again. I've got each character in C. And I'm going to say if C is the space, then I don't want to print out the space. What I want to do is I want to print out a tab. And if you remember, the tab is a /t. Otherwise, I'll just want to print out the character, right? Anything except the space. Something like that. So let's try that out. And there you go. It says this, then you see a tab is, then a tab A, and a tab and test, and so forth. We could play all kinds of games. You can replace one character with another. You can create your own little cipher if you want that you can send across to a friend and they can decipher it on the other side. Anyway, that's pretty much the range-based for loop. There's a couple of examples I've shown you here that hopefully make it really, really easy. I mean, this is so much simpler. Notice again, there's no int I, there's no ++ I, we're not counting. We're simply looping through a collection, and we don't even have to worry about the type with the auto. So it makes it really easy to think at a very high level to solve your problems without getting bogged down with all the little details. Okay, so that's the end of this video. In this video, we'll learn about the C++ while loop. The while loop is an example of a pre-test loop because the test is done at the beginning of the loop. So it's possible that if the test fails immediately, then the loop body will never execute. The syntax for the while loop is the keyword while followed by an expression in parentheses. This expression has to evaluate to a Boolean value. This is followed by the statement or statement block to execute if the expression evaluates to true. In this slide, we can see a simple while loop that's simply counting. We have a looping variable named I, and we initialize it to 1. The loop condition is I less than or equal to 5. So as long as I is less than or equal to 5, we continue executing the loop's body. In the body of the loop, we display the variable I and then increment it by 1. Eventually, I becomes 6, and the loop condition fails and the loop terminates. It's important that we increment I in the body of the loop. If we don't, then the loop will never terminate, since I will always be 1, which is less than or equal to 5. This is called an infinite loop, and it's not usually what we want. I'll talk about infinite loops in a later video in this section because sometimes they can be useful. Let's see another example. Let's write a while loop that displays the even numbers between 1 and 10, just as we did with the for loop. In this case, we declare I and initialize it to 1, since this is where we want to start looping. Then in the loop condition, we'll check to see if I is less than or equal to 10. So in other words, we will loop while I is less than or equal to 10. And then at each iteration, we execute the body of the loop. In this case, we have an if statement that uses the modulo operator to see if it's an even number. If it is, then we display it. Then we increment it. Note that we increment I regardless of whether it's even or not. Eventually, I becomes 11 and the loop terminates. Let's see another example of using a while loop with an array. In this example, we're using a while loop to iterate over an array. The array is named scores, and it's an array of 3 integers. We set the integer I to 0 since array indexes begin at 0. And we loop while I is less than 3 as we've done in other array code. In the loop body, we display scores sub I, then increment I. When I becomes 3, the condition fails and the loop terminates. Loops are commonly used in programming to provide input validation. In this example, we want the user to enter an integer less than 100. If they don't, we want to ask them again and again and again until they enter a valid integer. So we declare a variable named number and initialize it to 0. Notice now how we prompt the user for the integer and read it from the console before the loop begins. Now we have the value they entered in number. The loop condition is now evaluated, and if the user's number is not greater than or equal to 100, then we have a valid number and we never go into the loop. We simply print the thanks message at the end. However, if the user enters an integer that is greater than or equal to 100, we go into the loop and ask for another integer, read it in, and then we test again. This will continue until the user enters a number less than 100. Notice that we have some duplicated code here. We have the same output and input statements outside the loop and inside the loop. This is usually a clue that the code could be better. We'll make this code better in the next video when we discuss the do while loop. But this kind of code is commonly seen. Let's see another example. In this example, we ask the user to enter a number between 1 and 5. Notice the code is very similar to our previous example, with the exception of the condition in the loop. In this case, we're testing both ends. So if the number is less than or equal to 1, it's not valid. We also test number greater than or equal to 5, which is also invalid. If either of these conditions is true, then the number is invalid. So that's why we use the logical OR here. In this example, we'll use a Boolean flag to control our while loop. First, we declare a Boolean variable named done and we set it initially to false. The idea is that when this variable becomes true, then the user entered a valid number. So the loop test, while not done will be true since we set it to false, so we enter the loop. In the body of the loop, we prompt the user for a number and read it. If the number is not valid, we display an error message and loop again since done is still false. If the number is valid, we display thanks and set the done flag to true. Now the loop condition will fail and we exit the loop. There are many ways to write logic and to achieve the same outcome. Always remind yourself of the KISS principle. Keep it simple, stupid, or keep it short and simple, or keep it simple and straightforward, however you want to think of it. Basically, don't be too clever. Keep your code as simple as possible. Let's head over to the IDE and see some other examples of the while loop. I'm in the Section 9 workspace in the while loop project. What I want to do is write a couple of while loops, some that count down, one that counts up, and a couple of more complicated ones. In this case, I've already written one that counts down. So the idea is we ask the user to enter a positive integer to start the countdown, and then we start the countdown and we blast off when we get to 1. So if they type in 5, we'll say 5, 4, 3, 2, 1, blast off. Okay, so let's walk through this code so you can understand it. First thing we're doing is we're defining that num right up here. That's where the user is going to enter the number into, and let's say they entered a 3. So they're going to enter the 3 and we're going to store it in num. So I've got num over here and its value is 3 right now. Now we check this condition. Is 3 greater than 0? Well, that's true. So we execute the output statement, which says just display num, and I'll do that over here. So I'm going to display a 3, and then I decrement num. Remember, when it's all alone on a line like this, the pre-decrement and a post-decrement means exactly the same thing. So I just change num from a 3 to a 2. I go back up and test the condition again. Is 2 greater than 0? It is. I output the num, which is 2, and then I decrement it to 1. I'll check the condition again. Is 1 greater than 0? It is. So I'll display the 1. Then I decrement this to a 0, and I check the condition one final time. In this case, 0 greater than 0 is not true. So I stop, and I end up executing that line right after the loop blast off. So what we end up with is 3, 2, 1, blast off. Okay, so that's a good way to walk through it. And what we'll do is we'll run this And let's do it with a 10. And there you can see the code going 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Okay, so now let's write a while loop that counts up. So I'll comment this code out right here, and I'll paste some code that I've already written to save a little time, and let's walk through this code. In this case, notice that I'm defining, again, declaring and defining this same variable num to be an integer. I ask the user to enter a positive integer to count up to. So in this case, I want to count from 1 to whatever they typed in. Okay? And I'm reading it in. So again, suppose they typed in a 3. So now I've got num, and its value here is 3. I can't do what I did up here with just a single variable because I don't want to change num. Num is my target as to where I'm going to stop. So I need another counting variable or a looping variable. In this case, I want to use I. So I've got I over here, and I'm initializing I to 1 because that's where I want to start counting at. So I becomes 1. All right. Now we do the loop. We test the condition. Is num greater than or equal to I? So is 3 greater than or equal to 1 in this case? This is true. So what we do is we display I, and I'll do the display over here. We'll display I, which is 1. And then we increment I. So now I is 2. We do the loop condition again. Is num, which is 3, greater than or equal to 2? It is. We execute the body of the loop. So we print out I, which is now 2. Okay, hope you guys are with me. I increment I now becomes 3. Then I go back up and I test the loop again. Is num, which is always going to be 3, is num greater than or equal to 3? It is, right? 3 is equal to 3. I want to output I again. I is 3. And then I increment I. Now I becomes 4. We'll test one more time. Is 4 greater than is 3 greater than or equal to 4? It is not, so it fails at this point. Now we come down here, and whatever statement would be here, we would execute. Okay, so you can see that walking through these examples is pretty easy to do. It's kind of time consuming, but once you get used to the logic, you can pretty much do a lot of it in your head. Okay, so let's do another one now. And I'll clear this up, and I'll comment this all out again. So in this case, what we want to do is we want to do some input validation. And I've written the code again. Let me paste it in, and let me indent all this. I don't know why it puts it all flush left. There we go. Okay, so we've got an integer here called number that we've declared, and we've initialized it to 0. And we're asking the user to enter an integer less than 100. And we're reading that into that variable number. Right? Now we want to loop. Remember, we want an integer less than 100. So we want to loop while that number they entered is not less than 100. So we could say not less than 100 or greater than or equal to 100. Either case will work here. So in other words, if the number they entered is greater than or equal to 100, it's not valid. So in that case, we'll just ask them to enter an integer less than 100 again. We're prompting them to enter it, and we're reading it. And then we're just checking that while statement over and over and over. When this condition fails, that's when we have a valid number. Okay, so let's run this, and we'll print out thanks when we have a valid number at the end. So let's run this, and you see what it looks like. Let's say I want to integer less than 100. Let's do it correctly. We'll type in 50, and we get a thanks. But if we run it and type in a number that's not less than 100, let's say we typed in 120, it prompts me again. I'm in the loop now. So let's say 115, 1,000. It'll just keep going forever until I type in a valid number. And basically, this is the basics of input validation. So 99, that's valid, thanks. Okay? So there you go. You can walk through this the same way that I walked through the other one. Notice that you can write this condition in here a lot of different ways, right? Because greater than or equal to 100 or not less than 100. Okay, so there's different ways that you can write that condition, and you'll see it all kinds of ways out there. All right, so the last example I want to do is one using a flag, a Boolean flag, to do input validation. So let me comment this out, and I'll copy that code in real quick. Okay, so there's the code. Now we're going to walk through this real slow and in detail so you can see what's going on. This is a common use case, and this is the kind of code you see out there a lot. So in this case, we've got a flag called done, and we're initializing it to false. False means that we're not done, right? We still need to get more input from the user for whatever reason. Either we haven't started yet, or they've entered something illegal or out of range. Okay? And I've got this variable right here that I've declared here called number. That's the integer. That's what we're going to read into. Now, it's important that we set that flag to false to begin, because that's how we're getting into this loop the first time. Okay? So don't just leave that to true, or just don't leave it to nothing and take a chance that it is false. Explicitly set it to false, because that's going to get us in that loop the first time. So the first time we're going to say while not done. Well, it isn't done, right? It's false. So we're in here and we ask the user to enter an integer between 1 and 5. And they type the number right there. We're going to store it in the variable number. Now we do a check. If the number is less than or equal to 1, remember, we want numbers. There's the 1, here's the 5. So we want numbers between there, right? So we want 2, 3, or 4. 1 and 5 are not valid in this case. So if the number is less than or equal to 1, in other words, the number is over here somewhere, or the number is greater than or equal to 5, so the number is over here somewhere, then it's out of range. So we simply display out of range, try again. Notice how we didn't change the done flag. The done is still false, right? So at this point, we just executed that statement. We don't do the else part, and we loop right back up to here, right? Done is still false, so we're going to go right back into the loop and output again. Enter an integer between 1 and 5, grab the integer, and so forth. Right? Now, when you do type an integer that's in range, suppose we typed in a 3, then this if statement fails here, and we go to the else. And all we're doing here is saying thanks, and then we set that flag to true. This is like super, super important here. Don't forget to do that. That means we are done. So when we loop back up again here, that condition fails and we're out of the loop. Okay, so hopefully you can walk through this and just take it a step at a time and really understand it. The challenge exercise at the end of this section is a pretty tricky and hard challenge, but it uses this kind of logic to ensure that you've got input validation, and you're going to prompt the user every time that they are not in range. All right, so let me clear this, and let's run this example. So we're going to enter an integer between 1 and 5. Let's say we type 1. 1 is not valid. We want it to be between 1 and 5. Again, 2, 3, or 4. So that's no good. 5 is no good. 70 is no good, right? Negative 12 is no good. So let's give it something good. Let's give it a 3, something that's right in the middle. Thanks. Okay. So you can see that using this kind of logic is better than using this sort of logic where you've got a statement repeated here and then the same statement over here, and you've got duplicated code. We don't have that here. And the reason we don't have that here is because we're using that flag to really decide whether we're in the loop or not. Now, in the next video, we'll talk about a do-while loop where we're doing the condition at the end, and that makes this kind of code even nicer. Okay, so that's the end of this video. Please try these examples yourself, come up with your own versions of them, and walk through them so that you really understand the logic and what's going on. In this video, we'll look at the last looping construct in C++. It's called the do-while loop. The do-while loop begins with the do keyword followed by a block statement, then the while keyword followed by the loop control expression in parentheses. Notice that you need a semicolon at the end of the do-while statement. In a do-while loop, you execute the body of the loop while the conditional expression is true. Pretty straightforward. Note that the condition is checked at the end of each iteration. That makes the do-while loop a post-test loop. It also means that you're guaranteed that the loop body will execute at least once. This comes in very handy in many cases, so we don't have to force our way into the loop like we had to do with the while loop. Let's see an example of using the do while loop for input validation. In this example, we execute the body of the loop, then test the condition. So we ask the user for a number between 1 and 5 and assign it to the variable number. Then we test to see if number is out of range. If it is, then we loop again. If it is in range, then the loop terminates. You can see how much cleaner the logic is in this case. Also, let me talk for a minute about the variable number. Notice how we declared it outside the loop body. Since number is used in the while loop's condition expression at the bottom, it cannot be declared within the body of the loop. If you do so, you'll get a compiler error. In this example, we're declaring selection as a character type. It's outside the loop because we're using it in the loop condition at the bottom. So let's look at the loop. I always start reading loops at their conditional expression. In this case, we know we're looping while the selection is a lowercase or an uppercase y. If the selection is any other character, the loop terminates. Now let's see what's going on in the loop body. We see we have two doubles, width and height, declared and initialized to 0. And we ask the user for these values and read them in from the keyboard. Then we're calculating the product of the width and the height and initializing another double named area with that result. We display the area to the user, and then we ask if they want to calculate another. Note that we have executed that first iteration of the loop unconditionally. That means we always execute this loop at least once. This makes sense in this case since I want to be able to calculate the area. Now we ask the user if they want to calculate another, and we read their response into the selection variable. Then we test this variable in the loop condition. If they entered a lowercase or an uppercase y, we perform another iteration of the loop and calculate another area. If they enter anything else, the loop terminates and we display thanks. The choice between a while loop and a do while loop isn't always crystal clear. However, if you know that you must perform at least one iteration of the loop, then you should consider the do while loop as your first alternative. Let's head over to the IDE and we'll see how we can use a do loop to do a real simple menu system. Okay, so I'm in the IDE and let me show you an example of the application we're going to build. I'll run it now and you can see it's a simple menu driven application. There's the menu, press 1, 2, 3 or Q. If you press 1, you do this. If you press 2, you do that. If you press 3, you do something else. Obviously, these selections could do any kind of behavior depending on your application. So in this case, I enter a selection, I press number 1, and it says you chose 1, doing this. If I press 2, it says you chose 2, doing that. I'll press 3. You chose 3, doing something else. Obviously, if I press a lowercase q or an uppercase q, it'll quit, but anything else should give me an illegal entry. So let's say I pressed 4. It says here unknown option, try again. Let's say I pressed P. Again, unknown option, try again. The only valid choices will be 1, 2, 3, and a lowercase or uppercase q. So now if I type a q, the program terminates and says goodbye. Okay, so that's what we're going to build. And in the section challenge, at the end of this section, you're going to be using this kind of logic to build a more complex application. All right, so let's start. Where do we start? Well, we know we need to display a menu at least one time, right? Because the user has to select Q or X or whatever we choose is the exit criteria. So that's a good choice for a do while loop. So basically, we're doing the do part, which is display the menu while they haven't quit. Make sense? So that's what we're going to build. Now, obviously, we need a character variable, and I'll just call it selection. And whatever the user types in will be stored into that character variable. Now, let's do the do logic here. We've got a do loop, and we want to do the body of the loop while a condition is true. Now, what is that condition? Well, we want to loop as long as they haven't typed a lower or an uppercase q. So we can do something like while selection is not equal to a lowercase q and selection is not equal to an uppercase q. Okay, if you were thinking or here, that would not be right, and you would test your code and you'll see that it doesn't work right. So let's just write a real simple test here before we even bother with anything else. Let's just say cin selection. No menu, no prompting, no nothing. We're just going to grab a bunch of characters here and see what happens. So let's run that. Okay, let's type in an A, we loop, a Q, we stop. Cool, that's what we want. Let's try that again. A 1, we loop, a 2, we loop, a 3, we loop, a 4, we loop again. The only time we should stop is when we get an lowercase or an uppercase Q, we stop. So our logic is correct here, right? Now what we can do is we can actually prompt the user, and with the menu, we could say cout, and let's just put a new line at the beginning, so it gives us a new line every time. We'll do a dash of characters here, and we'll do that. And then we'll give them the menu options. So you can press 1. And if you press 1, we'll do this. Obviously, this would be, add a record or delete a record or do something in a real application. So that would be that. And I'm just going to copy this and paste it to save a little time here. Okay, so number 1. Number 2 would be do that. Number 3, or option 3 would be do something else. And then finally, we can say Q or X or whatever letter you like to quit. Perfect. And we'll give them one more little prompt here that says, and we'll put a new line in front just to separate. We'll say enter your selection. Colon, no end line here, so that it looks nicer for them. And then we input the selection right into selection. All right, so let's run this, and now we should see a menu show up. And there you go. Do this, do that, do something else, or quit. So if we press 1, we stay in the loop, and we display the menu again. Same thing with 2, same thing with 3. 4 gives us the same issue because we haven't checked for anything that's illegal, right? 5, P, whatever. Now, whenever I type Q, I stop. So what I need to do now is decide what the user has typed in and what to do. Okay, how do I do that? Well, it's a lot of choices here. We've got literals here. We got 1, the 2, the 3. These are character literals, so we could certainly use a switch statement really, really easily. What I'm going to do is I'm going to use an if-else-if ladder here. Again, I encourage you to do this with a switch statement with all kinds of logic. That way you can play around with it. So let's do this. Let's say if the selection that the user entered is the character 1. Remember, this is a character, so we need those single quotes. So if the user entered the 1, we simply want to say something like cout. Let's see, you chose 1, which was do this. Or let's just say doing this. Okay, we'll put an end line at the end. Else. And we don't need block statements here. We could certainly use them and it makes it easier to modify our code, but I want to try to keep as much on the screen as I can. So else, if the selection is a 2, then what we want to do here, and again, I'll just copy and paste this to save a little bit of typing time. Then let me spell that correctly. That's better. You chose 2, which was doing that. Else, and remember your indentation. Make sure the indentation is correct because it adds to the readability big time. So if the selection is equal to 3, then in this case, I'll copy that again. You chose 3, which was doing something else. And then, so now what? Where are we at? Well, let's worry about the unknown option as the bottom else of this condition. So if nothing else matches, then we're going to say, oh, sorry, try again. But in this case, if you really think about this, 1, 2, 3, and Q are all valid, right? So let's deal with Q. I'll say else if selection is equal to a Q, right? Or, and notice that here we need an or, whereas in the while we needed an and, or selection is equal to a lowercase q, then in this case, really all we want to say is goodbye, because the loop's going to fail and we're going to be out of here in a minute. Okay, so that takes care of that case. So what's left? This else state here. So what just happened? Well, it's not a 1, it's not a 2, it's not a 3, it's not a Q. It's got to be something that I don't know and I really don't care. It's something that's illegal. So in this case, we'll just say cout. Let's say something like unknown option. You spell that right. And maybe try again. We could do something like that. Let me clear the space up and let's walk through this and make sure we're not missing anything. We've got our selection variable declared. That's important. We're in the do loop. We're going to execute this code immediately, right? This is unconditional. The first time in, we're in. So we're displaying the menu and we're reading the selection from the user. If the user selects 1, we output you chose 1 doing this, and that's it. We're out of this if ladder. We test down here and we loop while the selection is not lowercase or uppercase q. We come back up, we display the menu again. If they typed a 3, we execute this code right here and we keep looping. If they type Q, what do? We simply say goodbye. And then this condition fires at the end. It'll fail and we're out of the loop. If none of these are true, we just say unknown option. I don't know what you've entered. Okay, so let's try this. And again, I'm in the section 9 workspace in the do while project. So let's build and run. And we've got a clean compile and a run. So let's try this. Press 1. Do this. You chose 1 doing this. Exactly what we want. 2. You chose 2 doing that. 3. You chose 3 doing something else. Let's say we pressed 4. Unknown option, try again. But notice how we don't get out of the loop. We don't want to get out of the loop, right? We want to ask them to enter Q if they want to get out. So at this point, we can press an uppercase Q. And there it is, goodbye, and the program's finished. Okay, really, really common use case is this idea of menu-driven programs. You want to display that menu the first time, ask the user for the selection, and basically use an if ladder here, or a switch statement would work here. Try rewriting this program using a switch statement. You'll see it's pretty easy to do as well. Same logic, really. Okay, so that's pretty much it. In the challenge exercise at the end of this section, we're actually going to do stuff when the user presses 1. We're going to use a vector. You're going to be adding things to the vector and displaying the vector elements and so forth, depending on what they choose. Okay, so that's the end of this video. I encourage you, like I said, to walk through this and tweak it and change this to an OR and see why it doesn't work. Understand that. That's really, really important. That's a very common mistake. All right, I'll see you in the next video. In this video, we'll look at the continue and break statements in C++. The continue and break statements can be used within all of C++ loop constructs to provide more explicit control over the looping behavior. Their behavior is really easy to understand. When a continue statement is executed in a loop, no further statements in the body of the loop are executed, and control immediately goes directly to the beginning of the loop for the next iteration. So you can think of this as skip processing in the rest of this iteration and go to the beginning of the loop. In the case of the while loop and the for loop, the condition will immediately be tested again. When the break statement is executed in the loop, no further statements in the body are executed and the loop is terminated. So control is transferred to the statement immediately following the loop. Let's see an example that uses both the continue and break statements. In this example, we have a vector of integers. Let's assume that this data comes from some sort of device, and occasionally we get noise in the data. The noise is represented by the -1. We really don't want to process the noise. We want to ignore it. We also need to stop processing when we get the stop signal, which is represented by -99. In this case, we can use the range-based for loop to iterate over all the vector elements. At each iteration, we can check if the value is -99, in which case we're done. We could set a flag to done and handle the done boolean in the loop condition as we've done before, or we can simply break out of the loop. In this case, we're using the break statement to break out of the loop completely. In the else if statement, we know we haven't seen a negative 99, so we can check for -1. That represents noise. If we see it, we can continue. This stops the iteration and control goes back to the beginning of the loop and a new iteration begins. Finally, if we hit the else statement, we know we don't have a -99 and we know we don't have a -1, so we process that data. In this case, we just display it. In this example, we display 1, 2, 3. Continue and break statements are very, very easy to use. However, don't overuse them. I'm obviously exaggerating here, but if you have a loop that has 10 breaks and 12 continues in its body, that's a very complex piece of code to try to understand. The less ways that you can come into a loop and out of a loop, the better we can understand and debug it. We'll see the break statement again when we talk about infinite loops in the next video. In this video, we'll learn about infinite loops. An infinite loop is often called an endless loop. An infinite loop is a loop whose control expression always evaluates to true, so it iterates over and over. Usually, infinite loops are mistakes by the programmer. If you have an infinite loop, it's pretty easy to know since the program does something or does nothing over and over again, so we find and fix the problem. However, sometimes infinite loops are written as infinite loops on purpose, and programmers use break statements as strategic places to eventually break out of the loop. There are cases where this makes sense and could be justified. However, writing an infinite loop and using break statements to terminate the loop is usually bad practice and should be rewritten so the loop condition expression is descriptive of what the loop is doing. Here are a couple of examples of infinite loops that are appropriate and in fact necessary. Infinite event loops are commonly used in event-driven programs such as those you find on mobile devices and embedded systems. In these programs, the program loops forever, listening for mouse clicks, mouse movements, touches, and so forth, and reacting to them. This continues as long as the program is running. Another example of an endless loop is an operating system. An operating system is constantly looping, handling input, output, handling resources, and so forth. It only shuts down when you shut down your computer. Let's see a few examples of infinite loops in C++. First, let's look at an infinite for loop. Remember that all three expressions in the for loop are optional, so if you omit all three, you get just 2 semicolons. By definition in C++, that's an infinite loop. The output statement will be displayed as long as the program is running. Let's look at a while loop. Here's an example of an infinite while loop. It's probably exactly what you were thinking of. While true will always be true, and the output statement will execute over and over again. Of course, we don't have to use the true keyword. We can use an expression that's always true. So if we say while 10 is less than 12, since 10 is always less than 12, it'll loop forever. You get the idea. Finally, let's look at an infinite do-while loop. Again, the loop condition will always be true, so the output statement repeats forever. Okay, so what? Why would I ever do this? Well, you might write an event loop like this, but more often you see code that looks more like the following. Note that in this example, we have an infinite loop since while true will always be true. However, we have a strategically placed break statement that terminates the loop. Let's walk through the example. Inside the loop, we declare a character variable named again. We ask the user if they want to loop again, and read the response as a character into the variable again. If again is uppercase N or lowercase n, then we break and terminate the loop. If they enter anything else, we loop again. This is an example of an endless loop that might be okay. However, best practice suggests that the loop condition be more informative of when the loop iterates. If I was doing a code review of this code, I would refactor it to do just that. However, you do see code like this out there, and now you know how it works. That completes this video. In the next video, we'll see how we can nest loops one within the other. In this video, we'll go over using nested loops. Just like we nested if statements, one inside the other, the same technique can be used to nest loops. We can nest loops as many levels deep as we need. I'll be using just 2 levels in the examples I'll show you. That is, one loop inside another. Nested loops have many uses, but they're especially useful for multidimensional structures like 2D, 3D arrays, and 2D and 3D vectors. When we talk about nested loops, it's common to refer to the loops as the outer loop and the inner loop. Let's see some examples. Here's a pretty generic example of a nested loop. In this case, we have a for loop with another for loop within it. The outer loop is incrementing outer val from 1 to 2 by 1. The inner loop is incrementing inner val from 1 to 3 by 1. Notice the output. The integer to the left of the comma is the outer val, and the integer to the right of the comma is the inner val. Notice how inner val increments from 1 to 3, while outer val remains at 1. Then outer val increments to 2, and we do it all over again. You can think of this as the outer loop iterating 2 times, and each time the inner loop iterates 3 times. That's why we say that the inner loop loops faster than the outer loop. Let's see another example. In this example, we can take advantage of a nested loop to display the multiplication table from 1 to 10. A nested loop is perfect since we want 1 times 1, 1 times 2, 1 times 3, all the way to 1 times 10. Then we want to do 2 times 1, 2 times 2, and so forth. So we want an outer loop iterating from 1 to 10, and an inner loop also iterating from 1 to 10. And the body of the inner loop simply multiplies the outer loop's variables times the inner loop's variable. Notice the output statement after the inner loop that displays a line of dashes. This executes each time the inner loop completes. We'll execute this loop in the IDE in a minute so you can see it work. Let's see an example of a nested loop using a 2D array. In this example, we have a 2-dimensional array of integers named grid. Grid has 5 rows and 3 columns. Suppose we want to assign 1,000 to each element in the grid. We can do this easily with nested for loops. The outer loop iterates for rows 0 to 4 inclusive, and the inner loop iterates the columns for each from 1 to 2 inclusive. Then in the body of the loop, we simply assign 1,000 to grid sub-row sub-column. Notice I'm using block statements for the body of these loops. I didn't have to here, but it's good practice to do so since it makes adding code later much easier. Now that we've initialized the grid values to 1,000, we can use a similar nested loop to display the values. In this example, we're assuming the grid has been initialized as in the previous slide. At each iteration of the inner loop, we display the element at grid sub-row sub-column, followed by a space. So we're displaying these elements across the screen. When we complete the inner loop, we print a new line, and then execute the outer loop again. You can see the pattern is the same as with initialization. This is a very common pattern for working with multidimensional structures. Let's see how we can use nested loops with vectors. In this final example, we declare a vector of integer. So we have a vector whose elements are vectors of integers, very similar to a 2D array of integers with the advantage of vectors. With a vector of vectors, we can allow each vector within the vector 2D to be of different size. In this case, we have 3 vectors of vectors, and each of those vectors is a vector of integers. I know it sounds complicated, but if you look at the example, it should be pretty clear. The first vector has 3 integers, 1, 2, 3. The second vector has 4 integers, 10, 20, 30, 40. The third vector has 5 integers, 100, 200, 300, 400, and 500. If we wanted to display the contents of vector 2D, we could do it easily with nested range-based for loops. And if we use the auto keyword to allow the compiler to deduce the type of each loop element, it makes it dead simple. Notice the outer loop in this case. The compiler deduces vec to be a vector of integers. And in the inner loop, it deduces val to be an integer. In the body of the inner loop, we simply display the value followed by a space. As we did in the previous example, we display a new line after we're done displaying the inner vector values. You can see how little code and how simple the code is. You can see the output from this loop at the right on the screen. In these examples, I've used for loops within for loops, but you can use any combination of loops within any other loop to achieve your desired behavior. Let's head over to CodeLite and see some of these examples live. Okay, so I'm in the CodeLite IDE. I'm still in the Section 9 workspace, and I'm in the multiplication table project. This is the piece of code that executes and displays a multiplication table for up to 10 by 10. So let's go over this really carefully because this is a classic example of a nested loop. Notice we've got the 2 for loops, one within the other, and the outer loop is looping on the num1 variable. The inner loop is looping on the num2 variable. So we're going to start the outer loop, and we're going to assign, right here, we're going to initialize num1 to 1. And now we check, is num1 less than or equal to 10? It is. So we go into the body of the loop. Well, the body of this loop is another loop. And in this case, we're initializing num2 to 1 right here. And we check, is num2 less than or equal to 10? It is. So we execute the body of the inner loop, which is this output statement right here. So what we do here is we display num1, which is 1. We display the asterisk string right there. We display num2, which is 1. We display that equal sign right here. And then we multiply num1, num2. That gives us 1, and we display that value. That's it. We display a new line, and now we loop again. So we come back up to the loop. We do the increment. So now num2 is 2. We check, is num2 less than or equal to 10? It is. Execute the body of the loop again. This time through, we've got num1 is still 1 right here. Num2 is now 2. And we display the output and so forth. So we're going to do this until we get to 1 times 10 equals 10. And num1 will still be 1. At this point, num2 is 10. Now we're going to increment num2 to 11. We come over here and we check, is num2 less than or equal to 10? It's not, so we fail. Now we terminate the inner loop. We execute this statement right here, so it's going to display a bunch of dashed lines here. And then remember, we're still inside the outer loop, so we have to go back out to the outer loop and do the increment. So now num1 becomes 2. Is 2 less than or equal to 10? Yes. We go back into the inner loop again. So think of this as, here's your outer loop, and it's looping. And each time it loops, you're going to do the inner loop 10 times. Then you're going to go back out, outer loop, and you're going to do the inner loop again 10 times. Okay? My art is not pretty, but hopefully you'll understand what I'm talking about. All right, so that's what's really going on here. Let me clear this and run it so you can see this in action. So there's the output. Let me scroll up. So you could see here 1 times 1 is 1, 1 times 2 is 2, and so forth. Notice in this case, let me move this just over here so you can see the variables. Over here, this left 1 is num1. And then you can see that num2 is looping faster. That's why we say the inner loop loops faster than the outer loop. We go through all 10 of them, then we display the dashed line, then we go back out to the outer loop. Now num1 is 2. And then 3, and then all the way to the bottom where we end up with the 10s. And we end up with 10 times 10. At this point, the outer loop fails, and we're done. Okay, so hopefully that makes sense. And what we'll do next is we'll do an example that's a little bit more complicated. We'll actually grab some user input, we'll grab some numbers, put them in a vector, and display a histogram based on those numbers. Okay, so I'll close this. And I will open up the histogram project. I'll double click on that to make it the active project. Right now, there's not much in here. It's just a really, really simple basic main that does nothing, just prints a new line. So what do we want to do here? We want to ask the user how many data items they have. Let's say they type 6. Then we ask them for each one of those data items, which is just an integer. And then when we're finished with that, we'll output all that information using a histogram. So that's pretty straightforward. We need to ask the user how many items they've got. So let's create an integer variable there called numItems. And we'll just initialize that to 0. And then we'll ask them, how many items do you have? Let's say data items. Okay, and we'll read that integer into numItems. So now we know how many data items they have. What we want to do next is loop that many times. So if I've got 5 data items, well, I want you to ask me 5 times to enter that data. So it really makes sense to use a for loop here because we know exactly how many times we want to iterate. We also need to store this information somewhere, right? So all that information they type in, we'd like to store it somewhere. Since we really don't know what number they're going to type in, an array would not be a good idea here, because you don't know how big to make it. You'd have to make it really big just to be sure that everything will fit. So we'll use a vector. First thing we'll do is we'll include vector here. So we're good to go there. And let's declare the vector right now. We'll call it vector of integers in this case. And let's just call it data because that's what it is. And we'll initialize the vector. It's empty. All right. Remember, a vector is a dynamic data structure, so we'll be able to read data from the user and put it into that vector using its pushback method. So let's loop. How many times are we going to loop? We're going to loop from 1 to that number they entered, right? So if they enter 10, we're going to go from 1 to 10, and we're going to grab 10 data items. So let's do that right now. For int I, we'll use I, and we'll initialize I to 1 because we want to start here at 1. And I want to loop while I is less than or equal to the number of items that they want to enter into the vector. And I will increment I by 1 each time. Now I'm going to use a block statement here. Now, what do you think is going on in here? Well, I need to ask them for the data, right? I'm going to loop, let's say I typed in 10 items. This is going to loop 10 times. So we need somewhere to read the data into. That sounds like an integer to me. So we'll say data item. We'll initialize that to 0. And then we'll just say cout, enter data item. And we may as well tell them which one it is because we know it, right? It's I. We'll do something like that. We'll put a colon so it looks nice for them. So this will say enter data item 1, enter data item 2, all the way up to whatever they decided they wanted. What we'll do now is we'll read that integer that they type in into that data item variable we just created. So we've got the data. What do we do? We need to put it into that vector now. Remember how to do that. The vector's name is data. So we say data.pushback, and we push that data item in there. So it's going to put the data item in the back of the vector. That's it. That's pretty straightforward. So at this point now, what we've got is a vector that contains whatever data they typed in. So if they typed in 5 integers, that vector has 5 integers in there. So what do we want to do now? Well, we want to display the histogram. But before we do that, let's just display the data and make sure we have it, right? It's always good to test as you go. So let's do that. We'll say for. We'll use a range-based for loop here. Auto val, that's the value, and the collection is data. Okay, so for each element in that data collection, let's just output it now, just to test. Okay, that's it. Let's run this. How many data items do you have? Well, I have 5 data items. Enter data item 1, 10, to 20. Let's just put them in tens. That way we know what we're getting. 30, 40. It should ask me one more time. 50. Now it should be done. And I'm displaying the data items. So everything's looking good. Let's run it again with 3 data items. Let's put 1,000 in here. Let's put a 10 in there. Let's put a 1,200 in here. 1,000, 10, 1,200. Perfect. So that's exactly what's going on right now. Is right where we want to be. How many items do you have? And enter data for each one of those values. Good. So it's always a good idea to test as you go because it just makes life much, much easier to test as you go rather than try to test this big monolithic thing at the end. All right, so let me just do a quick statement here and I'll put a new line in the end just to give a little space. I'm just going to say displaying histogram. Now, what we need to do is pretty much what we did here, right? Except we don't want to display the value. We want to display a dash for each one of those values. So for example, if the value is 10, we want to display 10 dashes. If the value is 100, we'll display 100 dashes. That's what a histogram looks like. So how do I do that? Well, I need to have another loop in here, and I'm just going to get rid of that right now. So we still have this loop right here. It's looping through the collection. So what do I do here? Well, I know how many times I need to loop, right? I need to loop val times. So a for loop is good. We can use any loop we want really, but let's use a for loop because it's really simple. So we're going to say for int, and let's use I again. And we're going to start at 1, and we're going to loop while I is less than or equal to val. That's the number we just read. Okay. Now what? Well, the increment is by 1. We need to increment by 1. So that's my inner loop. What do I want to do in here? All I want to do is just type a dash. And we'll use dashes for a reason. You could use an asterisk, but I'm going to use an asterisk in a second. That's it. So let me fix that typo. If the user typed in 5 integers and the first one is 6, then val is going to be 6, and we're going to loop 6 times, displaying 6 dashes. If the next one is 12, we're going to display 12 dashes. After we're done displaying those dashes, we need to display a new line. Otherwise, everything's just going to go right across the screen. So I'm just going to say end line right here. And we need to close off this. Let's do that for loop right here on a block as well, since we're probably going to add a little bit more code. Okay, so that's where we're at now. You can see pretty straightforward. Let's run this. And I forgot a semicolon right there, so I put that in there. Okay, how many items do you have? Let's just start simple, 3 items. What's the first data item? 5, 10, 15. What I expect now is 3 rows, one with 5 dashes, one with 10 dashes, and one with 15 dashes. Awesome, that's what we've got. Displaying histogram, 1, 2, 3, 4, 5 dashes, 10 dashes, 15 dashes. You see that? That was pretty simple. And it's pretty powerful too, because we've got dynamic data structure that's growing as we need it. Let's run this one more time with a little bit more data. Let's say I have 10 data items, and I've got a 10, 34, and I'm just going to put some, really any numbers in here. 7, I don't want to do a 90. Let's do a 30. Let's do a 50, and let's do a 1 and a 2 down at the bottom. Okay. So there we go. There's my histogram. You can see the last 2 should be 1 and 2, and they are right here, 1 and 2. And you could count them if you like, but I think they're correct. Obviously, you would want to count them if you were going to test them to be sure that everything is correct. So there's my histogram. Pretty straightforward. This is kind of hard to see, though. I mean, how many dashes are here? I can't really tell. So why don't we say that every 5th dash, let's display an asterisk instead. That'll make it easier to see. Okay, so how do we do that? We're right in here. So what we could do is we could modify this code slightly. We could say if that specific I, my counting variable, right, mod 5, is equal to 0. So if that means I'm on a 5th number, right? In this case, I want to display an asterisk. Otherwise, so I need an else here. I just want to display the dash. And let me indent this correctly. There we go. So notice the indentation here. It's really important. If you look at that piece of code right there, you can see that I have a for loop, and I've got another for loop nested within it. And that for loop has an if-else statement. So every time that loop executes, I'm executing that if-else statement. Okay? So you can see the structure of the code by just looking at the code. You don't have to try to figure it out. If everything here was indented to the left, flush here, it'd be really hard to see the structure. So let's run this and see. Okay, let's say I've got 10 data items, and I've got 34, 32, 24, 5, 10, and just some other numbers that I can put in. And let's do 2 and 1 again at the end. There we go. So now you can see that every 5th number is being displayed with an asterisk. In this case, it's really easy. I can tell that's 10. I can tell that's 19. I can tell that's 5, 10, 15, 20, 25, 34, and so forth. So it makes it much easier to interpret the data. Here's a really easy, simple example of using a nested loop. In this case, the for makes sense because we know how far we're going, but we could easily rewrite this with whiles or do whiles or anything we like. Remember, at the end of the day, a loop is a loop is a loop, right? So they all do the same thing. They all iterate. It's just a matter of trying to choose the right one for the application. So hope that helps. These kinds of examples are going to be real useful in the challenge exercise, which is next. Okay, so welcome to the Section 9 challenge. This challenge puts together just about everything we've learned to solve a problem. The Section 9 workspace under the challenge project. There's also a challenge solution project, which includes my solution, which I'll cover in the video right after this one. Let's talk about the challenge, and then I'll give you a demo of the running solution. This challenge is about using a collection or a list of integers and allowing the user to select a few options from the menu. So here's the menu. P, A, M, S, L, Q are the selections. If the user presses P, you print the elements of the list. If they press A, you add a number to the list, which you asked them for. If they press M, you display the mean of the numbers in the list. S and L, the smallest number and the largest number. And of course, if they press Q, you quit. Now, anything else, you should tell them invalid choice and so forth, okay? Just like we've been doing. So let's go over a little bit more of the detail here. We're only accepting valid choices from the user. Both uppercase and lowercase selections should be allowed. And if they enter an illegal choice, you should say unknown selection, please try again, and then redisplay that menu. Okay, if the user enters a upper or lowercase p, we display all the elements of the list. Remember, this is a list of integers. If the list is empty, you should just display 2 square brackets and then say the list is empty. If the list is not empty, then all the list elements, all the integers in that list should be displayed inside square brackets separated by spaces. So in this case, the list has the integers 1, 2, 3, 4, and 5, and this is how we'll display them. If the user enters an uppercase or lowercase a, then you'll prompt them for a number to add to the list, in which case you add it, and then you display whatever number they entered added. Okay, it's okay to have duplicate entries in the list, and the last couple are pretty straightforward. If they press M, upper or lowercase, you basically iterate through that list and calculate the average of the list or the mean of the list and display that. If the list is empty, obviously you can't calculate the mean. You simply display unable to calculate the mean, no data. For S, again, upper or lowercase, you basically iterate through the list and find the smallest integer in that list. And that's what you display back to the user. So in this case, if the list contains 2, 4, 5, 1, you'll display the smallest number is 1. If the list is empty, you should display unable to determine the smallest number because obviously the list is empty. L works the same way, except you're looking for the largest element in the list. When they press Q, you say goodbye and the program terminates. Okay, so that's the challenge. Before you begin, write out the steps you need to take and decide, what order you should do them in. Think about the loops. You need loops. You need if statements or switch statements. Think about what the best way to do this is. Start small, build little pieces, test those little pieces, and then add as you go and test as you go. One big hint, use a vector. Don't use an array here. Use a vector. That should be pretty obvious because we want this to grow dynamically. A couple of more things. You could add functionality once you finish this basic challenge to search for a number in the list, and if it's found, how many times did it occur? Maybe it's not in the list. The vector class has a .clear method that you can call to clear out the list. So maybe you want to have an option for the user to delete everything in the list. Maybe you want to not allow duplicate entries. So if I press to enter the number 5, you'll let me enter it. If I want to enter it again, you'll say, sorry, it's already in the list. So come up with your own ideas. It's really all about learning and practice. Okay, so let me give you a sample run of this. So here's the menu. As you can see, P is print, A is add, M is mean, S is smallest, L is largest, and Q is quit. Let's do the obvious one first. Let's press Q. We're out. It says goodbye. Our program is over. Okay, so let me run it again. And let's print the numbers in the list. Right now the list is empty. So if I press P, and again, it could be uppercase or lowercase, you get the 2 square brackets and the list is empty. Now I want to add a number. I'll press A. Let's say I want to add the number 10 to the list. 10 is added. And let's say I want to add another number. So I'll press A again, and I want to add -10 this time. So we've added -10. If I want to print the numbers again, I'll press P, and there's my list, 10 and -10. I'll add a couple of more. So let's add 100, and let's add 500. And we'll display the list again with a P. And now we've got 10, -10, 100, and 500. Just like what we thought. Display the mean of the numbers. We'll press M. In this case, the mean is 150. Let's add another number. Let's add 3. And do the mean again. Notice it's 120.6, so the mean should be a double, not an integer. Finally, let me print the list again. We've got 10, -10, 100, 500, and 3. The smallest should be -10, and the largest should be 500. So let's test that out. I'll press S for the smallest. The smallest number is -10. And I'll press L for the largest. The largest number is 500, exactly what we expect. And of course, if the user types in 1, unknown selection, please try again. Or if they press O, if they press anything that's not one of these letters, we tell them unknown selection, redisplay the menu, and grab the input from them again. Press Q to quit. That's it. That's the challenge. As I said, this can be a tricky little challenge to do because you've got a lot of things going on. You've got loops and loops within loops and if statements and maybe switch statements and maybe do loops, maybe while loops. It's really up to you to decide how to solve it. Give it a shot. Don't be discouraged if it takes you more than a few attempts to get it. That's pretty normal. I'll see you in the next video. We'll go over my solution to it, or at least one solution to it. All right, good luck. Hello, welcome back. I hope you enjoyed the challenge and I hope it was successful. In this video, I'd like to go over that challenge and give you one solution to it. So I'm in the Section 9 workspace in the challenge solution project. In your case, you're going to have this solution already, but we'll work through it together here. So let's say, where are we? Well, we need some sort of data structure. We need a list. We need a collection that the user can type integers and we can store it into, right? So in this case, we're going to use a vector. It's the only one we know right now, and it's a really easy and logical one to use. So in order to use a vector, we need to include vector. So I'll do that right now. And obviously, we need to declare a vector that's going to hold the numbers. And we also need to declare a character that's where we're going to store whatever they typed on the keyboard. So let's declare those two variables right now. We could call this vector whatever we like. I'll just call it vector. Remember, it's a vector of integers, and I'll call it numbers. You could call it data. You could call it whatever you like, and I'm initializing it to empty. And then I've got a character, which I'll call selection, and I'll also initialize that to empty. What we're going to do is we're going to read the user's choice into that variable. Okay, so where are we now? Remember, what we're going to do is we're going to display the menu to the user. We're going to ask them for a choice. Depending on what they choose, we'll do something or other. And then at the end of this do loop, we want to keep looping while they haven't pressed Q, right? Either uppercase or lowercase. So let's write that logic first. Let's start with baby steps. Here's the do loop. And then we want to do while the selection is not equal to. Remember, in this case, they can type in an uppercase or a lowercase q, right? So while it's not equal to a lowercase q, and again, those are characters, so make sure they're single quotes, not double quotes, and the selection is not equal to an uppercase q. There's a semicolon here at the end of this while loop right there, this do while loop. That should take care of our logic. Now, what we want to do in here is we want to display that menu, right? Right away. That's the first thing we want to do unconditionally. So what I'm going to do is I'm going to copy and paste my menu code right here, which is just a bunch of output statements. And we're reading the selection. So we can test this right now. We're going to display print a number, add a number, all the menu choices that you saw in the demo. And then we're going to ask them to enter a choice, and we're going to read that choice into selection, which is that character variable right here. So what do I expect here? Well, I expect that if the user types lower or uppercase Q, the program will end. If they type anything else, we should display the menu again and again and again, asking for enter another choice. All right, so let's try that. We'll build and run. And there's the menu, print numbers, add a number, display a number, and so forth. So let's say we enter P, we get the menu again. Uppercase P, same thing. A 1, a 3, a 5, it doesn't matter, anything. Now, what we're really interested in is we want the program to quit when I press both Qs, upper and lower. So I'm going to press lowercase q, program stops, perfect. I'm going to test this again with an uppercase q, program stops again, perfect. Make sure you test both of them because a lot of times I've seen typos like this, and you'll test with the lowercase q and it quits correctly, but then the uppercase q doesn't work. So make sure that you test everything really well. Now, this is where we're at right here. We know the user has selected something, right? So what do we need here? Well, we need some selection logic. We need to say, well, if you picked P, I want to do some stuff. If you picked A, I want to do something else. We have a choice. We could use a switch statement really easily because these are going to be character literals. This is a character. So I could do a switch off of selection and they say case PP, case AA, case M and M, and by that I mean uppercase, lowercase, and that'll be fine. What I'm going to do is I'm going to use an if-else-if ladder because it's usually what you'll see out there in this kind of example over the case statement. Okay, so let's try that. First thing, let's deal with the print. So we've got the selection here. So here I want to say if the selection is equal to, let's say, an uppercase P, or the selection is equal to a lowercase p. And I'm going to do a block statement here because I'm going to write some extra code here. So that's where we're at. If the user typed a P, whether it's upper or lowercase, we're going to execute this code right here. Well, what does this code say? Print all the numbers in the list. What's my list? Numbers right here. What's the best way to do that? Range-based for loop, no question. Really, really easy. There's one thing we need to take care of though. If that list is empty, we need to tell the user list is empty. We can do that now, or we can do it in an else statement. I'm going to do it right now. So I'm going to say, remember indent right here, I'm going to say if numbers is the vector, dot size is the method that returns the size. If that returns a 0, what's going on? The list is empty, right? So I'm just going to say cout, and again, indent under the if, cout, the 2 square brackets with nothing in it, and then I'll just say the list is empty. That's it, end line, and that's the if part. Now, what about the else part? The else part's going to have a few more statements than this, so I'm just going to say else, and then again a block statement here. I could have said if numbers.size is not equal to 0, and then put this code up here, and then the else would have been the empty part. Both ways are absolutely perfectly logical, and they're both correct. So, but in this case, right now I'm here. So when am I in here? I'm in here when the size is not equal to 0, right? In other words, there is stuff in that vector. So what I want to do now is print it out. I want to print it out in a nice way with those brackets. So I'm just going to say cout, and I'm going to print out that left bracket followed by a space. No end line because I want to print the numbers right next to it. And then I want to close it off with an end bracket. Now, what I want to do here in the middle is print out those numbers, one after the other with a space between them. How do I do that? What's the best way to do that? A range-based for loop. So let's do that. For auto, I'll call the variable num, and the collection is numbers. And what do I do for each one of those? Display it. Cout num, followed by a space. That should do it. Okay. Now right here, I definitely want to do an end line. That will take me to the next line. Now let me clean this up so we can see the structure a little better. And I'll get rid of this space as well. So look what's going on here. We entered a selection. The selection is P, so the user wants to print out all those elements. We know that there is either nothing in the list, in which case we do this. Otherwise, we print out all the numbers in the list. Right now, the list is empty the first time I do this because I haven't been able to add anything, right? So we'll run it. And when I select P, it should say list is empty. There it is. The list is empty. Then I get the menu again. That's important. I'm going to quit. Now let's test this with a list that's not empty. What we'll do is we'll just come right up here and just put some stuff in there. 1, 2, 3, 4. Right? The list is definitely not empty now. So we'll run this. And we expect to get 1, 2, 3, 4 right in the brackets. Perfect. So it looks like our print is done. I'll quit. And we'll move on to the next one. Now we're here. It wasn't P. Let's assume that it wasn't P, right? So what we'll do is we'll create the else if ladder here. So I'll say else if the selection is an A, uppercase, or the selection is a lowercase a, then we want to worry about adding something to the list, right? So I've got my block statement here. So what do I do here? Well, I need to ask the user to enter a number and then add it to my vector. Right, so I need a variable, int, let's call it num to add. That's what we're going to read the number into. We'll initialize it to 0. And we'll say, we'll output to the user, enter an integer to add to the list. Something like that. And what we'll do is we'll read it into num to add. So now we've got the number that we want to add. What do we want to add it to? The vector numbers. How do you do that? Numbers dot push back, right? We're going to push it to the back of the vector, and we're going to push num to add, just like that. And then we're going to tell the user we've added their number. So I'll just say something with cout num to add. Let's say just simple added. And we'll put an end line here. That looks pretty good. We can test that out as well. What I'll do is I'll come up here and I'll initialize that vector again to empty. We'll get rid of that test right there. So there we go. The vector is empty again. We'll run this. And let's add. We'll press A. Enter an integer to add to the list. Perfect. We'll type in an integer 10. We're reading that into num to add now and pushing it to the back of the vector. It says here 10 added. Now, if we print the numbers again with the P option, we should see a list with a 10 in it. Awesome. That's exactly what we have. Let's add a 20. And we'll print it again. Now we've got a 10 and a 20. Exactly like what we expected. Okay, we'll press Q to quit. So we're working our way down these options here. The next one would be M to display the mean. So let's do that. Again, we'll say else. Remember, that's that else if else ladder. Else if the selection is equal to a capital M character, or the selection is equal to the lowercase m character. In this case, I want a block statement, and in here is where we're going to calculate the mean. Okay? Just like we did before in some of the other examples that we've done. How do you calculate a mean? Well, we need a running total, right? We add them all up and we divide by the size of how many elements are there. But we need to be careful of one thing. We have to be sure that the vector is not empty, right? So we'll do this test again. So we'll say if numbers dot size is equal to 0. We'll simply say cout, and we could do this in a block statement, but I'll just use a single statement. We'll say unable to calculate mean, no data, or something like that. And we'll finish it off with an end line. Now we've got our else statement in a block, because we need to do more than one thing here. So now the only time we're ever going to be in here is if there is data, right? There's stuff in the vector, there are integers in there. So what do? We need to calculate, add them all up. So let's create a variable called total, and it's an integer is fine. And now what do? We loop, so we loop through that vector again, and we total up all the numbers. So let's use another range-based for loop. That's perfect for this situation. Let's say num, and the collection again is numbers. And what do at each iteration? We just say total equals total plus that number. Perfect. Now we're out of that loop. Remember, don't indent here. We're going here because we don't have a block statement there. And now we just simply say cout the mean. Let me clean that up. The mean is, and what we can do here is we can actually do the calculation right in line. We could just say total divided by numbers.size, which is the amount of data in that vector, and line. Okay, now that's almost correct, but it's not quite correct. There's a little error here, and if you remember what it is, we've got an integer total being divided by an integer size, so we're going to do integer division here. So this is where a good test case comes in handy. Let's run this, and let's type in, let's add a 1, and we'll add a 2. Let's print our list, 1 and 2. Let's take the mean. We expect 1.5. We get a 1. That's because we're doing integer division instead of double division. So let me quit here. We need to provide a static cast here of one of these two guys. So we'll just do this. So we'll stay static underscore cast to a double and of total. That's it. We'll run this again. Let's add a number 1. Let's add another number 2. Print them out. Make sure we have the 1 and the 2 in there. Yes, we do. Let's take the mean. Now we expect 1.5. Now we've got 1.5. Okay, so the two pieces left are smallest and largest, and this video is getting a little long, so I'm going to stop this here and I'll join you in the next video where we'll do the last few pieces. Welcome back to the continuation of the solution. We stopped at mean right here, and the last two parts that we've got to do are display the smallest number and display the largest number. And then of course we have to handle quit, which is really easy to do. All right, so let me scroll back down here and clean up a little bit of this white space. All right, so this is where we're at right here. So now the user hasn't typed in a P or an A or an M. Maybe they've typed in an S, which is the smallest. So we'll do another else if ladder here. We'll say else if the selection is equal to a capital S or selection is a lowercase s. In this case, we need to calculate the smallest number in the list. There's a lot of ways to do this, but again, let's deal with the case where the list is empty, right? So we'll say if numbers, just like we have before, if numbers.size is 0, then we've got an empty list. We could just say cout, and we could say unable to determine the smallest list is empty, or something like that. Any kind of message that makes sense. And we'll put an end line here. Now we're in the else section. At this point, obviously there is some data in that vector. So what we can do is we can, again, iterate through the entire vector and look for the smallest number. Well, how do we do that? It's pretty simple. Just pick the first number and assume it's the smallest. And then iterate through the vector. And if you see anything smaller, just replace that one with the smallest one. Okay? So it's, again, it's pretty straightforward. So let's do that. Let's say we've got a smallest. We'll call it smallest. And what we'll do is we'll initialize that guy to numbers at 0. All right. So let's think about what's going on here. What we're doing here is we're saying that the smallest integer is the first integer in the vector right now. Reasonable assumption. We know that there's at least one integer in there. So we'll do that. Then what we'll say is we'll do, again, a range-based for loop. We'll say auto. We'll call it num. And the collection is numbers. So we'll loop through there. And what we'll say is if the number we just read is less than the smallest that we've already seen, then what do? Then we make the smallest the number we just read. That's it. Really straightforward. Now we're going to do an output statement, but look where we're going to do it. We're not going to do it here. We're going to do it here because at this point, we're out of that for loop. So we're going to say cout, the smallest number is colon, and its smallest. And we'll provide an end line. That's it. Let's test this out. And we could put data in here up top, right up here, and just put a bunch of data, and then we know what the smallest is. But I really want to test it all as we go. So I'm going to run it now. And let's add 10, and let's add 20. And we'll select S. We expect 10. That's exactly what we got back. Let's add another number. Let's add -20. Let's print the numbers. We've got 10, 20, -20. If we want the smallest at this point, I'll press S again. We should get -20. And there it is, -20. There's a whole bunch of other test cases you could do, but this works just fine. I'll press Q to quit. And next is the largest, right? The logic is exactly the same as this, except it's going the other way. So in this case, let me clean up that white space right here. We're going to say else if the selection is equal to a capital L, or the selection is equal to a lowercase l. Now the user wants to find the largest number in there. I'm going to use another block statement and the same logic. I'm going to say int largest, and I'm going to assume that largest is the number at the 0th location, right? The first number in the vector. Oops, let me back up here. I forgot to check to make sure that there's numbers in there, right? So if numbers.size, I got a little bit ahead of myself there. If numbers.size is equal to 0, then in this case, there is nothing to check, right? So we'll just do the same thing we did out here. We'll say cout unable to determine largest. List is empty. Here's the else part. That's the part where I got ahead of myself. Let's assume that the largest is that first number. I know there is a first number, right? Because the size was not 0. So at this point, we're going to loop through the collection again. So I'm going to say auto num numbers, just like we did before. And we're going to check if the number we just read is greater than the largest number we've seen. Then what we're going to do is we're going to say that the largest number is now num. Simple as that. And our output statement now says the largest number is, and we'll say largest. Okay, so that should take care of the largest case. So let's test this out. So let's add some numbers. We'll add -10. We'll add 1,000. We'll add 200. And we'll add 300. So let's display our list. So you've got -10, 1,000, 200, 300. We expect the largest to be 1,000, so I'll press L. And the largest number is 1,000. Let's check the smallest again, S. The smallest is -10. Cool. So we're almost done, right? All we need to handle is the Q case. I'll quit here. And the Q case is real simple because all we want to do is just say goodbye. So let's do that here. We'll say else if the selection in this case, right, just like before, is an uppercase Q, or if the selection is equal to a lowercase q, in this case, what we want is to simply say cout, and let's do that in a block as well. You really want to do these in blocks because you never know when you're going to come back to add code, and it's already set up to add code this way. So we'll say cout goodbye, end line. Perfect. And while we're here, we may as well handle that other case, right? That's the catch-all else right here. That's going to be the end of the else if else ladder. What happens here? Well, they typed something in that I have no idea what to do with. So at this point, what do we say? Cout unknown selection. Please try again. That's as simple as that. Okay. Seems like a lot of code, and it sort of is. When we talk about functions very soon, we're going to make this so much easier because instead of all of this code in here, we're just going to have one line that calls a function and one line that calls a function here and so forth. So we'll get to there soon, but let's finish this up now. Building and running. Let's press Q. We expect a goodbye message now. There it is, goodbye, and we quit. And let's type in something that we don't know what to do with an O. Unknown selection, please try again. A 1. Unknown selection, please try again. And that's it. That's the solution. Of course, you could have done this with a switch statement here, in which case it might have looked something like switch off of selection. And then here you would have case Q, case, lowercase q, cout goodbye, and then break here. And then you'd have all your other cases, just like you saw in the videos. But in this case, I think the switch statement is okay if we're using functions. We could just call functions here, but otherwise the switch statement tends to get even longer. I mean, I don't know how many lines of code we wrote for this example. Let's see. We started on about line 65 because the rest was just the stuff at the top. So we went from about 65 down to about 140. So I don't know, about 70 lines of code or so. It would be obviously much less when we do functions. And with the switch statement, I think it would be even longer, the amount of code we'd written, just because of the syntax of the switch. But the if-else-if ladder works great here. Obviously, if I decide to add another option here. It's just a matter of coming in here, and you could do it anywhere really because it's all sort of mutually exclusive, right? And you could just do it right here. Else if, add it between this one, and there you've got your other option, just as easy as that. Okay, so I hope you enjoyed this challenge. This was a challenging challenge because it's using everything that we've learned so far, but there's a lot of logic going on here. Right? It's a simple program, but there's a lot of logic going on here. You've got, a do-while loop, you've got for loops looping through the iteration, and thank goodness that C++11 gave us this range-based for loop, because that makes it so simple. We don't have to do things like for int I equals 0, I less than, the size of the vector, and then increment I along the way. We don't have to deal with any of that. So that makes it really, really straightforward. Okay, so I hope you enjoyed this section. In this section, we'll talk about characters and strings. As we've already seen, the character type can hold values that represent characters. These values are basically integers that map to a character set, like the ASCII character set. And we've also seen that strings are sequences of characters. C++ supports two types of strings, C-style strings and C++ strings. So we'll first look at the cc-type library. This is a library of very simple but very useful functions that work with characters. For example, we can test characters to see if they're uppercase or lowercase, numeric, alphanumeric, punctuation, and more. We can also convert characters between lower and uppercase. After we learn about the cc-type functions, we'll talk about strings. As I said earlier, you can think of strings as a sequence of characters. So far, we've only used string literals, which were represented as a sequence of characters inside double quotes. I'll discuss both C-style strings and C++ strings in this section, and give you the basics of using each. However, you should be using C++ strings in modern C++. I think you'll understand why at the end of this section. First, we'll see what C-style strings are and how they're represented in memory. Then we'll see how to work with C-style strings using some of the string functions available in the C-string and C-standard-lib libraries. Then we'll learn about C++ strings. C++ strings are objects, just like our vectors were, and they're used using an object-oriented style of programming. In this section, we'll learn how to declare, initialize, assign, compare, and use some of the other C++ string methods. Methods are functions that work with objects. So let's look at C-style strings first in the next video. In this video, we'll talk about the functions that we can use with characters. The cc-type library includes very simple and very useful functions that allow the testing of characters for various properties, as well as the conversion of characters from upper to lower or lower to uppercase. In order to use these functions, you must include cc-type. The functions all expect a single character. In the case of the testing functions, they evaluate to true or false, and the conversion functions return the converted character. Let's see some of these functions. This table contains some of the functions in cc-type that allow for testing of characters. You call the function and pass in the character you wish to test in the parentheses. The function then evaluates to true or false depending on whether the character has the property you're testing or not. IsAlpha tests to see if the character is a letter, either uppercase or lowercase, and evaluates to true if it is or false otherwise. IsAlnum tests to see if the character is a letter or a digit. IsDigit tests to see if the character is a digit. IsLower tests to see if the character is a lowercase letter. IsPrint tests to see if the character is a printable character. IsPunct tests to see if the character is a punctuation character. IsUpper tests to see if the character is an uppercase letter. And IsSpace tests to see if the character is a white space character. There are a few other functions in cc-type that I haven't listed in the table. You can refer to the C++ docs for those. Now let's see the conversion functions. The two character conversion functions are toLower and toUpper. toLower evaluates the lowercase equivalent of the character passed in, and toUpper the uppercase equivalent. If these functions can't perform the conversion, Then the functions simply evaluate to the character that was passed in. As you can see, these functions are very handy. They're also extremely efficient. We'll use these functions in the next few videos when we talk more about strings. In the next video, we'll learn about C-style strings. I'll see you there. In this video, we'll learn about C-style strings. C-style strings are about as simple as it gets. They're a sequence of characters stored contiguously in memory. They're implemented as an array of characters, so you can access individual characters using the array subscript syntax that we've already learned. How do you know where the sequence of characters ends? C-style strings use a sentinel value that marks the end of the string. The null character is used, which is equivalent to the integer 0. So, C-style strings are often referred to as zero or null terminated strings. We've been using C-style strings all along in this course. We've used them mainly in our output statements as string literals. Recall that string literals are sequences of characters enclosed in double quotes. These string literals are constants, so we can't change them, just like we can't change integer literals. Even though we don't explicitly provide a null character at the end of the string literal, C++ inserts one for us. That's the way the end of string is handled. Let's see an example of a string literal and how it's stored in memory. Here's a real simple example that shows how C-style strings are stored in memory. In this case, we have a C-style string literal containing the sequence of characters C++ is fun. These characters are stored in a contiguous block of memory that can be accessed as an array. Notice that C++ is fun has exactly 10 characters, but the compiler allocated 11 characters for the array because it needed space for the null character at the end. Literals are great and very useful, but we more often than not need to create string variables. Let's see how we can create C-style string variables. In this example, we're declaring an array and initializing it to Frank, using initializer list syntax as we've been doing with integers and other types. Notice that the C++ compiler will allocate 6 characters for this array, since it needs to terminate the string with the null character. Also notice that the size of the array is fixed, so if I wanted to add a Y to Frank and create Frankie, I couldn't without having some potential problems, since the new string would not be null terminated. You won't get a compiler error or even a warning. In fact, in this case, my name sub 5 is still within the array bounds. Let's see another example. In this example, we are explicitly asking the compiler to allocate 8 characters for the character array. And we're initializing it to Frank. In this case, it will initialize the array with F, R, A, and K, and the rest of the space will be zeroed out with null characters. In this case, if I wanted to change the character at index 5, which is that first null character, to a lowercase y, it would be just fine, since the string now contains Frankie and is still null terminated. Let's see another example. In this example, we ask the compiler to allocate an array of 8 characters and we don't initialize them. This could be very problematic, because if you use this array as a string, all C-style string functions expect to find a null character. And here there may or may not be one. We really don't know what the data in the array is. Suppose we wanted to display the string now. How do you think this would happen? How do you think C-style strings are displayed? Well, in this case, we start at the first element of the array and we iterate through the array. At every character, we see if it's the null character. If it is, we stop since we reached the end of the string. If it's not, we print the character and then we move to the next character. In this case, we don't know what's going to happen. We might see a null right away, or we might not see a null for a very long time. In the meantime, I'm printing stuff to the screen. Some of the stuff may not even be displayable since some characters are control characters. You might think we can initialize C-style strings using the assignment operator, just like we have with other types, but this won't work. If we try to assign the C-style literal Frank to my name, we get a compiler error because that's not the way C-style strings work. Array names and literals evaluate to their location in memory, so we're effectively assigning one location to another, which is illegal. Think of this as saying assign 10 to 12. It doesn't make sense and the compiler won't allow it. In order to assign one string to another, we need to use a function called string copy that copies the C-style literal F, R, A, and K to the myName array. There are lots of C-style functions that C++ brings in from the C programming language. Let's see a few of them. The C-string library contains many functions that work with C-style strings. These functions are used to copy, concatenate, compare, search, get the length of a string, and many more. They all rely on one common factor, that the sequence of characters they're working on is terminated with a null character. If you're using C-style strings, you must be very aware of this. For example, suppose you have a C-style string and you want to determine its length. Well, let's say we have Frank. Since no length information is stored with the string, only the characters in the array, the only way to determine the length is to start counting at the first array element, and then increment along until you see the null character. So in the case of Frank, we would look at the F, increment 1, look at the R, 2, the A, 3, the N, 4, the K, 5, then we see a null character and we stop. Now we know that the length is 5. But if that null character is not there, we keep going and we keep counting. So the result will very likely be incorrect. Even worse, if you're copying one string into another and the string you're copying isn't null terminated, you'll very likely exceed the bounds of the target string and very likely cause a program crash. This all sounds pretty ominous, but in fact, we've been programming in C and C++ using C-style strings for a very long time, and we've gotten pretty good at understanding these issues. But wouldn't it be great if we didn't have to worry about these issues at all? That's where C++ strings come in. We'll talk about them later in this section. Here are a few examples that use the C-style string functions. You typically have a function and you pass into the function the name of the string or the string literal or both. We'll talk about functions in detail shortly, but conceptually they're really easy to understand. For example, if I'm a function and my job is to return the color of a crayon passed to me, then all I need from you is the crayon. So you call me and send me the crayon and I'll return red, green, blue, and so forth. That's the idea, and here it's the same. If you want to know the length of the string, pass in the string to the strlen function and it returns the string's length. Here are just a few examples that copy, concatenate, and compare strings. C++ also has another library called cstandardlib that contains functions that convert strings to other types. For example, if I have a string with the digits 1 and 2, I can convert that to the integer 12. Sometimes these are real useful functions. However, all of these functions rely on the same thing. They're all working with null terminated strings. If you're using C-style strings, you have to be very aware of that. Well, that completes this video. In the next video, we'll head over to the IDE and we'll write some examples using C-style strings. In this video, we'll go over some examples of using C-style strings. First thing you'll notice is I'm including C-string. I need to include that header file for the C-style string functions, and I'm also including CC_type. That's because I'm going to use some of the character-based functions in this example. Okay, so I'm using namespace standard, and I've declared 4 C-style string variables, which are really just arrays of characters on lines 9 through 12. First name, last name, full name, and temp. And I've made them to be pretty big, 20, 20, 50, and 50. That should allow us to put stuff in there without exceeding the bounds. Okay, so the first thing we'll do is, notice here, first name is uninitialized. They're actually all uninitialized. Let's display first name. This is a real problem because we've never initialized that array. So it's very likely we're going to get garbage. So let's run this. And by the way, I'm in the section 10 workspace in the C-style strings project. So let me run this. And there you can see the garbage right up here. You can see it right in there. What displays is, who knows, right? Whatever characters happen to be in those locations. You might get lucky and the null character might be in the first location, in which case nothing will print. But more often than not, you'll get garbage like this. And this is a real common symptom. And whether you're displaying to the console or inside a window in Microsoft Windows or X window, and you see something that displays like that on a button or up here on a title bar or something, that's a classic symptom of uninitialized string. Let me comment that out. We don't want uninitialized strings. Now, obviously, we'd want to initialize these guys just like that, or to a string if we want. So let me just go ahead and initialize all of them, which is really the best practice. Okay, so now they're all initialized. So the first thing we'll do is I'll uncomment these lines here. And this is nothing we haven't seen before. Pretty straightforward, right? Enter your first name, and we're using the extraction operator to read our first name into that variable first name, which is the array. So whatever I type in, I'm just going to use my name in these examples. Frank will be stored into first name, and it'll be F-R-A-N-K, and then the null character will automatically be put in there for us. Same thing with last name. Okay, so again, nothing we haven't seen before. Now here, let's talk about these two lines. In this case, let me grab my marker real quick. In this case, we're saying, hello, first name. Now, this will be replaced with the value of first name. What's the value of first name? Well, at this point, I have Frank in there. And remember, this is 20 big here. But in this case, let's just say I've got that. That's the null character. So how do we determine the value of first name? Well, we start here. Do we see a null? No. We move over. Do we see a null? No. And we keep going until we see that null. At that point, that's what's returned. So this will display Frank. That's really what's going on when we're displaying these C-style variables. Okay. So it's going to say, hello, Frank, your first name has, and then we see this function right here, the strlen, or the string length function. A function is nothing more than a request for somebody else to do something for you. And we'll write functions really soon, I think in the next section. So in this case, I'm calling the strlen function. I'm passing in that array of characters, Frank. So what's it going to do? It's going to do the same thing we just did here, right? Let me clean this up a little bit, and we'll walk through this again. So in this case, how does the string length determine the length of that name? Well, you start here. Is that a null? No. That's 1. Is that a null? No. That's 2. How about this guy? Nope. That's 3. The N? Nope. The K? That's 5. Now we see the null. The length is 5. That's what's being returned here. Now, strlen doesn't return an integer. It doesn't really return an unsigned integer. It returns a type called size t. And I haven't talked about that yet, but I'm going to now. Size t really is an unsigned integer. It could be an unsigned long. You really don't know what it is based on your system. That's the whole point. We really should be using size t, because regardless of what system you're on, this will work. You can be sure it will be unsigned though, right? Because it doesn't make sense to have negative sizes for strings or negative sizes for loop variables and things like that typically. So from this point forward, I'm going to start using size t where appropriate rather than int or unsigned. It's the more correct way of doing it. Okay, so that'll return 5. So this will display, hello, Frank, your first name has 5 characters. And your last name, same idea. It'll print out my last name here, and my last name has 11 characters. So it should display 11 characters. Okay, so let's run this example. My first name is Frank, and I'll put in my last name, Metropolis. And it says, hello, Frank, your first name has 5 characters, and your last name, Metropolis, has 11 characters. Exactly what we expect. Now, everything I'm talking about in this video is totally dependent on that guy right there. If for whatever reason those null characters or that null character is not there, you can imagine, right? We're going to keep counting until we hit one, which may be, 1,000 characters down the line in memory. Typically, you don't have to worry about it when you use these functions, strlen, cin, strcat, like we'll see down here. They handle that for you. But if you're working with strings on your own and you're processing characters and moving characters around, you've got to be aware that you need to null terminate your strings. Otherwise, you're going to run into problems. All right, let me clear this up real quick. And let's do another example down here. I'll uncomment this piece of code out, and we'll talk about that real quick. So what do we have now? Well, we have Frank in first name, right? So first name is Frank. I just typed it in, and I'll type it in again in the next example. What we're doing here is we're copying using the string copy function. We're copying first name to full name. This is the way it works. It's going from this right argument to the left one, not the other way around. This is confusing sometimes for students. So I'm copying first name into full name. So again, here was first name, and it had Frank in it. And over here is full name. Again, this is first name, and this is full name. How does it copy? Well, one character at a time. It's going to copy the F, the R, the A, the N, the K, and it's going to keep copying until it hits that null character. At that point, it copies the null character and it stops. Okay. So at this point, full name will have Frank followed by the null character. The strcat function is the concatenate function. In this case, what I'm doing is I'm adding a space. You can see the space right there in double quotes. I'm adding the space to full name. So now it's putting a space here, right in there, and then it's putting the null character. So at this point, that's going to be Frank followed by a space. I'll just use that underscore to denote the space. Then I'm doing another string cat. And what I'm doing now is I'm concatenating. Again, this goes this way. I'm concatenating the last name to the full name. So now I'm putting in my last name here. And it will also put in the null character at the end. And then I'm just displaying it. Okay. So notice what we're doing here. What we're doing is we're basically building up full name from first name and last name using strcat or string cat. Let's run this. And what I'll do here is I'll say, again, my first name is Frank and my last name is Metropolis. Hello, Frank. All that's the same. And then it says here, your full name is Frank Metropolis. Notice how it concatenated the Frank, the space, and the Metropolis into one. So full name now contains that string. Okay, so let's do another example. I'm going to comment all of this out so we're fresh every time. And in this example here, this is an example that shows you one of the behaviors of the cin extraction operator here. What I'm doing here is I'm prompting the user, me in this case, for my full name, and I'm going to enter the full name, and then I'm going to display the full name. Okay, so let me run that. And I'm just going to say my full name is Frank Metropolis. But now when I try to display my full name, notice I only get Frank. That's the normal behavior for that extraction operator. It's reading in FRANK space. That's a white space, so it stops. That's it. Okay. Sometimes you want to be able to read the entire name, right? The whole line. So this is what we'll do in these next few lines here. In this case, again, I'm prompting enter your full name, but now I'm using cin's getLine function. This works again with C-style strings. So in this case, I'm providing the name of that C-style string, or that array name here is full name, and a limit. This is how many characters maximum you're going to read. So I'm saying cin getLine. So this will stop either at 50 if you reach the max, or when the user presses enter. So in this case, it's going to read the whole name, right? So let me run that again, and I'll say Frank Metropolis again, and press enter. You can see that the full name now is the first name and the last name. So it's reading the entire line. Now, let me do a couple of more examples. Let's do a comparison example here. In this case, remember, full name will have my full name in it, Frank Metropolis. And what I'm doing that, I'm copying that to temp. Temp, if you recall, I'll scroll up real quick. Temp is another array of characters, pretty big, and that's 50 size, so my name will definitely fit in there. And when I say big size, my name will fit in there. That's one of the things you always have to worry about when you're working with C-style strings. You've always got to be sure that you've got enough storage. If you don't have enough storage, you're going to have a problem because you're going to run over the bounds and probably clobber some other memory location with something. Okay, so again, let's assume that I've typed in my name, and now I'm going to copy my name to temp. Then I want to compare those two. They should be the same, right? Because I just copied it to another variable name. Well, we can use the string compare function. We pass in the two strings that we want to compare, in this case, temp and full name. And if we get back a 0, that means that they're the same. If we don't get back a 0, that means they're not the same. So in this example, I expect to get back a 0. So let me run this real quick, and I'll type in my full name. They are the same. Frank Metropolis and Frank Metropolis are the same because it's the same string. So I did get back the 0. Okay. So now let's modify that string, and then we'll compare it again. So what we'll do this time is we'll use a for loop, and I'll uncomment this code out real quick. And you'll notice what we're doing. We're going from I equals 0, and notice I'm using size t here instead of int or unsigned. This is the better way to do it, the more correct way to do it. So I'm going from I equals 0, while I is less than the string length of the full name. Okay? Again, string length is going to return however many characters are in there. I want to be sure I'm going less than that because remember, we're going from 0 to the size minus 1. And I'm incrementing I by 1 each time. Then I'm using one of the character functions. I'm saying full name sub I. That's the specific character, right? So it's going to be F, R, A, N, K, and so forth. If it's an alpha character, right, a letter, then I'm going to convert that letter to uppercase and put it right back where it was. So now my name will be all capitalized. Okay, so let's run that. And I'll type in my name with mixed upper and lowercase. You can see here that it compared them and they're the same. And now my name is all uppercase because I used the toUpper function. So now let's compare those two now. Obviously, they're not the same, right? Because I just made one a little bit different. So let's do this. Let's comment all of this out and walk through it. And so what's going on here? I'm comparing temp and full name. They're not the same anymore, right? Full name is now all uppercase and temp is not. So I'm going to compare them and it's going to say, are they the same or are they different? Now I expect this to be different because this will not be equal to 0. Okay. So how does this work with the 0? Well, if the two strings are the same, and that's character by character lexically, the string compare function will return a 0. Otherwise, it'll return a negative number or a positive number depending on which of the strings is larger. Right? So in this case, I'm comparing them temp and full name and then full name and temp so you can see the result. So let's run this. So again, I'll use my name and press enter. So as you can see, the two strings are now different. And the string compare function will return 0 if the two strings are the same. You can see here that we're comparing two different strings. It returns less than 0 if the first string lexically comes before the second string, or return greater than 0 if the first string lexically comes after the second string. Okay, so that completes this video. This gives you a little bit of insight as how to use C-style strings and their functions. What we'll do next is we'll talk about C++ strings. In this video, we'll learn about C++ strings. Standard string is a class in the C++ standard template library, or STL. We could do an entire course on just the STL, and that course would be very long and complex. So in this video, I'll only talk about the major elements of the C++ string class. In order to use C++ strings, you must include the string header file. Strings are in the standard namespace, so in order to use them without using namespace standard, you must prefix them with standard and the scope resolution operator. This is also true for the standard string methods that work with C++ strings. Like C-style strings, C++ strings are stored contiguously in memory. However, unlike C-style strings, which are fixed in size, C++ strings are dynamic and can grow and shrink as needed at runtime. C++ strings work with the stream insertion and extraction operators, just like most other types in C++. The C++ string class provides a rich set of methods or functions that allow us to manipulate strings easily. Chances are that if you need to do something with a string, that functionality is already there for you without having to rewrite it from scratch. C++ strings also work with most of the operators that we're used to for assigning, comparing, and so forth. This is a huge advantage over C-style strings, since C-style strings don't work well with those operators. Even though C++ strings are preferred in most cases, sometimes you need to use C-style strings. Maybe you're interfacing with a library that's been optimized for C-style strings. Well, in this use case, you can still use C++ strings and take advantage of them. And when you need to, you can easily convert the C++ string into a C-style string and back again. Like vectors, C++ strings are safer since they provide methods that can bounds check and allow you to find errors in your code so you can fix them before your program goes into production. Let's see how we can declare and initialize C++ strings. In all the examples in this video, I'm assuming that the string header file has been included and that we're using the standard namespace. Here you can see 6 examples of declaration and initialization of C++ strings. There are other ways as well using constructor and assignment syntax, but I'm mainly using the initializer syntax in this video. In the first example, we declare S1 as a string. Notice that the string type is lowercase. Unlike C-style strings, C++ strings are always initialized. In this case, S1 is initialized to an empty string. No garbage in memory to have to worry about. In the second example, I'm declaring and initializing S2 to the string Frank. Notice that Frank is a C-style literal. That's okay. It will be converted to a C++ string. In the third example, S3 is initialized from S2. So a copy of S2 is created. S2 and S3 will both be Frank, but different Franks in different areas of memory. In the fourth example, I'm declaring and initializing S4 from Frank. but I'm only using the first 3 characters of the string Frank. So S4 will be initialized to the string FRA. In the 5th example, I'm initializing S5 from S3, which is Frank. But notice the 2 integers that follow the S3 in the initializer. The first integer is the starting index, and the second is the length. So in this case, we initialize S5 with the 2 characters at index 0 and 1 from S3. So S5 will be initialized to FR. Finally, we can initialize a string to a specific number of a specific character. In this case, 3 X's. Note that this uses constructor syntax with the parentheses instead of the curlies. Now that we've declared some strings, let's see how we can assign other values to them. With C++ strings, you can use the assignment operator. This feels much more natural than having to use the string copy function like we would have to in C-style strings. In this example, I've declared S1 and it's empty. Then I can assign the C-style literal C++ rocks to S1. Pretty cool and pretty easy. S1 will grow dynamically as needed. In the second example, I've declared S2 and initialized it to hello. Then I assign S1 to S2. In this case, S2 will no longer contain hello. It will contain a copy of S1, C++ rocks. Let's see how we can concatenate strings together. Concatenation of strings just means building up a string from 2 other strings. We can use the plus operator to concatenate C++ strings. In this example, I created 2 strings, part 1, which is C++, and part 2, which is powerful. Then I have an empty string sentence. Notice that I'm assigning to sentence the concatenated result of part 1 plus a space plus part 2 plus a space plus language. If I displayed sentence now, it would display C++ is a powerful language. Notice that the last example on the slide will not compile. This is because we have 2 C-style literals, and you can't concatenate C-style literals. It only works for C++ strings. A combination of C++ strings and C-style strings is okay though, as we saw in the previous assignments. Just like we did with vectors, we can use the same operators to access string elements. In this case, the elements of a string are characters, so we can use the subscript operator as well as the @ method. Remember, the @ method performs bounds checking, so if you go over bounds, you'll get an exception which you can fix. Let's see how we can display string characters one at a time. In this example, we have a string S1 initialized to Frank. We can use the range-based for loop to display the string characters. In this case, FRANK, and the null character will be displayed. Pretty much what you expected, right? Notice that the type of the loop variable is char in this case. What do you think will happen if we change that to integer? In this case, I've changed it to integer. Is this what you expected? We told the compiler to use an integer, and that's exactly what it's doing. So instead of displaying the character value of each element in the string, it's displaying the integer value that represents those characters. So in this case, 70, 114, 97, 110, 107, and 0, which represent FRANK and, of course, the null character. These are the ASCII codes for those characters. Comparing C++ strings couldn't be any easier or more intuitive. We use the same equality and relational operators that we've been using all along. We're comparing 2 string objects, so they'll be compared character by character, and their character values will be compared lexically. So a capital A is less than a capital Z, and a capital A is less than a lowercase a. That's because the capital letters come before the lowercase letters in the ASCII table. We can't use these operators on 2 C-style literals, but we can use them in the following cases. If we have 2 C++ strings, if we have 1 C++ string and a C-style literal, or if we have 1 C++ string and 1 C-style string. Let's see some examples. Here we're defining 5 C++ string variables, S1 through S5, and then we perform some comparison operations and see the results. Of course, you would normally use these Boolean expressions in an if statement or looping conditional expressions. In the first example, we check to see if S1 is equal to S5. This is true since they both contain the string apple. S1 equals S2 is false since S1 is apple and S2 is banana. How about S1 not equal to S2? This is true since apple is not equal to banana. In the case of S1 less than S2, this is also true since apple comes before banana lexically in the ASCII table. S2 greater than S1 is also true, since banana comes before apple lexically. Notice that banana has an uppercase B, whereas apple has a lowercase a. S4 less than S5 is false, since apple with a lowercase does not come before apple with an uppercase. And then finally, A1 equal apple is true, because they're the same. Notice in this case, apple is a C-style string literal. The C++ string class has a rich set of very useful methods. Too many methods to cover in detail in this video. I encourage you to study the C++ string class, since it's going to be a class that you'll use often, and it's important that you know what it provides so you don't reinvent the wheel when you need to solve a problem. The substring method extracts a substring from a C++ string. It doesn't change the string, it simply returns the substring, and you can do whatever you want with it. In this case, I'm simply displaying it, but you could easily assign it to a string variable. Here I've initialized S1 to this is a string. The first example takes a substring of this string starting at index 0 and including exactly 4 characters. If there are less than 4 characters left in the original string, then all the remaining characters are included. In this case, the substring is the first word in the string, this. In the second example, we return the substring starting at index 5 and include 2 characters. That's the substring is. Finally, the last example starts at index 10 and includes 4 characters. This will return the substring test. Let's see how we can search a string for another. The C++ string class has a very handy method named find. Find works with characters and strings. It expects a string or character and returns the index or position of the beginning of that string or character in the original string. So if you have a string S1 that's initialized to this is a test, and we want to find the string this, we'd get back a 0 since this starts at index 0. In the second example, we're looking for the string is. In this case, it would return 2 since the first is starts at index 2. In the third example, we're finding the string test and we get back a 10. In the fourth example, we're searching for a single character, the lowercase e, which is found at index 11. In the fifth example, we use a variant of the method that also allows the index where you want to start the search from. In this case, I want to find the is substring again, but I want to start at index 4, so this time it finds the is that's located at index 5. Finally, what happens if the string or character we want to find just isn't there? Well, in this case, the method returns an position, which means no position information available. You can check for this value in an if statement, and if true, you know what you were searching for wasn't there. Very easy, very powerful. There's also an rfind method that starts searching from the end of the string to the beginning of the string. We can also remove characters from a C++ string using the erase and clear methods. For the erase method, you provide the starting index and how many characters to delete. The clear method deletes all the characters in the string, so the string becomes the empty string. We've seen a lot of string methods, and you can see how powerful this class is. Let's look at one more useful method and one more useful operator that are commonly used. The method is the length method. It returns the number of characters currently in the string object. In this example, S1 is Frank, so S1.length will return a 5. This is so easy and something that's impossible to do with C-style strings since they don't contain size information. The operator I wanted to cover is the compound concatenation assignment operator. In this case, S1 is Frank, and I can say S1 plus equals James. And James will be concatenated to Frank, and the entire result string will be assigned back to S1. This is really handy and works very much the same way that the compound assignment operators worked with integers and doubles and so forth. There are also many more methods in the C++ string class for you to discover as you study C++. Okay, there's one more thing I'd like to talk about before we end this video. Input with C++ strings. C++ strings work great with input and output streams. As you've seen, inserting C++ string variables to an output stream like cout is pretty easy and works just like we've been doing all along. Extracting a C++ string from an input stream like cin also works the same way we expect. However, there's one issue that's also true for C-style strings. Suppose we've defined S1 as a C++ string, and we extract a string from cin as usual. Now, suppose I type in hello space there. When I display S1, I will only see hello. The there was not extracted. This is because the extraction operator stops when it sees white space. In many cases, we want to read an entire line of text up to when the user presses enter. For example, I want the string to be hello there. Suppose I asked you to enter your full name. I want to be able to read William Smith, not just William. In this case, we can use the getLine function. The getLine function has a couple of variants. The first variant expects two elements inside the parentheses. The first element is the input stream. In this case, we're using cin, which defaults to the keyboard. The second element is the name of the C++ string where you want the text that the user enters stored. That's it, very easy. In the example, I'm saying getLine cin S1. Now, everything the user types is stored into S1. getLine stops reading when it sees the new line. It doesn't include the new line in the string, it just discards it. The other variant of getLine has another element in the parentheses. The first two are the same as before, the input stream and the C++ string variable name. The third is called the delimiter. This is the character that you want getLine to stop reading input at. So as long as the user doesn't enter this character, everything will be stored in the string variable. Once the delimiter is seen, it's not included in the string variable and it's discarded. In the last example, I'm using a lowercase x as the delimiter. So if I type this is x, then the string stored in S1 will be this is, and the x is discarded. Well, we've covered a lot of material in this video, and there's much more in the string class to learn. But this gives you a good starting point so you can use the C++ string class effectively. Also, you've now been introduced to object-oriented programming with both vectors and strings. Pretty soon we'll be developing our own classes, which is pretty cool. That completes this video. Please play with the string class, create examples, assign, delete, display, and try out some of the methods in this video. It won't take long before you're really comfortable working with C++ strings. In this video, I'd like to go over using the C++ string class and some examples there. So I'm in the Section 10 workspace in the CPP strings project. Now, remember, the string class is a class. So when we create strings in this case, here you see I'm creating 8 strings from S0 to S7 on lines 9 to 16. These are objects. We'll talk about exactly what objects are in the world of object-oriented programming in a future video. But we are using object-oriented programming here to work with these C++ string objects. Okay, it's important that you include the string library. Otherwise, you'll get a lot of compiler errors, and I'm using the standard namespace. First thing is, let's declare and initialize some of these string objects. Here I'm declaring S0 through S7. You can see S0, I'm just saying string S0. It's important to understand that with classes and objects in this case, S0 is an object. I am getting an initialized object. There's not going to be any garbage in there. And we'll display that in a second, just so you can see what that looks like. Then I'm declaring other string objects here. So S1 is being initialized to Apple, S2 to banana, S3 to kiwi, S4 to apple, and so forth. S5 is being initialized to S1. Well, S1 is Apple. So a copy of that string is going to be put into S5. So S5 is going to be its own version of Apple. So if I change S1, it's not going to affect S5. There's also a couple of other initializers. There's actually a bunch of initializers and constructor style initializers, a whole bunch of examples that you can use, but I'm just sticking to the commonly used ones in modern C++. In this case, S6 is S1. I'm initializing it from S1, which is Apple, but I'm only using a part of it. I'm starting at index 0 and I want 3 characters. So it's only going to be initialized to the string app. And then in this case, S7, I'm initializing that string to 10x characters. Notice the x is in single quotes here, so that's a character. And also notice that I'm using parentheses here and not curlies. This is a constructor style initialization, and that's the one that works with this example. Before we look at the initialization values, let's look at this right here. Notice that I declared that string object S0. If this had been the example that we saw using C-style strings, and we never initialized it. You remember we saw all that garbage? You're not going to get that here. So if I display S0, you won't see anything because it's empty. And if I ask S0, what's your length? This is a method. This is an object, and this is what object-oriented programming is all about. I'm asking the S0 object, in other words, this string right here, hey, what's your length? And it's going to return its length. In this case, I expect back a 0 because it's an empty string. So let me run this. And you can see that nothing printed out because the string is empty. And I get back a 0, which says that the string has no length. It's empty. So you can see that it is being initialized. That's really important with objects. Okay, I'm going to comment that out. And then let's look at some of these initialization examples. I've just initialized those objects right up here where I declared them. Now I'm just going to display them. And you can see that we're getting exactly what we expected here. Let me scroll that up just a little bit. So S1 is apple, S2 is banana, then I've got kiwi, apple with a lowercase a, apple, and app, that's that 3, the initializer where we only wanted the first 3 characters, and then I've got 10 X's. Okay, so you can see really powerful, really easy way to initialize these string objects. So now let's comment this out again and work with some of the operators and methods of the string class. In this case, I'm comparing. If you recall, using C-style strings, we had to use the strcmp, or the string compare function, pass in 2 strings and get back either 0 or a positive value or a negative value, and then we'd have to check things like that. Well, here we can just use the operators that we're used to. And I'm using the bool alpha IO manipulator here just so it displays the words true and false. And you can see I've got a whole bunch of examples, and it's actually easier to run it than to read all that code. But you can see here that I'm comparing apple with apple, and I get back true. I'm comparing apple with banana, I get back false. Then I'm asking, is apple not equal to banana? That's true because they're not equal. Is apple less than banana? True because the capital A comes before the capital B in the ASCII table. What about banana greater than apple? Yes, again, I just flipped the sign and flipped the strings. What about apple with a lowercase a? Is that less than apple with an uppercase a? It is not because the uppercase characters come before the lowercase characters in the ASCII table. And then the last one I'm using is right here where I'm actually comparing an object, S1, with a C-style string literal apple. And that works perfectly fine because what happens is this string literal right here gets converted to an object, and then we're doing object-to-object comparison. So that's true. Remember, it's doing character by character comparison. Okay, so real familiar, real intuitive, very easy to use. So let me comment that out. And let's do assignment. If you recall with the C-style strings, we had to do strcpy or string copy. Using C++ string objects, we just use the assignment operator, just like we're used to. So they feel like they're really part of the language, just like you would with integers and doubles and characters and so forth. So in this case, I'm assigning watermelon to S1. Okay. Whatever was in S1 before is now gone. Okay, I've overwritten it with watermelon. And then I'm outputting S1 is now, and obviously I expect back watermelon. When I say assign S1, well, S1 is watermelon to S2, I'm going to get a copy of that watermelon object, right? So I'm not going to, they're not pointing to the same watermelon. I'm going to get 2 copies that are individual. So if I change S1, it won't affect S2 and vice versa. And if I display S2, I also expect watermelon here. Okay. Here I'm saying S3 is Frank, so I'm assigning the string Frank to S3, and that should also display Frank. Now, once I've assigned these strings, I can manipulate them. So in this case, I can say change the 0th character in S3. Well, that's the F in Frank right here. Change that to a capital C. And notice single quotes because I'm changing a character. So I'm saying assign the capital C to the first element of that string, right? The one at the 0 index. So this would change it to crank, which will print out CRANK. I can also use the @ method. Again, this is the whole idea of object-oriented programming. I'm saying, hey, S3, change the character at position 0 to a capital P. So when I display that, it should display prank. Let's run that and double check. So you can see here that S1 is watermelon, S2 is watermelon, S3 is Frank, and then I'm changing the first letter of Frank to crank, to C, sorry, and displaying crank. and then I'm changing it to a P and displaying prank. All right, I'll comment this out, and let's look at concatenation. I'll compare this to the C-style string where we had to use the string cat function, strcat, to concatenate two strings. Here, we could just simply use the plus operator. And in this case, I'm saying assign watermelon to S3. Okay, that's easy. But now I'm saying S3 equals S5. Well, S5 is apple, and S2 is banana, and juice. So I'm concatenating these 1, 2, 3, 4 strings together by simply using the plus operator. The plus operator is considered overloaded. That means it works with integers, it works with doubles, and in this case, it works with string objects. Okay. So what we're going to do here is we're going to say apple and banana juice and assign that to S3. So in this case, watermelon is gone. We're overriding that. And then when we display S3, it should say apple and banana juice. All right, so let me run that quickly. And there you go. S3 is now apple and banana juice, just like we expect. If you try something like this, you're going to get a compiler error. The problem here is that we've got a C-style string literal and another C-style string literal and the plus operator. C-style strings don't work with the plus operator. If you wanted to do something like this, you would have to use strcat and concatenate them together. In this case, you're going to get a compiler error saying something about, I don't know what to do with these two character arrays and this binary operator. Okay, so keep that in mind. If you're trying to use the plus operator, you've got to use it on at least one of the objects. Notice over here, we're using an object and a C-style string literal. That's okay because it'll convert. But when you've got two C-style string literals like this, it doesn't know what to do. Let's move on and talk about looping. In this case, we're going to use a for loop to loop through a string. Okay. Remember, a string is simply a collection, right? A bunch of characters. So we can easily loop through them. And we'll loop through them two different ways. First, we'll use a regular for loop, and then we'll use the range-based for loop. In this case, I'm assigning apple to S1, just so we have something to start with right here. And I'm initializing I to 0. Notice that the type of I is size t. This is really the proper way to do this. It's always going to be a non-negative number, right? Because we're looping through a string. Now, if you've got looping variables that need to go negative, you don't want to use size t. You just want to use a regular integer or something that's signed. But in these kinds of examples, size t is the proper type to use. So I'm initializing I to 0. And I'm going to loop while I is less than the string's length. Remember, we're going from 0 to the length minus 1. So in this case, I'm asking the S1 object, what's your length? And it's returning 5 because it's apple. So I'm going to loop 0, 1, 2, 3, 4, and then I'm going to stop. And as you see, I'm incrementing 1 each time. So every time through the loop, all I'm doing is just simply outputting that character at the ith location. So cout s1.at_i. I could use array subscript syntax. They both work. The .at method does bounds checking. The subscript method does not. So when I run this, I should see apple print out across the screen. And there it is. I'm just displaying it one letter at a time. I can also do this using the range-based for loop, in which case I'm just saying for every character C in S1, output it. Right, so it's going to go A, P, P, L, E, stop. So in this case, I see apple twice now, right? Once for the for loop and once for the range-based for loop. You can see some of these are very, very intuitive and easy to use. There's a couple left. Let's talk about substring here. This one, again, is very intuitive. Suppose S1 this is a test. I've just assigned that string to S1. And I want the substring that starts at 0 and is 4 long. So it's going to go T, H, I, S, right? The capital T is index 0. So that's going to return the word this, or the string this. In the second substring example, I'm starting at index 5, which is 0, 1, 2, 3, 4, 5. So it's starting at the I and is, and I want 2 characters. So it's grabbing this is right there. And that's what it's returning. And then the last one, I'm starting at index 10, which is the lowercase t in test, and I just want 4 back, and it's giving me test. So you can see it's very, very easy. And of course, all these, you can see here, it's displaying this is a test. All these are hard-coded, but you can certainly use variables for these integers and loop through in loops and grab pieces of substrings, and you can do a lot of really cool stuff. We can erase characters. In this example, I'm saying S1. Again, I'm assigning this is a test to it, and I'm erasing from S1. Again, notice the object-oriented style. Think of this almost as you're asking the S1 object, right? Because notice it's S1 dot. So you're saying the erase method is going to execute on that object, S1. Because we could have S2.erase, S8.erase, anything.erase, right? But in this case, it's happening on S1, which is, this is a test right here. So what I'm saying here is erase starting at 0 and erase 5 characters. So it's going to erase the capital T, the H, the I, the S, and the space. When I display that, S1 is now just the is a test part. I got rid of the this and the space from the beginning. All right, let's do a couple of more. The get line is a little bit different from the get line that we saw with C strings. If you remember with C strings, we said C in dot get line, and we had a length. Well, we're not worried about a length here because the C++ string class handles lengths for us. So it looks a little different, but it's the same basic effect. Here I've got a new string that I'm declaring called full name, and I'm initializing it to empty. I'm asking the user to enter their full name, and then I'm using the getLine function here, and I'm passing in where I want to get the input from, in this case the keyboard or cin, and where I want to store the result, full name. This will get an entire line up until I press enter. So, and then I just display the name. So in this case, if I run this and type my name, notice full name is Frank Metropolis, my entire name. It doesn't stop at the space the same way that the extraction operator does. The last thing we'll do is we'll look at the find method, which is a real handy method. So in this case, here's the secret word. The secret word is boo. That's the string. And I've got a word variable here, which is a string object. I'm asking the user to enter the word to find. The idea is they're going to type one of these words in here, right? And I'm going to tell them where that word is in the string, what position it begins at. So if I typed in the, I'm saying, hey, S1, again, the S1 object, find that word within you. So it's going to find the word the within it, and it's going to return 0 because it starts at the 0 index right there. That's the T. Again, I'm using a size T for the type because it's always going to be right 0 or greater or an error. And I'll talk about the error in a second. So at this point, I'm looking for that word in the string, and position holds its position whether it was found or not. How do I know whether it was found or not? I need to see if the position returned was that value, right? String end position, no position. So in this case, if the position I got back is not equal to that, then I found it. So I'm simply going to display found word at position, whatever. Otherwise, it wasn't found. So let's run this. And remember, the string is, the secret word is boo. So I'm going to run this and search for boo. And it says I found it at position 19. Let's run it again, and we'll use the word secret this time. It found it at position 4. And you can see there it is, right there at position 4. And we could try to find something that's not there, like hello. And it says hello, not found. Okay, so let me wrap up this video now. You have all the elements you need for the challenge that's coming up next. You could certainly try the challenge using C-style strings and then C++ strings, but I'm just going to do it using C++ strings because we really should be using C++ strings going forward. All right, so head off to the challenge. Hello, welcome to the Section 10 challenge. In this challenge, what I'm asking you to do is to create a substitution cipher program. This is really straightforward, but it'll give you some experience using the C++ string class. Now, there's an easy way to do this and a not so easy way to do this. I'm not going to tell you what the easy way to do this is because I want you to learn and try to figure it out on your own. Let me talk about the challenge. A simple, very old method of sending messages is the substitution cipher. I remember using this as a kid with some of my friends. We used to have something called a secret decoder ring. And the idea is you have a message, and then you look at every character in that message and you replace it with the character on the ring. So for example, every time you see a lowercase a, it gets replaced with a capital X. Or every time you see a lowercase b, it gets replaced with a capital Z, and so forth. So it's called the substitution cipher. It's really a straightforward cipher. It's not a very secure cipher at all, but it's a fun cipher to do. So here's the idea. I want you to write a program that asks the user to enter a secret message. That'll be a string. And then I want you to encrypt that message using the substitution cipher and display the encrypted message. Then take that encrypted message and decrypt it back to the original message. Okay? You can use two strings for your substitution. You can have one string for the alphabet. And let me write this here for you. That way you can maybe understand a little bit better. So let's say you have one string, which is the alphabet. And this string contains all the characters that you want to substitute. So for example, let's say we've got A, B, C, and so forth, and capital A, capital B, capital C. Okay. Then I've got another string called the key. And you can name these anything you like. And the idea here is that for every character up in the alphabet string, you're going to have a character in the key string that'll substitute it. So if I want to substitute that lowercase a for an X, it'll be here. And let's say that the B gets a Z and the C gets a Q. And then this uppercase A gets a lowercase, let's say Z, a lowercase q, and a lowercase d. It doesn't really matter what you replace them with. So now the idea is really straightforward. Whenever you see the secret message, let's say the secret message is ABC. You look in the alphabet, you look for that little a, you find it in position 0. Then you go to the key, look in position 0, and whatever's there, you replace it. You do the same thing with lowercase b. It's going to be replaced with a Z. And you do the same thing with the lowercase c. It'll replace it with a Q. Okay, obviously, you just keep going down the string. Whatever you find, you replace. So that would be my original message. This is now my encrypted message. How would I decrypt the message? You do the same thing, just the other way around. You look in the key for an X. I find it at position 0. So I go to position 0 in my alphabet, and I grab the little a. Again, I look for the Z. It's in position 1. There's my B in position 1. And then my Q is going to be in position 3. Or sorry, position 2. And it gives me my C. So there you go. Really, really straightforward to do. Make the cipher stronger if you wish. This is a really weak cipher. Right now, it's only substituting the letters. And let me scroll down here just a little bit to show you what I'm giving you to start with. You can see what I'm giving you to start with. I'm giving you an alphabet, which is a string of all the lowercase and uppercase letters. I kept these in order just to make it easier to debug. And then you've got the key. Those are the substitutions. So for every one of these letters, there is an equivalent letter here that we're going to substitute. So for example, whenever we see a lowercase a in our message, we're going to substitute it with a capital X. Whenever I see a capital Z, I'm going to substitute it with a lowercase r. That's for encryption. And then for decryption, you just read the encrypted string and you go the other way around. So if you see a capital X in your encrypted string, you'll replace it with a lowercase a to decrypt it. That's it. Really straightforward. As I said, I'm only using letters here. I'm not dealing with numbers or spaces. You can be as creative as you want with that. There's a lot of ways to make this a lot stronger and just have fun doing it. Remember, I'm writing this right here on line 28. Remember, the less code you write, the less code you have to test. You reuse existing functionality in the libraries. Use the code that's in the string class. Don't try to create all this on your own. Remember the KISS principle. Keep this as simple as you can. Reuse as much as you can. And that makes your program very likely a lot more correct than it will be if you try to do everything on your own. Remember, those library functions and methods that we've used, they've been tested and they've been debugged for years and years. So they're pretty solid. So reuse those. So let me give you a sample run so that you can see what to expect. So I'm going to run this, and you can see here, enter your secret message. And I'll say, I'll meet you at Billy's house at 10 a.m. Okay, now I'll press enter, and it says encrypting message, and here's the encrypted message. You can see it's replacing characters. it's pretty obvious what's going on here, right? You can see the capital I in isle is being replaced with a lowercase j. The apostrophe is not being replaced at all because I'm only dealing with letters. The lowercase l is being replaced with the capital D, you can see here. So you can see going across that that's your encrypted message. Then I'm taking that encrypted message and decrypting it, just doing the opposite I just did, and I got back the same message I started with. Okay, so you can see it's pretty easy. So my secret message would be, this is my secret message. There's the encrypted message. You can see the third character here is an I, which is being replaced by a capital J. And you can see the I again right here in the is, and there's the capital J again. Okay, so have fun, like I said, and make it stronger. That's what I like to do. Learn and play around with ideas that you may have to make this stronger. It's a lot of fun to try. Okay, so when you're done, I'll see you over in the solution, and I'll show you my solution. Welcome back. I hope you enjoyed the Cipher challenge, and I hope you were successful with it, and I hope you extended it even further. If you did, post it on the forum. Share what you did. That's pretty fun stuff. Okay, so what do we need? First thing we need to do is ask the user to enter a secret message, right? So let's do that first. Let's knock that out before we even start writing any other code. So we need a string object, and we can call that string object secret message, and we'll initialize it. That's what the user is going to type in. Okay. So I'm going to say cout, enter a secret message. And we'll leave it just like that. And let me fix that typo. And you know what? Let me use proper English here. Enter your secret message. Now the user is going to enter their message, and we need to read it. It's potentially more than one word, so we can't just use cin an extraction operator. We're going to use getLine. And I want to get a line of text from cin, and I want to store it in secret message. Okay, so now at this point, secret message, that string object, will contain whatever the user typed in. Perfect. So we want to encrypt that string. Well, I need to store the encrypted message somewhere, right? So let's create another string object, and we'll call it encrypted message. And we'll initialize that as well. That's going to hold the encrypted message once we finish encrypting it. But at this point, it's just simply empty. So we'll do a little output statement here just so we can see some processing. And we'll say something like encrypting message. And we'll put an end line at the end. All right, so now we start to process. What do we need to do? Well, there's a lot of different ways to do this. There's the easy way and the harder way. Let's talk about the harder way first. Suppose that the message is Frank. That's the secret message. Well, I need to iterate through that string. Obviously, I need to look at the F, the R, the A, the N, the K. I've got to do that no matter what, because I've got to look at every single character. Well, what I could do is I could read the first character, that's the F. Then I can loop through this array here, looking for that F. And when I find it, I need to know what position it's in. So I could have a counter that's counting up, right? So that when I start at 0 and then I go to the next one, eventually it's going to find it and I've got a position. That's the hard way. That's not the way I want to do it. Remember, the string class has a method in it called find. So if I want to find that character F, it's going to return the position of F, or it's going to return no position. That's really all I care about. Okay, so that's the way I'm going to solve this problem. Less code is better. So let's solve this. So right here, we're about to encrypt the message. Now we need to iterate through the secret message, one character at a time. So I'm going to use a range-based for loop here. It's perfect for this. So I'm going to say for every character C in my secret message. So now in the loop, I have access to C, which represents the current character I'm looking at in my secret message, right? So I'm going to call the find method in the alphabet string. I'm going to ask the alphabet string to find C, right? So if C is F, it's going to find that lowercase f and return its position. Now that position's type is size T, just like we mentioned before. That's an unsigned integer that's really dependent on your platform. This will work everywhere. We'll call it position. And I'm going to ask the alphabet string, or the alphabet object, to find that character in itself. If it finds it, we're good. We're going to substitute it with the equivalent character at the same position and key. If it doesn't find it, then we're just going to process that character as is. It's not one of these. So I'm not going to substitute it. I'm just going to use it. All right, so what do we need? We need an if statement. We're going to say if the position is not equal to no position. What does that mean? That means we found it, right? Let's do the else. And I'll just use a block else in case we need to add some code later. Now, if we didn't find it in here, we're not going to substitute. We're just going to use the character as is, right? So I'm going to say encrypted message plus equals C. Just add the character as is to the encrypted message. We're not going to substitute it. Now, what if we do need to substitute it? Let's go back here again. We need a new character, right? We need the character in the key. So let's create a variable called new character, and we can initialize this variable to the character in the string at that position, the key string, right? So we have position already. So we can ask, again, we can ask the key string to give us the variable at that position. And we can initialize it to that. So now we've got the new character that we want to substitute. And what do? We simply say encrypted message plus equals new character. That's it. That should be all the code we need. Now let's just output the encrypted message. So the encrypted message would be the encrypted message. All right, so let's run this. This is the first half. This is just the encryption side. But you can see the code is really easy to understand, very straightforward. So let's run it. And let's say this is a test. And that's the encrypted message right there. Okay, now let's do a simple test case. We know that we're going to replace the lowercase a. You can see it right here. Oops, let me use my pen real quick. You can see that we're going to replace the lowercase a with an uppercase X. And it's obviously the capital Z with an R. So a good test case would be A, Z, 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 and we expect back X, 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 R, 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 right? That's the encrypted. So let's try that out. So we'll do 3 lowercase a's and 3 uppercase Z's. A, Z, Z, Z. And as I said, what we expect back is XXX, lowercase 3 R's. That's exactly what we want. Okay, so it looks like we're in the ballpark. Now, obviously, you would have to test a lot better than this, but that's a good example of a simple test case that tells you you're definitely on track. I'll erase this, and let's try a couple more. Let's try meet me at Bill's house. Now, in this case, you see we have an apostrophe. We're not going to handle that apostrophe, right? We're not substituting, so we're just going to print it out as is. So I expect to see that apostrophe in the encrypted string in the same position. So you can see here, there it is right there. So that's correct. All right, so that's the encrypted message. Now let's decrypt the message. Same idea, right? We're just going the other way. We need a string object for the decrypted message. And we'll initialize that to an empty string as well. We'll say cout. Let's do another new line here, and we'll say decrypting message. All right, so now let's do the code again. What are we doing this time? Well, this time we're looping through the encrypted message, right? Grabbing those characters, finding them in the key, and substituting them back in the alphabet. All right, so let's do it. It's the same exact idea, except we're going backwards here. So for every character, let's call it C, in the encrypted message this time, for every character in there, we're doing exactly the same thing. The position is we're going to ask the key this time to find that character. And then if the position is not equal to no position, then we found it. Right? The else part means just handle it as is. So let's handle that part real easy. So this time we're going to save this to the decrypted message, right? So decrypted message plus equals C. In this case, we did find it. So we want to get a new character again, just like we did before. There's my new character. And I want to initialize it to, this time, not the key, but the alphabets dot at position. So give me the character at the same position, but in the alphabet string. And I'll initialize it to that. And then here we'll just say decrypted message plus equals new char. Awesome. That's it. Our string should be decrypted at this point. And what we'll do here is we'll just say cout. Put another new line here in front. Decrypted message, and I'll fix that typo in a second. In this case, it would be decrypted message followed by a new line. Okay, let's try this out. Hopefully we get back what we started with, right? So enter your secret message. This is a test. I'm encrypting first. That's the encrypted message right here. Then I'm decrypting and I'm getting back this is a test. Perfect. Let's try a couple more. Meet me at Bill's house at, let's say, 12:30 p.m. Okay, this is a good test case because, well, maybe Nil's house, not Bill's house. Meet me at Nil's house. You see we have an apostrophe. We have the 1, the 2, the colon, and the 3 and the 0. We're not handling those since they're not letters. Okay? So we should see those characters as is in the encrypted string. So let's try that. There you go. There's the apostrophe. There's the 12, the colon, the 30, just as we expected. And then when we decrypt the message, we get back, meet me at Nil's house at 12:30 p.m. Okay. Now, suppose we wanted to make this a little better, not a lot better, but a little better. Let's deal with those spaces, right? I want to fill up those spaces with something. So what we could do is we could come up here to my alphabet, and I can insert a space right at the beginning. That's a space character. Now, what am I going to replace the space character with? Anything I want that's not already in here. Let's say one of those characters, a left bracket. That's fine, but now we've got to deal with the left bracket, right? So let's put the left bracket up here, and we're going to replace that with a space because we've got to go both ways or it's not going to work. Right, so now we're going to handle spaces. At least we'll fill up all that void space. So let's try to run it, and we'll do something like this is a test. And you can see now it's sticking those square brackets in there. So it makes it look a little more jumbled up at least. Obviously, this is so easy to break. And then the decrypted message is still correct. This is a test. There's a lot of things you can do here. There's some real famous ciphers that are substitution ciphers, like the keyword cipher and the Caesar cipher that you can play around with. You can use random numbers. We'll talk about generating random numbers so that maybe the first time you see a space, you replace it with something, and the second time you replace it with something else. That would just make it a little bit more interesting and hard to break. But there you go. This is an example of using C++'s string class. Very easy. I mean, there's no counting. There's no checking to make sure that things fit. It's handling everything for me. All right, so hopefully your solution is similar. If it's not, you can learn from this one. And if you've got a great solution, you can share it with the rest of the class. I'll see you in the next video. In this section of the course, we'll learn about C++ functions. Functions allow us to divide our programs into modular units of executable code and call and reuse these units as we wish. Functions are a very powerful abstraction mechanism. You've already seen functions defined, the main function that we've been using in every program. And you've also used some functions such as getLine and the C-style string functions, string copy, string length, and others. In this section, we'll understand what functions are and why they're so useful. Then we'll look at functions in detail. First, we'll see how to define functions and create function prototypes that make our functions useful anywhere in our code. As we've already seen, when we call a function, we usually send information to the function. This information is sent in the form of function parameters. We'll see how to define these parameters and exactly how they work. Functions also usually return some kind of information to us when they're done processing. For example, if we have a function that calculates the square root of a number, well, that function expects the number, and it will return to us the square root of the number, which we can use however we wish. Functions can also take many parameters, and in some cases, we want to default the value of some of those parameters so we don't have to provide them every time. We'll learn how to set these default values per parameters to make our code easier to write. Then we'll learn how to pass arrays to functions and how to work with them inside the function. I'll discuss references in the next section, but we'll look at how we can pass information to a function efficiently by avoiding copying. We'll also see how we can change past information as well as protect it from change. Then we'll discuss inline functions. Inline functions are functions that the compiler optimizes to avoid the overhead involved when we call functions. Remember when we used the auto keyword to allow the compiler to deduce the type of a variable? Well, we can also use the auto keyword to allow the compiler to deduce the type of the function return value. This is pretty cool, and it can save us from writing a lot of unnecessarily complex code. Finally, we'll learn about recursive functions. These are functions that call themselves. You might be wondering, why would a function call itself? You'll see, it's pretty cool, and it can help solve a class of problems that would be more complex to solve without recursion. At the end of this section, we'll do a challenge project, and we'll be well on our way to starting to learn object-oriented programming. Let's get started. In this video, we'll learn about what functions are in C++. When we develop C++ programs, we typically use the predefined functions and classes in the C++ standard libraries. These are functions and classes that have already been written for us and tested, and they're available for us to use. We've already seen how useful the standard vector and standard string classes can be. C++ has many other libraries that we can use in the same way. Depending on our application, we may also use third-party functions and libraries. These may be open source, commercial, or other types of libraries that have been developed by other programmers and are available to use in our applications. So if we want to develop games in C++, we'd very likely use third-party libraries or frameworks such as Cocos 2DX, Unreal, Spring, CryEngine, or others. Why would we use third-party libraries? Well, that's pretty easy, because these libraries take a tremendous amount of effort to develop, and chances are high that the functionality you need has already been implemented and tested and ready to use. So why reinvent the wheel? Reusing existing functions and classes from existing libraries is great. But even then, you still need to write your own C++ functions and classes that are specific to the problem you're trying to solve. We'll talk about classes and object-oriented programming soon. In this section, we'll focus on functions. Functions allow us to modularize our program. This is a big deal since we can divide our program into logical, self-contained units of code that we can reuse whenever we need to. Let's see a simple example. On the left-hand side of the screen, you can see a program written in the way we've been writing them up to this point. Lots of statements, one after the other. Some of these statements might be if statements, some might be looping statements, but you can see that this program has three logical sections, one for input, one for processing, and one for output. But everything's in the main function. This is okay for relatively small programs like the ones we've written, but as programs get larger and more complex, this breaks down quickly, and the code becomes difficult to manage. Also, we tend to copy and paste code a lot since we may need the same functionality in different places in the program. There's a field in computer science called software engineering. Software engineering is all about designing your solutions and writing your code in a way that can be easily understood, debugged, and extended. One of the fundamental principles in software engineering is abstraction. Abstraction is exactly what functions help us achieve. Let's look at the example on the right side of the screen. In this case, we've replaced 10 statements with 3. These 3 statements are function calls. Now, when we look at our main function, we see less detail, more abstraction. We can now see read input, process input, and provide output. So we've modularized our program. We know that we still have to execute all the code we had before, but we've removed it from main and replaced it with a call to functions in each case. Let's see what these functions look like. On the left side of the screen, we see the same main function with the 3 function calls. And on the right side of the screen, we see the implemented functions: read input, process input, and provide output. Notice that each of these functions executes the same statements that we were executing previously in the main function. This makes our code more modular, more readable, more maintainable, easier to debug, and easier to reuse. Let's see how this can help us develop programs. A common analogy that's used when learning about functions is the boss-worker analogy. Let's assume you're the boss and you need to get a task done. This task involves several subtasks, and your job is not to perform the individual subtasks, but to coordinate the execution of those subtasks and report the synthesized results back to your own boss. So you've hired 3 workers that have expertise in each of those subtasks. So you assign a subtask to each worker and provide each of them whatever information they need to perform it. Since each of the workers knows exactly what to do, when they complete their subtask, they report their results back to you. This may simply be a comment that says, "I'm done," or it could be a complex report that they created and provide to you. Now that all subtasks are completed, you look at the individual results, synthesize the report, and give it to your boss. Sounds like an easy job being a boss, right? Actually, no. The boss needs to know what worker to assign the specific subtask to, the order to do them in, the information to provide to each of them so they can do their job, and the boss needs to know what he or she is getting back in order to synthesize it and report back. This is a great analogy to using functions. If you need to call functions, you write your code to the function specification. You need to understand what the function does. You need to understand what information the function needs. You need to understand what the function returns to you. You need to understand any errors that the function may produce and why. You need to understand any performance constraints, and so on. What you don't need to worry about is how the function works internally. Unless, of course, you're the programmer coding the function. This is super important to understand. When we use string, vectors, math functions, complex image processing libraries, collision detection in games, we don't need to know how those algorithms work. This concept is called information hiding, and we'll revisit this again when we talk about object-oriented classes. Let's see an example of this. C++ has many libraries. One library is a mathematics library. In order to use this library, we must include CMath. The CMath library has many mathematical functions, including trig, exponential, logarithmic, power, rounding, and many more kinds of functions. These functions are global functions, which means they're available to the entire program. We call these functions by using their name followed by a series of arguments. In the output statement on this slide, we're calling square root and we're passing in 400.0 to it. The square root function will calculate the square root of 400 and return the result which is printed. In the last example, we're calling the power function, which expects 2 arguments. In this case, we're calculating 2.0 raised to the 3.0 power. Notice that to use these functions, all we need to know is what they do, their name, what they expect from us, and what they return to us. How the square root or the power is being calculated isn't something I need to know to use them. That's classic abstraction. There are many built-in functions and classes in C++. However, we'll need to learn to design and write our own. In this section, we'll learn to write our own functions. Here's a preview of a very simple function so you can see where we're going. Don't worry about the syntax, I'll cover all that later. In this case, I have a function called addNumbers, and it expects 2 integers named a and b. The body of the function simply returns a plus b. So we take the sum of a plus b and return the result to the caller. Notice the int to the left of the function name. That tells you what the function returns. In this case, an integer. Pretty easy, right? Now every time we need to add 2 integers, we can call addNumbers and supply the 2 arguments that the function expects. Then I can do whatever I want with the result I get back. In this case, I'm displaying it. I know what you're probably thinking. Why in the world would I write a function that adds 2 numbers when I can just use the plus operator? Well, normally you wouldn't, but suppose we had a requirement that if any of those numbers is negative, then we must return 0. Let's see how we can modify this function. So this is what the function might look like if we had to return 0 if either a or b is negative. It would probably be a good idea to give this function a better name, but hopefully this preview example gives you a good high-level view of a simple user-defined function. Let's head over to the IDE and use some of the functions in the C++ standard library. Before we learn to write and define our own functions, it's important to understand to use functions that are already defined for us. I've opened up a browser and I've gone to cppreference.com. I'm going to show you 3 pages within this website, and I'll provide URLs and the resources for the course. Here I'm going to the C++ standard library header files. Here are all the standard header files in C++, and you can see there's a whole bunch of them. This would become your next learning experience in C++. Once you understand the basics of the programming language, once you understand object orientation within C++, then it's a matter of learning what's out there and available to you. There's a lot of stuff out there and there's a lot to learn, but don't worry, you won't learn it all at once. You'll learn it little by little as you use C++. What I want to do here is I want to talk about a couple of libraries, and we'll run a couple of example programs using those libraries. We'll use some of the functions in those libraries. The first library we'll use is the math library, and I've got a pane open right here to the CMath standard library header. Now we're going to use some of the functions in here. You can see that they're all defined, and if you need information about any of them, you can just click on here and you can learn about them. We're going to use the square root, the cube root, and the power function. They're just like what you would think, right? You pass in a number, you get the square root. You pass in a number, you get the cube root. And in this case, I pass in two numbers to the power function, and it will raise the base to some exponent. And here's a whole bunch of information about those functions. Okay, we're also going to do sine and cosine, and a couple of other interesting and very useful functions: the ceiling, the floor, and round. The ceiling of a floating point number is the next integer. So if my number is 12.4, the ceiling would be 13. The floor is the other way around. So if I have 12.4, then the floor will be 12. And rounding works just like you would expect. 12.5 rounds up to 13, 12.4 rounds down to 12. So that's what we'll do. And then in the next little program we'll write, we'll come to the C standard library, and I'll open up that website for you as well. This is C standard lib. That's the name of the library header. That's what you need to include. And there's a couple of functions in here that we'll use, and I'll scroll down just a little bit. They're right here. It's rand and srand. Rand generates a random number, a pseudo-random number, and I'll explain what that means in a little bit. And srand seeds the random number generator. So what we'll do is we'll use this function, rand, to generate the number. Let's say we're rolling a six-sided die and we can get something between 1 and 6. We could really make that between anything and anything, and I'll show you how to do that. And then we'll seed that random number generator so that the patterns of numbers we get will differ every time. So I'm going to head over to the IDE now, and we'll start with the math functions. Okay, so I'm back in the IDE, and I'm in the section 11 workspace in the math project. And here we're just doing some real simple math examples to show you how to use these functions. First of all, we're including CMath. That's required. Otherwise, you're going to get a lot of compiler errors because the compiler won't know about square root, it won't know about sine or anything else. In this little example, I'm declaring a double called num, and I'm asking the user to enter that number. Once the user enters the number, I'm simply calling the square root function that will return the square root of the number, and we'll display it right in line. The cube root, the sine, the cosine, the ceiling, the floor, and we'll round that number. Then after that, I'll ask the user for another number, which I've defined called power. In this case, we'll raise that number that they typed into this power. So if they typed in 2.5, we'll raise it to whatever power they wanted to. And again, here what we're doing is we're calling the power function right here, and we're passing in the number and the power to raise it to. Pretty simple. You can see from this code, I don't know how square root works or cube root works or sine or cosine or power. I don't know how this stuff is implemented behind the scenes. That's the whole point. I don't care. I don't need to know. And this is where abstraction really shines, because we're just trying to solve a problem. And I know I need to raise something to a power, or I know I need a sine or a cosine. I can simply look up the library, understand how that function is being called, understand what that function returns, and then just use it and use the result. So let's run this program. And let's say the number we enter is 125.6, and I'll press enter. So the square root of 125.6 is 11.2071. The cube root we expect to be right around 5, right? Because 5 times 5 is 25, times 5 is 125. So that gives us, it's not a formal test case, but it's a pretty informal test case that makes us feel good that our code is working. Here's the sine of the number, the cosine of the number. Now the ceiling of 125.6 is the next integer up, which is 126. The floor would be the integer down, which is 125. And in this case, we round 125.6 up to 126. So let's enter a power. Let's raise this to the 4.2 power. There you go. That's a pretty big number. So 125.6 raised to the 4.2 power is 6.54269 times 10 to the 8th. There you go. We've used the math functions without knowing anything about how they're implemented. That's a real powerful place to be. Let me go back to the IDE now, and we'll create some random numbers. Okay, so I'm back in the IDE and I'm still in the Section 11 workspace. This time I'm in the random project. Now, in order to use random numbers, I'm using the rand function. Now, the rand function has been used a long time in C++ and in C as well. But there's a better way to create random numbers if you're really doing statistical processing, and that's the random header file. I'm not going to cover that. I'm just going to use rand since that's what we're learning about calling functions. But if you really need very precise distributions, consider using the random header file. Okay, so in this case, we're including the C standard library that gives us the rand function. And we're also including the ctime library. I'll talk about that in a minute. In order to use random numbers, we really need to seed a random number generator. Now, what's a random number generator? A random number generator is just a generator that creates random numbers. Computers are real bad with random numbers. We have what are called pseudo-random numbers. What that means is that the numbers themselves are random, but the sequence that they're generated in is not. So in order to create more real random numbers, we want to seed that random number generator with a different value each time. That way it creates different sequences of values. So we'll do that in a second. I'll do it without seeding and with seeding so you can see the difference. But let's talk about what's going on here. I need a random number generated, right? So I'm going to create a variable called random number and I'm initializing it to 0. And then what I want to do is I just want to loop and create 10 random numbers. And that's what my count variable is. I can make that as whatever I like, but in this case, it's a 10. And then in this case, I'm assuming we're rolling a die. So I want to return a random number between 1 and 6 inclusive. So 1, 2, 3, 4, 5, or 6. This could be 1 to 10. This could be 1 and 2 if you're flipping a coin. This could be anything you like, whatever range you like. This is how you would create that range. And I'm just going to create min and max to be 1 and 6. You can modify those to whatever you like to create whatever range you need. Okay. Now, the rand, if you look at the rand function in the documentation, it says that it returns a random number between 0 and rand max. I have no idea what rand max is on my system. It'll probably be different on your system, but it's guaranteed to be at least 32767. So I'll run it here and we'll see what we get. Now this function right here is the one that's seeding the random number generator. Remember, we want to seed this random number generator with a different number every time that we run this program. So what better way to seed it than with the system time? And that's what's going on right here. I'm seeding the random number generator to, I'm calling the time function and passing in a null pointer, which is 0. This line of code right here, you can see an example of that in the docs that I showed you earlier. It shows you exactly how to seed the random number generator. So now we've seeded the random number generator, and what we want to do is we want to generate 10 random numbers. So I'm going to start from I equals 1, while I is less than or equal to count. So I'm going from 1 to 10 by 1. There's my increment. And then each iteration of the loop, I'm going to call rand. Rand returns a number between 0 and 32767 or higher in this case. I have no idea what rand max is on my system. We'll see in a minute. I need to really scale that number down because I only want numbers between 1 and 6. So if I take rand and I take the modulus of it based on max, right? So take rand, divide it by 6, and whatever the remainder is, I've scaled that number down now. So in this case, if I divide a number by 6, the remainders are either going to be 0, 1, 2, 3, 4, or 5, right? Those are the only options I have. But since I want to go 1 to 6, I just add min to it. And it's as simple as that. So that's going to give me a number 1 through 6 inclusive. And I'm going to output it. So let's run this program and see how it runs here. I'll build and run. And rand max on my system is 32767. So now we know what it is. And here you can see that I'm generating 10 random numbers 1 through 6. So I'm getting 2 2s, a 5, a 3, a 1, a 2, and so forth. If I run this, remember the first sequence there is 2 2 5. So let's run this again. And now I've got 4 6 3 as the first 3 numbers. And I'll run this again. And now I've got 2 2 1 and so forth. Now, if we did not seed that random number generator, let me comment that line out right here. If I don't seed that and run it again, you can see 6 6 5 5 6. Okay, let me run it again. 6 6 5 5 6. So we see the numbers are random, but the sequence that we're getting is not. We're always going to get the same sequence of numbers. Now that can be useful sometimes if you're trying to repeat experiments and so forth, but usually you don't want that. And that's why we seed the random number generator here. So there you go. You see a couple of examples of using some built-in functions. We use the math library and we're using the random number generation library, and we're using the C standard library to generate random numbers. None of this do we really care about how the random number generator works, unless that's what really interests you, and you can dig into the libraries and see exactly what algorithms they use. But if I need to create random numbers, this is how I do it. Really easy. In this video, we'll learn how to define our own functions. Function definitions have four main parts. We'll look at the syntax of functions in the next slide, but for now, let's look at what these parts are. The function has to have a name. The name of the function follows the same rules we use for naming variables. Function names should be meaningful and provide the reader the intent of the function. For example, a function called func1 and another function called func2 may be okay when teaching functions in my slides, but what if I read some production code with function names like that? I'd have no idea what these functions are doing based on those names. Functions perform operations, so usually you see function names as verb or verb phrases. This isn't always the case, but it's a good habit to get into. The second part of a function is the parameter list. This is the list of variables that the function expects from you when you call it. For example, if you're calling a function that adds 2 integers, then the 2 integers are in the parameter list. Sometimes functions don't need any parameters at all. Suppose I have a function that simply displays hello, or a function that returns a system time to me. These functions can be called with an empty parameter list. All functions have the ability to return information to the caller of the function. In order to return information, we must specify the type of that information. So I might return a Boolean or an integer or a double or a string. Also, it's possible that a function returns nothing. For example, if I need a function to just display hello, I really don't expect anything back from that function. In this case, we say that the return type is the keyword void. Finally, functions have bodies. These are statements to be executed and they're enclosed in curly braces. You've already seen an example of this in the main function. So as you can see, a function definition is pretty logical. The name of the function, what it expects, what it returns, and what it does. Let's see how this looks in C++ syntax. Here we have a simple function definition. Notice the name of the function is function_name. And after the function name, we have open and close parentheses. In this case, this function expects no parameters, so there's nothing inside the parentheses. This function returns an integer. We specify that by providing the type of the return value before the function name. Finally, we have the body of the function, which consists of statements inside curly braces. You can see that this is the same syntax as we've used in our main function. Of course, we can have functions that return nothing, expect many parameters, and so forth. The syntax for all of them is very regular and exactly what you would expect. Let's see another one. In this case, we have the same function named function_name, but this time it expects exactly one parameter. That parameter is an integer type, and it's available for us to use in the body of the function. In this example, we have a function that returns nothing when called. In this case, we provide the keyword void before the function name. This tells the compiler that there is no return type. With void functions, we can still have simple return statements in the body of the function, but they're totally optional and not often written. If there is no return statement, it's understood that the function returns after the last statement is executed. Pretty simple syntax. Let's look at one more. In this example, we see a function definition for function name that expects multiple parameters. In this case, the function expects 2 parameters, an integer and a standard string. When the function is called, these 2 parameters must be provided as arguments in the same order as specified in the parameter list. Suppose we want to write a function that displays hello followed by an end line every time it's called. We could easily define that function as follows. The function name is say hello, it expects no parameters and returns nothing. In the body of the function, we have an output statement that just displays hello. Notice that in this case, there is no return statement required since the function doesn't return anything. Once the say hello function is defined, we can call it from main or from any other function. In this example, you see the function say hello defined above, and you also see that it's being called by the main function below. This program will display hello. In this example, we're calling the say hello function 10 times inside a for loop in the main function. This will display hello 10 times, once per line. Of course, we can define as many functions as we need in our applications to help modularize our program. In this case, I'm defining 3 functions: say world, say hello, and main. Execution always begins with the main function. So in this case, main calls say hello. So we execute say hello, and we display hello to the console. But then say hello calls say world, and we display world. So this program displays hello world to the console. Here's the same example with some other output statements sprinkled in. Again, execution always begins with the main function. So in this case, main calls say hello. So we execute say hello. Remember that when say hello is finished, we need to complete the code in main. So we display hello to the console, then say hello calls say world. And when say world is done, we complete the code in say hello. So we execute say world, and it displays world to the console, followed by bye from say world. Then we go back to where we left off in say hello and execute bye from say hello. Then we go back to where we left off in main and execute bye from main, and our program terminates. You can walk through this code and you'll see exactly what's happening. There is one caveat about function definitions. The compiler must know the function details, that is, the function name, the parameters, and so forth, before the function is called. So look at this simple example. I'm calling say hello in main, but the compiler hasn't seen the definition of say hello yet. In this case, you'll get a compiler error telling you that say hello has not been declared in this scope. We'll talk about how to solve this issue with function prototypes in the next video. But before we do that, let's head over to the IDE and write a few functions. Okay, so I'm in the IDE. I'm in the Section 11 workspace in the Function Definitions project. What I want to do here is I want to write a program that calculates the area of a circle and the volume of a cylinder. Pretty easy calculations, but I want to break everything up into functions that we define. We create our own user-defined functions. And this is what I want my main to look like. 2 simple function calls: area of the circle, volume of the cylinder. That's it. Now within those functions, we can prompt the user to enter the radius, the height, whatever else we need. Okay, so let's get started. Let's write that area circle function first. Now in this case, I don't want to pass anything into the function or return anything from the function. This function is simply going to ask the user to enter the radius of the circle. It's going to call another function that will actually calculate the area, and it'll print the result. Okay, so let's write that function. We'll start with void since it returns nothing, and the name of the function is area of the circle. That's it. Simple as that. Nothing in the parameter list right now because we're not passing anything in, as you can see here in the call. Okay, so what do we need? Well, we need to ask the user for the radius of the circle, right? So we need a variable here, and we'll just call it radius. And double is perfect. We'll initialize it to 0. And we'll say, we'll prompt the user and we'll put a new line at the beginning. We'll just say enter the radius of the circle. That's it. And we'll read the input into the variable we just created. Okay, you can see this pattern happening over and over again. It's pretty standard. Okay, now what do I want to do? Well, now I want to call another function that actually calculates the area. That function, again, remember the area for a circle is pi r squared. That function needs to know the radius in order to calculate the area. Let's write the function call first. We'll say something like cout, and we'll do something like, again, the area of a circle with radius, whatever they typed in, which was radius in this case. And then we'll say is. Now, what do we do? Now we need to call a function that actually calculates that area and gives me back the double that I can display here. Okay, so let's call that function calc area circle. And that function expects the radius, right? And then we'll print a new line at the end. And really, that's it for this function. Let me clean that space up right here. All right. So now we need to write the other function, this function right here, calc area of the circle. Obviously, we need to return something from that function, right? The function is calculating the area, so it needs to return something to me so that I can display it here. So in this case, I want to return a double. And let's call it calc area of the circle. And what does it expect? It expects the radius, which is a double. What does it do now? It just returns pi r squared, right? Simple as that. But we haven't defined pi. Let's define it up here. We'll say const double pi, and we'll set it to 3.14159. That's close enough for this example. So there's my pi. It's constant, which is what we want. We don't want to be changing pi. And in the function body here, all we need to do really is just say return pi times the radius squared. We could use the pow function, or we could just say, radius times radius, which is what I'll do right here. That's it. That should do it. Let's walk through this. We call area of the circle, transfers control over to this function. We have a radius variable right here. We're asking the user to enter the radius of the circle. We're reading it, and then we're passing that value into this function, calculate the area of the circle, and it's going to calculate the area of the circle and return that value back to me, which I'm going to print right in here. Now, I could store that into a variable or do anything I want with it, right? So let's run this and test it out. Oops, let me comment out volume of the cylinder because we haven't written that one yet. That's the next one we'll write. So the radius of the circle, 12.5. It says here the area of a circle with radius 12.5 is 490.873. Okay, obviously we'd want to test that to make sure that that's correct. And that's pretty much it, right? Pretty straightforward. Now let's write this one right here, the volume of a cylinder. Well, how do you calculate the volume of a cylinder? Well, the volume of a cylinder is pi r squared times the height of the cylinder, right? And I'm not using any units here. You can think of this as inches or centimeters or meters or whatever you like. It doesn't really matter too much. So we need to write this volume cylinder function. This is going to be very similar to the area circle function, right? It's just going to prompt the user for some information. In this case, it's going to prompt the user for the radius of the cylinder and the height of the cylinder. So let's write it. We'll say void volume of a cylinder. And the reason that that's popping up in the completion is because I had that in there before, and I guess it remembered, which is kind of handy. All right, so we need the radius of the cylinder, and we'll initialize that to 0. And we also need the height of the cylinder. We'll initialize that to 0 as well. All right, so let's ask the user. Let me just copy and paste this to save a little typing time. So what is the radius of the cylinder in this case? And we'll read that into radius. Perfect. And then what we'll do here is we'll copy these guys as well. And we'll ask them for the height of the cylinder. Enter the height of the cylinder. We'll read that into the height variable. All right, so now we've got everything we need. So what do we do now? Well, let's do the output statement, right? We'll say cout. And we'll say the volume of a cylinder with radius. And we'll provide the radius value here. And then we'll say something like and height. And we'll output the height here. And finally, we'll just say, just like before, is. Now we need to call a function which you haven't written yet, right? So let's call it calc volume of the cylinder. We'll write that function in a minute. Now, what do we pass into it? Well, we need to pass in the radius and the height. Doesn't matter what order you put it in, but that's the way you have to provide the variables. So I could have said height radius and just sent in the correct ones. So in this case, I'm going to write that so it expects the radius first and then the height, and then we'll print a new line at the end, and that'll be it. Okay, so that's where we're at with this function. It's finished now, so let me clean up some of this space right here. Now what we need to do is write that function, calc volume cylinder. So let's do that, and we'll do it right here. We'll say, actually we'll do it a couple of lines up right under the other calculation, right here. So we'll say double, because it returns a double, calc volume of the cylinder. It expects the radius, which is a double, and it expects the height, which is also a double. Right? So in this case, what do? We return pi radius squared times the height. And that gives us the volume of the cylinder. That should do it. We're calling volume cylinder now, so we'll do it 2 times. Now we'll get the area of the circle, which let's say it's, again, let's just say 10. And that's correct. That's what we expect, right? Pi times 100. So what's the radius of the cylinder this time? Well, let's say it's 12.1. And what's the height? Let's say it's a really tall cylinder, 25.2. So the volume of the cylinder with radius 12.1 and height 25.2 is 11,591. And we just need to put a little space after the is there. Okay, now there's one thing that we could do to make this a little better. You'll notice that this calculation right here, pi r squared, we're doing it again right here. So what we could do is we could refactor this code just so it's a little better, and we could say return, and what we could do is we can calculate the area of the circle and pass in the radius to it, and then multiply that by the height. That way we're reusing that function. Okay, so hopefully you can see what's going on here. The volume of a cylinder is the area of the circle times its height. So we may as well just call that function to do it for us. You can see the repeated code. Okay, so there you go. That's it. We've created, and let me run that again just to be sure that we're working correctly. See 12.1. So what's the radius of the cylinder? 10.2. And let's say it's 30.1. And there we go. Okay, so that's it. You can see how really straightforward it is. And the nice thing about this is when you read your code, you can see your main, and it's really easy to follow, right? Before in our main, we had all of this stuff in there. Now we're just saying area of the circle. Oh, okay. And remember, I can call these as many times as I want. In this case, it's going to ask me 2 times. I could put them in loops. I can do anything I want. So what's the radius of a circle? 10.1. Okay, it's asking me again, because I called it again. 10.2 this time. Then it goes to the radius of the cylinder. Okay, so that's it. That finishes off this video. You can see how easy it is to create these user-defined functions. And this is really what you want. You want your program to be modularized and have these small, well-defined units that do what you want it to do and just do one thing really, really well. In the previous video, I mentioned that the C++ compiler must know all about a function before it allows that function to be called. I didn't say why though. The reason for this is that the compiler can't check to see if the number of parameters passed in and their types are correct when the function is called, unless it knows about the function being called before it's called. There are 2 ways we can make this happen. The first way is to make sure we define all functions before they're used. This is okay for many small programs, but it quickly becomes very difficult to do. And in the case of 2 functions that call one another, it's impossible. So rather than have to worry about the order in which we define functions, C++ allows us to create function prototypes. Function prototypes tell the compiler all it needs to know about a function so that it can be sure that the function is being called correctly. Function prototypes are also called forward declarations, since you're basically telling the compiler, hey compiler, this is what this function is going to look like, make sure I use it that way. In smaller programs, all the function prototypes are generally placed near the top of a program, usually after the pound includes. As programs get larger, we split our programs up into multiple files, so we include .h or header files, and we include function prototypes in these files. We'll see that a little bit later in the course. Let's see what these function prototypes look like. Here I've defined a function called function name at the bottom of the slide. The function prototype for this function is the first line of code you see. Notice that it looks very much like the function header. That's the part of the function definition right before the body of the function. With a function prototype, the compiler doesn't need to know what the implementation of the function is, only its header information. So in this case, it knows that you'll later define a function named function name that expects no parameters and returns an integer. And if you use a function named function name, it will enforce those conditions. If you try to use it in any other way, say by calling it with an integer in the parameter list, then you'll get a compiler error. Pretty easy, right? You can have as many prototypes as you need, 1 per function, and it doesn't matter what order you declare them in. Let's take a look at another one. In this case, we have the same function named function name, but this time it expects exactly 1 parameter. So we provide a function prototype to the compiler that has an int in the parameter list. Note that we can supply the name of the parameter if we wish, but it isn't used by the compiler. The compiler doesn't care about the name, only the type. So either of these function prototypes can be used. Best practice is to provide the parameter names for documentation purposes. Let's see another example. In this example, we have a function that returns nothing when called. So the function prototype must include the void keyword prior to the function name, just like the function definition does. In this case, the function expects two parameters, an integer and a standard string. So either one of these function prototypes in the slide is valid. In one case, we provide the parameter types and names, and in the other, only the parameter types. The function prototype for the say hello function we saw in the previous video would look like this: void, say hello, and then the empty parameter list. Notice the semicolon at the end. That's very important. We're not specifying a body, only the prototype. If we try to call this function in any other manner, we'll get a compiler error. So let's see how the compiler uses this information in the function prototype to help us write code. The function prototype here says that I'll define a function named sayHello that expects no parameters and returns nothing. Then I use or call the function in main. The first function call is fine since it matches the prototype. The second function call will cause a compiler error. We told the compiler that the function expects no parameters, but we're passing in an integer to the function call. The compiler won't allow this. The third function call is within an output statement. Think about this one for a second. You're telling the compiler to display the value that sayHello evaluates to. But the function prototype says that the function sayHello doesn't return anything. So the compiler gives you an error since something's not right. In this slide, I'm providing the same code that you saw in the previous video. However, in this example, I'm providing function prototypes for the sayHello and sayWorld functions at the top of the file. Now the compiler knows about these functions, and I can call them in any order I wish in my program, and the compiler will make sure that they're called as intended. Let's head over to the IDE and prototype some functions. Okay, I'm in the Code IDE, and I'm in the Section 11 workspace in the Function Prototypes project. What I'm going to do here is, I'm going to take the sample that we did in the previous video, where we calculated the area of a circle and the volume of a cylinder and so forth, and I'm going to rearrange these functions to actually break the program. Now this worked because I was very careful about how I defined these functions and where I defined these functions. So again, the compiler is going straight down and reading the source file. So it sees calc area defined here, calc area of a circle. Then it sees it used. Since it's already seen it defined, it's happy about that. In this case, it's the same thing. It sees calc volume of the cylinder. I use it down here. It's happy about that. So everything it's seen before it's being used. But if I take some of this code, let's say that I take all of this code actually, right before my main, and I just cut it, and I'm going to paste it after the main. Okay, so now we've got some issues because the compiler is now seeing, and let me clean up this white space a little bit. The compiler is now seeing area circle function being called, but it hasn't seen the definition yet because it comes later. That's going to cause an issue. Same thing with volume of the cylinder. So you're going to get issues here. So let me run this, or compile it actually, it won't run. And there you go, area of the circle was not declared in the scope. So it has no idea what that function's all about because it hasn't seen it yet, okay? You're going to get two errors here. If we change the order and put this guy down here, we're going to get even more errors because now we're using something before it's being seen. So now we're going to get probably 3 errors, right? So that's a problem. How do we fix this problem? Well, that's where function prototypes come in. Okay. So let's use function prototypes. They're really, really easy to use. What I want to do is for every function that I'm defining, I want to prototype it before I've defined it. So obviously at the beginning of the file. And we'll do it right after the namespace statement. So let's look at this first one here. I'm just going to copy it and paste it because basically that's what I want. So I'm going to put it right here. And I'll just put a little comment here just so you know what's going on. So here are my function prototypes. Remember, the function prototype is only the name of the function and what it expects and what it returns with a semicolon at the end right here, no function body. So now the compiler sees that you've prototyped calc volume cylinder to expect 2 doubles and return a double so it can type check that, okay? Let's deal with all of these. So let's do the next one, which is my calculate area of the circle. I'll copy that up here. and paste it, put a semicolon on the end. Now remember, we don't need to have these variable names here, these parameter names. The compiler could care less, so I'm just going to get rid of this one just so you can see. The compiler doesn't care. All the compiler needs to know is what is the type of that parameter. So in this case, double is fine. As I mentioned earlier, best practice is to put the names in there for documentation purposes, but I'll leave it out here just so you can see that it actually does work just fine. Okay. So now we've got those two. Let's deal with area of the circle, and then we'll deal with volume of the cylinder. So we'll put area of the circle right here. The order in which you put the prototypes in doesn't matter because the compiler is going to see them all. So there's the area of the circle. Notice this returns nothing and expects nothing. Okay, and then we'll do the last one, which is the volume of the cylinder. So I'll come back up and I'll put that last prototype right in here. That's it. Now if I compile and run, I'll get a clean run. So we'll put 12 and type in whatever numbers you like. Okay. So that's pretty cool. Makes it really easy to not have to worry about order and, oh my goodness, you know, did I call this? Did I define this first? This was a problem in early languages. I remember using Pascal and there was just no way to get around this. Eventually they added something like forward declarations, which really makes things handy. So this is just standard practice that C and C++ programmers use to create those function prototypes. Now, what really is nice about this, suppose that I mess up my function prototype and I tell the compiler that that area circle function that I'm going to define later, this is the way you should check to make sure I use it correctly. Well, I'm not using it correctly right there because I'm not passing an integer into it. So if this won't compile, this will give me an error right here. It says too few arguments to this function right here. So you've told it, again, remember, it hasn't seen this one down here yet, right? You've told it that that function will be used as in the prototype, and here you're not using it as in the prototype. Okay, so let me get rid of that. Also, if I send in, let's say, a 5 into here, or a 4, right? Again, this is not going to match. You've just told it that this function here expects nothing, but now you passed in an integer. So again, it's not going to like that. It's going to say too many arguments now to the function call. Okay, so let's clean that up. And that's really all there is to prototypes. Now, normally, as your programs get larger, these prototypes will end up going in a different file, in a .h file. And we'll get to .h files or header files, our own header files, when we talk about classes, because that's very common to create two pieces of the program. One is the header information, and one is the actual implementation. Very similar to what's going on here with IOStream. Those are really considered header files. So you're going to grab a lot of information from there. And that's usually where we put our function prototypes. But there you go. Let me run this again and make sure it's clean. Got a clean run here. So this I'll leave this code out there for you to play with as well. Get used to these function prototypes. We do them all the time, and it will really make your code better. Let the compiler help you every chance it gets. In this video, we'll learn more about function parameters, and we'll also talk about the return statement. When we call a function and pass data into that function, this data are the parameters to that function. In the function call, these data are called arguments. In the function definition, they're called parameters. We'll define the vocabulary more precisely in the next slide. As we've already seen, when we call a function, the arguments we use to call the function and the parameters that the function expects must match in number, order, and type. Let's see an example. In this example, we have a function prototype that tells the compiler that we'll define a function named addNumbers that expects 2 integers and returns an integer. Then in the main, I declare an integer variable named result, and we initialize it to 0. Then we call the addNumbers function and pass in the integer literals 100 and 200. The compiler will type check this function call to be sure it's valid. Since I'm passing in 2 integers and the function prototype says exactly that, then the compiler will not produce an error. You can see at the bottom of the slide that I've defined the addNumbers function. It has 2 integer parameters, a and b. In the case of the function call in main, a will be 100 and b will be 200. 100 plus 200 is computed and 300 is returned. The 300 is then assigned to the variable result in the main function. Let's take a look at another example. In this example, I didn't provide a function prototype to save space, but you should know at this point that it would be void say hello Sanders string. Notice that the function sayHello expects one parameter, and it's a C++ string object. And it displays hello followed by whatever string is in the name object. The next three statements would normally be in main or in another function. These are the function calls. The first is sayHello Frank. Notice that Frank is a C-style string literal, but the function expects a C++ string object. Aren't these types different? Why doesn't the compiler produce an error here? Yes, the types are different, but the compiler will try to convert one type to another if it knows how to make the function call work. In this case, the C-style string literal Frank is converted to a C++ string object. The same would happen if a function expected a double and I passed an int into it. The int would be promoted to the double, as we've already seen. Notice the last function call. In this case, I'm calling the function sayHello with a single string object parameter myDog, which is a variable name for a string object with the string Buster in it. Let's talk a bit about how parameters are passed into functions. In C++, when you pass data into a function, that data is passed by value. What this means is that the value of the data is passed in by copy, so the compiler makes a copy of the data. That means that the code in the function does not change the argument that was passed in. When we finish the function, the original data that was in the function call will be unchanged. This is good and not so good. It's good because since we're making a copy, we can't change the original argument by mistake or intentionally. It's not good because sometimes making a copy of data can be expensive, both in storage needed and in time needed to actually copy that data. Also, sometimes we really do want to change the actual data being passed in. Fear not, C++ has solutions for all these use cases, and we'll learn about them soon. Let's define some vocabulary used in programming languages, that is, formal versus actual parameters. Formal parameters are the parameters defined in the function's definition, in the function header. Actual parameters are the parameters that are used when the function is called, that is, in the function call statement. Many programmers and languages call actual parameters the arguments to a function. In C++, the actual parameters are passed by value or copied to the formal parameters. Let me show you an example that will make this clear. In this slide, I have a function definition for a function called paramTest, and this function expects one parameter called formal. This is an example of a formal parameter. If this function expected more than one parameter, they would all be considered formal parameters. In the main function, I'm declaring an integer named actual and initializing it to 50. I'm displaying actual, which will display 50. Then I'm calling the paramTest function with the actual parameter. This is the function call. Any parameters passed to functions here are considered actual parameters. In this case, the value of the actual parameter is copied to the formal parameter. So formal in the paramTest function will have the value 50, but it's at a different location in memory than the actual since a copy was made. I then display formal in paramTest, so 50 is displayed. Then I assign 100 to formal and display it again, so you see 100 is displayed. Now the function is done and we return back to main and we print actual. Actual will still be 50. It was never changed because paramTest was working with a copy all along. It's very important that you understand the concept of pass by value since it's critical to understanding functions. Let's talk about the function return statement next. As we've already seen, if a function is defined as returning a value of a specific type, then the function must return a value of that type using a return statement. We've already seen a few examples of this, and we've been doing it in the main function all along. If the function return type is void, then the return statement is optional. A return statement can occur anywhere in the function body, but you usually see it as the last statement in the function body. The return statement immediately terminates the function. It's possible to have multiple return statements in a function depending on the logic in your code. However, this is not a best practice. You typically want a single return statement. Remember having multiple break statements in a loop and the potential problems you could have with readability? Well, the same is true with multiple return statements in functions. Finally, if the function returns a value, then this value becomes the result of the code that's called the function. Let's head over to the IDE and see some examples of parameter passing and pass by value. Okay, I'm in the IDE and I'm in the Section 11 workspace in the Function Parameters project. In this example, what I'd like to do is go over some simple function calls that pass in parameters by value. And I want to make the point, and hopefully you'll understand that those by value parameters do not change. And that's really important to understand. So I've got 4 function prototypes here. The first one is called pass by value 1. The second is called pass by value 2. And the first one just expects an integer. The second one expects a C++ string object. The pass by value 3 function expects a vector of string objects. And the last one, print vector, just prints out a vector. So if you send it a vector of strings, it displays all the strings in the vector. Okay, so let's look at it, the first one, pass by value 1. It expects a number, and the parameter name for that number is num. That's the formal parameter. And all I'm doing is changing num to 1,000. Really, really simple. So let's look at my main. In my main, I've got num, which is 10, and I'm simply saying num before calling pass by value 1 is, hopefully that'll print out a 10, right? That's what we expect. Then I'm going to call pass by value, and I'm going to pass into it num, which is 10. Remember, pass by value 1 changes that value to 1,000. And then I come back and I print out that number again. Now, you may think that we're going to get 1,000 here, but we're not. It's pass by value. So we actually passed in a copy to that function. So the function was changing the copy, not the actual, which is this num here. So let me run this, and then I'll walk you through exactly what's going on. You can see here, num before calling, 10. Num after calling, still 10. Okay, so let's talk about that. Remember, num is equal to 10, and it's in my main. So in this case, here's my main function. And it's got a local variable in there called num, and we initialized it to 10. Then we called this function right here. So this would be pass by value 1. And I'll just call it 1, okay, just to save some writing time. So that's pass by value 1, and it expects an integer, num. So it's got its own copy of num. That's the formal parameter. And at this point, the 10 gets copied over to num. Okay, now I'm going to set num to 1,000. Remember, this num right here refers to that guy, not this one. So I'm changing the local num, the formal parameter, to 1,000. So I'm just changing this one to 1,000. I never touched this one. Now this function is finished. So this function is now finished. This is gone, and I'll talk about what gone means in a couple of videos when I talk about activation records and the stack. That's it. Now we return, and in the main we display num. Well, num never changed. Remember, this was an absolute copy of it. Okay, so hopefully that makes sense with pass by value. Let me show you another example. Here we've got another num, which is 20. So don't get confused with the names. I could use any name I want in that formal parameter. I just chose num to make a point. In this case, it's another num. So when we print here, we're going to print a 20. Then we're going to call pass by value 1 again and pass in that num. So the 20 gets copied to the formal parameter. We change it to 1,000. Again, we change that local copy. And when we come back, we still have a 20, right? We never touched the actual. So let me run this. And now we're going to see 1010 and 2020, just what we expect. Okay. It's no different when you use objects. So in this case, I'll uncomment that code. In this case, you can see that I've got a string, a C++ string object called name, and I've initialized it to Frank. And then before I call pass by value 2, I'm going to display it. That's going to display Frank. Then I'm going to pass that string object into pass by value 2, which is another function. And that function is right here. It's going to change its parameter to changed. Whatever was there before is now changed. And then when I come back, I'm printing out name again. Name has not changed because that changed here changed a copy. Okay, so let's walk through this one again. So what do we have? We have main. We've got the main function, and it's got a variable called name, and it's Frank. Okay, then we called pass by value 2. So this would be pass by value 2, and it has a parameter, right? A formal parameter, which is a variable. It's called s. and we copied Frank in there. So right now this becomes Frank. Now we say S is changed. So we get rid of Frank and we replaced it with changed. And again, these are all strings, string objects. Now we return back to main. This function is now done. I never changed the name because I never even knew about it. I was working with a local copy all along. Okay, so it's the same thing with integers as with objects. So in this case, if I run this program, you can see the name before calling passByValue2 is Frank, and the name after calling passByValue2 is Frank. Again, it hasn't changed. All right, let's do one more just to drive this point home. This is really important that you understand what's going on here. In this example, I'm using a vector of string objects. I don't think we've used a vector of string objects. We basically used, I think, vectors of integers and doubles. We can have a vector of anything. So here we're saying that Stooges is a vector of strings, and the strings in that vector are Larry, Moe, and Curly. So I'm printing out Stooges before calling passByValue3, and I'm calling this function called printVector that just prints out those strings in that vector, whatever they happen to be. Then I'm calling passByValue3, and I'm passing in Stooges, and then I'm just printing it out again. Okay, so let me run this first, and then we'll walk through it. So you can see that before calling the function, Larry, Moe, and Curly, after calling, that should say after right there, after calling the function, Larry, Moe, and Curly. Okay, so let me change that, make that correct. That way when you guys see it in the resources, you'll know what I'm talking about. So let me run that again. Okay, so before calling, Larry, Moe, Curly, after calling, Larry, Moe, Curly. So let's walk through this example. Here is the function passByValue3. So in this case, what have I got? Well, I've got my main, and my main has the Stooges variable, which is a vector of strings. In this case, it's Larry, Moe, and Curly. Right? These are all string objects. Right? Now, I call this function right here, and I pass in Stooges to it. So this is passByValue3, and it has that formal parameter v. That could be any name we want. Right now, Larry, Moe, and Curly get copied into v. So this will be Larry, Moe, and Curly. Now I execute this line right here, v.clear. That deletes these guys. So now v is empty. And that's it. Then I return back to main. What happens? This function is now gone. And when I come back to main, it still has that Stooges vector, Larry, Moe, and Curly. I never touched it because, again, I was working with a copy. In the next few videos, we'll learn how to send information in so that I can modify the actual parameters. But it's important to understand that by default, this is the behavior, pass by value, make a copy. Okay, so hopefully that makes sense. And if there are any questions, please post them on the course forums. In this video, we'll learn how we can call C++ functions using default argument values. As we've seen, when we call a function, we must provide all the arguments that that function requires, and they must be in the right order and of the right type. But sometimes when we call functions, some of the argument values that we pass in tend to be the same values most of the time. For example, if we have a function that calculates the cost of an item, we can provide the function with the base cost of the item and the sales tax rate. Suppose that 98% of our customers live in a region where the tax rate is 6%. That means that we have to provide the tax rate in every function call, even though it will almost always be 6%. C++ allows us to provide default values for arguments. So in the case of the sales tax, if we omit the argument from the function call, then the C++ compiler will automatically replace it with the default value of 6%. However, if we have a customer whose sales tax rate is 8%, then we can provide it explicitly and override the default value. As we'll see in the next few slides, we can add default arguments to the function prototype or the function definition, but not both. But best practice is to do it in the function prototype. Default arguments must appear at the tail end of the parameter list. We can also have multiple default arguments. Let's see an example that demonstrates default arguments. In this example, we have a function with no default arguments. In the next slide, we'll modify it so it does have a default argument. The function is called calculate cost, and it expects the base cost of an item and the tax rate. The function calculates the tax amount and adds that to the base cost and returns that value to the caller. In the main function, we're calling the function with 100.0 as the base cost and 0.06 or 6% as the tax rate. In this case, 106.0 is returned from the function and assigned to cost. That's pretty easy. But if 98% of our customers will have a 6% tax rate, I'm forced to supply this every time I call the function. Why not let the compiler default the tax rate to 6% unless I tell it otherwise? Let's do that in the next slide. Here we have the same function, except that the function prototype has been modified to provide a default value for the tax rate. Notice that the parameter tax rate in the function prototype now has a default initialization to 0.06 added to it. This effectively tells the compiler that if this argument is not provided by the function call, then use the value 0.06 for tax rate. Simple as that. Now notice the two calls in the main function. The first call simply calls calc cost with 200.0, which is the base cost. Since the argument for tax rate is not provided, the compiler will use 6% for the tax rate. In the second call, we are providing the tax rate. In this case, the compiler will use that and ignore the default value. This can be pretty handy. Suppose we have a function that prints documents and we have to supply the document name, the printer to print to, the paper size, the resolution, and so forth. Again, most of the time we print to the default printer with default settings, but sometimes we need higher resolution or a different printer. You get the idea. In this case, we can provide multiple default parameters for everything except the document name, which is always required. This makes writing the code much simpler. Let's add another default parameter to the calc cost function. In this example, we'll calculate the cost of an item based on the base cost of the item, the sales tax, and a shipping charge. As before, most of the times the sales tax will be 6%, and in this example, the standard typical shipping charge is $3.50. So, most customers will have a 6% tax rate and a $3.50 shipping charge. We can easily add a second default argument to this function. Notice that in the function prototype, we add another parameter named shipping, and we default this value to $3.50. The function body now calculates the tax for the item, adds the shipping charge, adds this to the original cost of the item, and returns the result to the caller. In the main function, we're calling calc cost in three different ways. In the first call, we're providing all three arguments to the function. In this case, no default values will be used, and the tax rate will be 8%, and shipping will be $4.25. In the second call, we're providing the cost of the item and the tax rate of 8%. In this case, the default value for shipping will be used, but the tax rate will use the 8% we provided. In the final example, we're only providing the cost of the item. So in this case, both default values are used. The tax rate will default to 6% and the shipping charge to $3.50. As you can see, default argument values give us the ability to make our code less verbose and potentially prevent errors by using default values rather than having to supply all of the arguments to the function all the time. In the next video, we'll learn about function overloading. Before we talk about function overloading in the next video, let me go over default arguments. I'm in the Section 11 workspace in the Default Arguments project, and this is the same example you saw on the slides. Here I've got a function called calculate cost that expects three doubles: the base cost, a tax rate, which is a default argument at 0.06 or 6%, and a default shipping, which is $3.50. Now, if those arguments are not supplied, then the defaults kick in. It's really pretty simple. And here's the calculation. Notice I don't have to include the function default arguments here in the function definition, only in the function prototype, and that's usually where you see them. So the code here says base cost plus equals base cost times the tax rate, so I'm figuring out what's my tax, and I'm adding the shipping to that, and then I'm adding the whole thing to base cost. So I'm not taxing the shipping. And then we've got some sample calls. In this first example, I'm calling calculate cost with all three arguments. So in this case, none of the defaults will be used. I'll use 100 for the base cost, I'll use 8% for the tax rate, and I'll use $4.25 for the shipping charge. I expect to get back $112.25. For this example here, I'm providing the first two arguments, and I'm not providing the shipping. So in this case, it's going to use 100 as the base cost, 8% for the tax rate, and it'll default to $350 here for the shipping. And in this last example, I'm supplying the base cost only. So in this case, 6% and $3.50 are what are going to be used. So if I run this program, you'll see that our results are exactly as we expected. 112.25, 111.50, and 215.50. Okay, so you can see default arguments are pretty easy to use. I could also default the base cost if I wanted to. I could say that the base cost is 100. Maybe that's the typical item that most people order. So in this case, I could just simply say cost is cost, right? With nothing in the parentheses. So I'm not supplying any arguments here. That's it. So what's going to happen here is it's going to use all three default arguments. So let me print that out real quick. So in this case, we expect the same result as well, if we would have done 106. So we'd have 100 is the base cost that's being used by default. We're using a 6% tax rate, so that's another $6. And our shipping would be $350. So in this case, we expect $109.50. So let's give that a shot. And that's what we're getting here, $109.50. This is pretty straightforward. The only rule with default arguments is that once you create a parameter that has a default value, then you've got to default the rest of them. So in other words, I can't say that base cost is 100 and then not have one here, because that's going to give me an error, right? Once you start, they all have to be on the tail end. So in this case, I could just say 0.06. So that's really the only rule there. And I'll run that again just to make sure I've got no errors, and there you go. So let's add another default type function to this application. How about a greeting function? So let's do something like this. Let's create a function prototype here for a function called greeting that expects a string, which is someone's name. Now let me include string because I need the library. So that's a string name. Perfect. So that would be Frank, Metropolis, Joe Miller, whatever you want. Then I've got another string, which is the prefix that we want in front of their name. Mr., Dr., Mrs., whatever you like. And I'm going to prefix it to Mr. Let's say that most of my customers are male. And I also want a suffix. And in this case, the suffix, I'm going to default it to just the empty string. Okay, so that's my function prototype. Let's implement this function now. We'll implement it right down here. And at this point, we don't need those default arguments. We can just get rid of them from here. And it cleans up the code a little bit. All right, so what do we want to do here? We just really want to display some stuff, right? So let's just say I want an output statement, and I'm going to say hello, followed by a space, followed by the prefix. And what we could do here is we could append a space. Right? We can use concatenation here, and the name, and another space, and the suffix. Okay, so we're just using concatenation here, just like we've learned in string class. And then we'll use the end line to finish it off. Okay, so let's run that and give it a few example runs here. So let's say, how about, let's do a really simple one. How about greeting? And I'm going to supply all of these arguments. So I'm going to say Glenn Jones is the name. Okay, the prefix will be doctor, and the suffix will be MD. Okay, so if we run that, we expect this to display Dr. Glenn Jones, MD. Okay, so let's give it a shot. And I forgot the semicolon. I'll fix that real quick. And there you go. Hello, Dr. Glenn Jones, MD. Perfect. Now let's run some of the other examples. So how about we do something like greeting James Rogers. How about professor and PhD for the suffix. Okay, we'll run that. And now we'll say, hello, Professor James Rogers, PhD. Pretty easy. Now let's use some defaults. In this case, we'll say greeting. Let's say Frank Miller and doctor. No suffix in this case, so it'll default to the blank or the empty space. So in this case, it'll just say Dr. Frank Miller, which is what I want. And then let's do one more. And we'll just say greeting. Let's say William Smith. So in this case, it's going to use all the default values. So it's going to use Mr. William Smith followed by the empty string right there for the suffix. Okay. So in this case, we're just going to see Mr. William Smith. There you go. Okay. If we have Mary Howard, and she would be Mrs. And we can give her a title as well. Whatever we like. There you go. So now we've got Mrs. Mary Howard, PhD. Instead of doctor, we could have said doctor here as well. You can see all the different combinations. This can come in pretty handy. I used to work with someone who used to say that if something is always required, then it should never be required, which makes a lot of sense. And I think that's part of the idea behind using default arguments and using overloading, which we'll talk about next.